was missing audio, so you guys hear me now? All right, so I was saying, welcome to FOSSXR Day 2, and I hope you guys enjoyed last day, and we're gonna have another series of very interesting talks today. There's something I'd like to, get your attention on is that that panel discussion we're gonna be having right at the beginning of the launch time, for this first half, actually, of the launch time. So it's going to be a panel discussion. You're all invited to come to see me if you're interested in participating in a more involved way, getting the bikes and, interacting with our people, because we're going to be holding that with people in Brussels right now, taking part of the LVRM conference, which is the Libre virtual reality meetings in Brussels. So those discussions are going to be driven by Olivier Meunier down there. We're also going to have Christoph, who's one of our virtual presenter. Christoph's also in Brussels right now, so check that out on the website, and please come see me if you want to take part in a more involved way in this today. And so I'd like to give you some context for this. If you don't have time to check it out, just going to read a paragraph, what it's all going to be about. So here's the context for that talk. So in Europe, the GDPR is in place since 2016, and with enforcement since 2018. And the EUC has issued in 2020 and the rest that kind of scrapped the Safe Harbor Treaty, and challenging the use of US tech services in the countries of the Union. And so in this context, and in the probable incoming of other privacy protecting laws in the US and elsewhere, the development of VR technologies need to take data sharing very seriously now. So the use of FLOSS tools is particularly well adapted to this situation, with transparency, of course, in the auditability and interoperability of the at core of the tech. And so the discussion will be about how we can enforce that data privacy is safeguarded through interoperable platforms and tools, and what to do with that safe harbor being down now, and how to build the metaverse, for example, while respecting user privacy. And so it's a big subject. We're going to have like a good chunk, maybe half an hour, to discuss this on either side of the ocean. So check that out. And so again, I'd like, of course, to thank our sponsors for making all of this possible. So our sponsors, the Kronos Group and Collabora. Thank you again for being part of this and supporting our mission, our open source centric mission. And I, of course, would also like to thank the code weavers, guys, without whom none of this would have been possible. I mean, they've done an amazing job. And yesterday with the venue and with the AV setup, and even the happy hour, so everything just went super fine. Thanks to them, and especially Adek. Big shout out to you, Adek, for all your support. So thanks a lot. And so with all that being said, I wish you, of course, a very good day 2 at FOSSXR, and thank you very much. Cheers.
Hello, hopefully that is live now. Hi, my name is Jan Schmidt, and I am here to talk about writing open source drivers for Oculus Rift headsets. I'd first like to say thank you to Frederic for giving me this talk slot first thing in the day. I'm calling in from Australia where it's 1:30 in the morning, and I'm glad to be doing the presentation a bit earlier in the night rather than late. So I've been working in my spare time on reverse engineering and writing drivers for Oculus Rift headsets and Windows mixed reality ones inside of two projects, inside of Monado, which we've talked about a lot in FOSSXR already, and in OpenHMD, which is an older project for providing VR headset drivers. I'm going to talk about the two Oculus Rift headsets. There's the CV1 and the Rift S, and to some extent the older DK2. I want to talk about the CV1 tracking branch that I work on in OpenHMD, and the newer Rift S driver, which I originally implemented in OpenHMD and which I've recently ported to Monado. So let's see. By the way, I do this on weekends and in my spare time, so it's a very long project in that sense. It's been 2.5 years of hacking away at it. So these are pictures of the two headsets I want to talk about. The Rift CV1 that came out in 2016 and can be considered the first real consumer VR headset, in conjunction with the developer kit one that came out, precursor Kickstarter kit. It used outside-in tracking, where we have these two cameras shipped with two. It's recommended to use 3 or even 4 to get a full surround view of the user. And those cameras view what the user is doing and then turn that into positional tracking. Then later in 2019, Oculus/Facebook released the Rift S, which then flipped things around and did what Windows mixed reality headsets were already doing, which puts cameras onto the headset and uses those to observe the surroundings and do SLAM tracking, as well as observing the controllers to generate controller tracking. I'm not going to talk about the standalone Oculus headsets, the Quest and the Quest 2, because they do all this stuff themselves. There's relatively little for us of interest for people to do in terms of PC VR and OpenXR stuff. They kind of do it all themselves. The only part that people can look at for doing open how did the CV1 work? Well, we have the cameras. On the PC talks to the headset and talks to the controllers via a radio link through the headset, and it reads out firmware blocks that tell it where those LEDs are, what are the 3D models of the LED positions and the normals. Oh, sorry. I've just been told to pause for a second. Right, technical difficulties. Okay, I'm back. So we read out the LED models from the controllers and from the headset. We get something that approximates the actual positions. They're calibrated at the factory to give us micrometer precision LED positions, but the headset has LEDs in a triangle on the back of the user's head, and that head strap is articulated and can stretch, so the LED positions are not exactly what we will observe in the camera, and that can cause problems with trying to match them up and extract positions. But, let's say we have a model of the LEDs. We have a camera that can view them. And the clever part here is that they use a radio signal from the headset out to the cameras and out to the controllers to trigger the exposures of the cameras. So each camera it captures each frame at precisely the same instant, and at that instant all of the LEDs are pulsed brightly, which means that the camera can run with a very short exposure. So even though it's an infrared sensitive grayscale camera, instead of seeing the room in grey like you might have seen in Moses's hand tracking talks, we just get mostly bright infrared sources. So in this photo, you can see just the LEDs of the headset and the controllers, and you can see a light bulb on the roof in the background that is generating IR. But that kind of makes it easier to find out which bits are the IR blobs. We get that, and maybe we get some noise if there's a sunlit window in the background. That's a lot of infrared. Then we track those infrared blobs, we extract the poses of the devices, and then we convert those into positions in the play space. In order to do that, we have to reference them to the position of each camera, which means we need to know where the cameras are in the room. So the next step is getting a configuration for the room setup. And anyone who's used the CV1 knows that when you do the room setup, you have a step where you have to take your device to the middle of the room and then do a room configuration step where it says, okay, I hold the headset up or hold a controller up and hold the trigger, and it watches it for long enough to get a reasonable idea that it is that it knows where those cameras are. So it can capture, each camera can see the device and then figure out what their relative positions are, and then you adjust it to match the physical position in the room. So you do that configuration once when you start up, or once when you move the cameras if you bump them. And the output of that is a XYZ coordinate for the position of each camera and a quaternion that tells you the orientation, the pose of the camera. We can also do online estimation when the tracking is running. We can compare the poses that are coming from each different camera and calculate, check, do sanity checks, do consistency checks on whether the cameras have moved or not, and then warn the user. Those cameras are pretty much just a standard UVC camera in a sense. They do output their video over the UVC interface like any webcam, but they have some quirks that mean that we can't write a standard Linux kernel driver easily, and the main problem there is that there's a bunch of non-standard HID requests with variable lengths that the kernel doesn't like. It once it sees a HID report, it caches the length of that. So when I want to talk to these cameras, I have to do UVC in user space with a custom driver. That causes some problems in that now we're trying to handle packets coming in at a very high rate, video rates in user space. So sometimes it can run into scheduling problems, and we miss packets and lose frames that wouldn't happen if we had a kernel driver. So maybe it's worth working on the kernel portion at some point, but for now it works okay. They generate 52.0833 frames per second and 19.2 milliseconds per frame, which if you do the maths works out to pretty much exactly the maximum bandwidth that they can squeeze over their uncompressed video frames. I already mentioned the frame exposure synchronization. The nice thing about that is that we have the headset in its IMU feed data is also telling us exactly when the exposures are being triggered. So as they start appearing on the UVC link, the driver can match up exactly where it relates to in the IMU data. There is a caveat, because the UVC data is coming in from each camera individually. the frames arrive at different times. So there's some housekeeping to do around matching up which frames are coming in and dealing with the fact that they're coming in at different times. So moving on, how does this system look in the Oculus Rift S system? So one, we changed so that the cameras are on the headset. They're doing a very similar job in that they are capturing the infrared view of the LED constellations, but they are also being used to do positional tracking for the headset now. So instead of the headset having infrared LEDs and we watch those, the headset has no infrared LEDs, it's just watching the controllers. So that kind of makes the tracking problem easier for the controllers. We've got fewer LEDs to see, fewer possible combinations. The LEDs on the controllers are still pulsed via a radio signal from the headset. But the problem space changes a little bit in that the camera positions are now constantly changing as you move your head around. So in order to figure out where the controllers are in the play space, we have to, at each moment, know exactly where the headset is, which then has to be hooked into the SLAM system that is going to be using this camera feed to actually track the headset movement. There's another quirk here in that the way the Rift S delivers the video frames is that all of the frames from each of the 5 cameras are packed into one big frame buffer like the screen capture here. And they're being delivered at 60 Hertz, but every second frame at 30 Hertz is a exposure of the room, followed by a fast exposure of the LEDs that looks like the constellation tracking thing. So we have, in one 30 Hertz instant, we have the SLAM extracting a pose for the headset. Then, one 30 Hertz frame later, we have another exposure where the headset might have moved, and we need to be able to predict where it is now. And from that frame, we're going to extract where the controllers are, and then reference back to the room play space to actually generate the globally tracked position. The controller tracking, well, I've already worked on that for CV1, so I think that's relatively easy for Rift S. The tricky part is the SLAM and VIO, but more on that later because, that's partially solved problem already. Right, so we have video frames. They give us those bright blobs. The same idea works for both CV1 and Rift S in a sense. But how do you take those bright white pixels and turn them into usable poses of the controllers? So the first problem is that every white blob looks like every other white blob, so you don't know which LED is which. In the early days of the CV1 and the DK2, what Oculus did was to pulse codes out of each LED. And so every frame, the LEDs would go brighter or dimmer in different patterns. And if you watched them long enough, you would extract about 10 bits of information, and those were set up as grey codes that you could determine which LED was which and get the correspondences out of them. But when the CV1 controllers were released, which was sometime after the CV1 headset came out, the number of LEDs doubled because each controller has 20-something LEDs and the headset has 40-something LEDs. So that's 80 odd LEDs to keep track of, and that's too many for the codes to work. Plus, as you move the headset around, different LEDs tend to become brighter or dimmer naturally, so the codes themselves were a bit unreliable when people started moving around more quickly or being further away from the camera. So when the controllers came out, Oculus stopped using pulse codes for the LEDs. So we need a mechanism that can work without that. We don't know the correspondences between blobs and LEDs. We need an ab initio bootstrapping mechanism for doing that. We tried at some point in the CV1 driver to use a forget the name of it. Thought algorithm that tried to converge on a solution, and it took way too long. It took 5 seconds to converge on an answer for which LED was which. So I switched to writing a sort of heuristic depth first search that sorts LEDs in the model based on their proximity and when viewed from different directions, and then it sorts all the blobs based on proximity in each image frame, and then it tries to match up combinations of 4 LEDs to 4 blobs in the image. We have an implementation of an algorithm called lambda twist, which is a P3P, fast P3P algorithm. And so for every combination of LEDs, we run the lambda twist algorithm, get the poses that might match, and then so we take 3 LEDs, 3 blobs, run lambda twist on those, and then see if it matches against the 4th point. If it does, we assess that as a possible candidate for a match and run it through a score heuristic based on how many LEDs are then expected to be visible in that pose, plus how many match up, how many don't match up. And it uses a 2-pass strategy where it tests only the nearest couple of neighbors first for each device, and then if it doesn't find anything, it will do some deeper searches, because sometimes the list of blobs is noisy. But it's still a tricky problem, right? In a very noisy environment, the blob extractor can generate up to 200 something blob candidates for possible LEDs. If you've got a bright window in the background that looks like a bunch of LEDs, for example, and there are 80 LEDs, so it can take quite a few milliseconds for that search to run. But it does work, and in general, it is pretty good. I'll hopefully get time to show a slide later and talk a bit about more about that. But that algorithm, as I initially conceived it, it worked okay, but it's slow. And at some point, I came up with the idea that, hey, I can improve the performance of the search by using the IMU in each device. So each of these devices has an IMU, an accelerometer, and a gyro that are used for tracking the rotation and acceleration of the device, and can give us a 3 degree of freedom tracking without needing any external cameras. So even if we didn't have the cameras, we can tell which way up is from the gravity vector. And if I know the camera positions, then I can take the orientation of the camera, and I can calculate which way gravity should appear in the view that we are looking at. And so I can project the gravity vector, and for each pose that the search tries to match, it can then check it against the gravity vector and reject potential poses that are not aligned with gravity, within a 20 or 30 degree match window. And that reduces again the number of viable correspondences for which we have to do a full pose check, and makes things faster again. I think it can even do better by skipping, instead of using lambda twist to calculate poses and then checking them against the gravity vector. If I get time, I can experiment with using just 2 LEDs and the known gravity vector to directly calculate what the pose must be, and then match against that, maybe. But given the uncertainty in the gravity vector when things are moving fast, that may or may not actually help. So I haven't spent the time to do that experimentation yet. But we can do even better than this. So instead of searching every frame for all of the LEDs and then searching all of the candidates, we can do a 6 degree of freedom algorithm, a fusion algorithm that is using the IMU and the data that the IMU is sending us in between camera frames to predict where it is going to be. So this is kind of the loop that I currently have in the OpenHMD CV1 driver. On the left, we have inputs. So we have the camera feeds coming in, we have the device data, the IMU data coming in, and the blob tracking algorithm incorporates predictions from the IMU fusion. So the fusion is the new piece added to the puzzle. It is receiving observations from the computer vision, joining them together with the IMU data, and then adding predictions. We predict where the LEDs are going to be in each frame, and we match them up. And in general, when we are locked on for tracking, we can zip through that quite quickly. And then we only have to do the full pose search when we lose tracking, when things move too fast, or when there's a glitch in the timing or something like that. But it wouldn't be fun if it was that simple. So there's another wrinkle to consider, that there are delays in all of these systems. These pieces of information are arriving asynchronously, and in order to prevent giving our users nausea, the poses that are being reported by the system, the latency has to be kept as low as possible, so that when the user does move, they feel that reaction with low latency and that it's correct, or people get sick. And there are quite a few delays. The first and biggest of which is that even though frames are arriving every 19.2 milliseconds from the cameras, it takes 17 or 18 milliseconds for that USB transfer to complete. And that means that we have a fixed delay. Even if it took us 0 seconds to extract the poses, we always have at least 17 or 18 milliseconds of USB transfer time to deal with, which means we have 17 or 18 IMU observations coming in before we even have a video frame to look at. Second, if you plug Oculus Rift CV1 camera into a USB 2.0 port, which Oculus recommends you do for several of the cameras. If you have 3, they recommend that you have at least one of the cameras on a USB 3 connection and that the others are on USB 2. When you plug them into USB 2, the cameras don't have enough bandwidth to output a 1280 by 960 grayscale video frame at 52 Hertz uncompressed. They have to compress it. And they do. They only offer a JPEG mode when plugged into USB 2. So we have to have a JPEG decoder in the loop here. That takes a couple of milliseconds per frame as well. Then when we're tracking, we have to search the video frame, read all the blobs, match them up against where we think the controllers and headset should be, run a ransack and refinement algorithm. And that can take between 1 millisecond if we're lucky to 10 or more milliseconds, on that order of magnitude. And if we're unlucky and we have lost track of the device, we have to go and do a longer correspondence search, which can be over 100 milliseconds if we've got a real lot of noise and really unsure about where things are. More often, though, the correspondence search is less than 40 milliseconds, but still that means we have around 2 or 3 frames of delay. At all times, there are several frames in flight in this system. One that's being captured and transferred, one that is being checked for, or decoded and checked for fast tracking, and potentially one that is queued up for a longer search that can take several frames. On the other side of it, there's the IMU fusion is running very quickly. It has to take less than 1 millisecond because observations are arriving every 1 millisecond. And that is true. It typically takes a fraction of a millisecond to run the IMU fusion. So based on, the early days I had a kind of run this loop and then update the position of the device in a hard-coded way and then do IMU prediction from there. But it was hard to deal with the latency problem in that. So in 2021, I implemented an improved sensor fusion algorithm that uses an uncentered Kalman filter and a state matrix that tracks the position, the orientation of each of the device, and extracts the IMU biases. So it corrects for static biases in the IMU data, and it compensates for the delays, the latency, using a lagged state slot mechanism, which is where for each frame that we have in flight, we augment the filter with a deferred latency entry, that as the IMU updates come in, they update the entire state matrix, but they also correct the lagged slots. And then when the observations from the computer vision finally are output, they update the lagged slots, which implicitly has kept track of what the relationship between the current base state is and the lagged state. So they will automatically do the bias updates and correct for global position and things, but it's pretty expensive as a filter. Like I said, there are 3 frames in flight, sometimes 4, but every slot that gets augmented into the state adds a position and an orientation to the state matrix, and each one, because UKFs are an n-cubed algorithm, if what I currently have is 3 lagged slots, that gives me a state matrix 41 by 41 for the covariance matrix. And because it's n-cubed, it's a bloody expensive UKF to run at 1,000 hertz, or 2,000 hertz, because we've got 1 kilohertz of IMU data for the headset and 500 hertz of IMU data for each controller. When I compile it in release mode and let the compiler do auto vectorization on this UKF, it takes a good fraction of a millisecond to run the IMU fusion. So I have been toying with the idea of, maybe I can use IMU pre-integration to quickly do the prediction and then only update the UKF at the camera rate, but I have not yet had the time to rewrite all of that code. Another downside is, because I was doing all this work in OpenHMD, OpenHMD has a policy of avoiding outside dependencies and wanting code that's in vanilla C. So there's no nice eigen, no C++, no eigen, no helper libraries here. This is all implemented in vanilla C and hand-rolled matrix code. So probably not as optimal as it could be. Lots of things I could experiment with on the fusion state, and it is the big thing that needs correcting. But it does work. It works pretty well a lot of the time. Where it gets things wrong is when the input information is noisy, and that's a problem. The poses that the computer vision extracts are not always correct, especially when you're moving controllers quickly in games. It's very, and when they're far away from the camera, there's only a few pixels per blob and they move fast, and it's easy to get them confused because they all look like each other. So we can be correctly tracking a controller and then suddenly we'll get one LED wrong. And I've found that OpenCV's ransack algorithm is pretty sensitive to that. If you have we've only got sometimes 10 or 12 correspondences between LEDs, and even one incorrect one can throw out the pose that's being extracted by OpenCV quite a lot and cause these kinds of jumps in the graph. So the yellow line is one camera, the red line is another camera, and the poses they're outputting, and it throws off the filtering, which can cause us to lose track of where the controller is, and we have sometimes a few hundred milliseconds before we can reacquire it. And in the meantime, the algorithm is just using dead reckoning to try and predict where the device is. So you can see in this graph, by the time it's reacquired here at 126.2 seconds into the run, we have a good, nearly 20 centimeters where it's drifted in the Y direction, and it snaps back. If that was directly reflected in the output poses, that would be quite a big jump in the hand controller or the headset, which really makes people sick. So what I've added is a little bit of a compromise on latency with a smoothing filter on the output a €1 filter that smooths the results a bit. So the lighter blue line is what is actually being output to the application. So at least it doesn't jump quite so badly. The latency can be felt when you move quickly, though. So I've also had to add a limited prediction time. So when we do have this 400 millisecond lost tracking, what actually happens on the output is that the device gets stuck and freezes. We don't keep predicting infinitely because you very quickly zoom the user off into infinity and make them feel very unwell. On the other hand, when things are tracking well, it can track really well and be, plenty usable and good enough. And it is very dependent on where the cameras are being positioned, how well the room calibration is done, how accurate the poses of the cameras are computed. And another thing I'd like to do in future research is to add that online continuous calibration that I mentioned, where we're continuously refining the idea of where the cameras are to lock them in more closely. And at the moment, every camera outputs its poses independently, and we don't really have any step where it combines the information from all of the cameras and checks whether they're all giving the same idea. Each camera feeds its info into the fusion algorithm. If they take too long, we drop them and move on. But if, like if one camera very quickly gives us a pose and the other one's still wringing its hands 100 milliseconds later, well, we just skip it, drop that lagged slot and move on. But, when the observation does eventually come in, we could use the combined information to refine the joint calibration of the cameras, a bundle adjustment step. So that's the state of things in the OpenCV1 tracking driver in OpenHMD at the moment in my branch on GitHub. What about Rift S? Okay, so the Rift S driver is one I originally implemented during lockdown in 2020. It was my first complete from scratch reverse engineering of a headset. When I started on CV1, I had the benefit that other people had already done a lot of the protocol work. But when I got my Rift S, no one knew how to talk to it yet. So I had to do a whole bunch of protocol reverse engineering to even be able to talk to the headset. And that's the second half of the talk coming soon, if I have time. The output of that was a 3 degree of freedom rotation driver in OpenHMD that used the IMU to track the headset and the controllers. But I always put 6 degree of freedom tracking as future work. Not quite sure how to solve the dilemma of OpenHMD not wanting external dependencies. But I procrastinated long enough. Monado grew the ability to do SLAM tracking on its own, as you will see in Mateo's talk a little later on. He's done a bunch of stellar work to give Monado SLAM tracking. He was working on the Windows mixed reality headsets, but that SLAM tracking was built in a way that it's been easy to add. So I took the OpenHMD driver for Rift S, I ported it to Monado. That's work that started while I was on holidays in April this year, and started looking at how to integrate the SLAM tracking. There were definitely some challenges. One of the things that you need to be able to do is adjust the exposure of the cameras so that you get, not just a flush, a washed out white room and not a completely black room, but you get enough detail to be able to extract features. And Mateo had written an auto exposure algorithm for WMR headsets, and I was lucky in the sense that Rift S uses the same cameras with the same exposure response. So the compensation tables that he had calculated for WMR directly apply to Rift S, and I was able to apply that directly. But I still couldn't get any SLAM tracking out of it, because we need to know, in order to track features correctly in a room, we need to be able to take this fisheye view and correct for the lens distortion. I could see in the Rift S firmware that there was a JSON block that had camera distortion parameters, but all it gave us was a bunch of floating point numbers and a name called Fisheye 62 camera distortion, which is not one that existed anywhere on the internet. So it's a distortion model that Facebook had come up with on their own. I did some reverse engineering on that by doing a hand calibration of the cameras using a chessboard and measuring a known function, and then trying a few different ideas for what the Fisheye 62 functions might look like until I generated a distortion curve that matched. And I got that done, and then discovered that at some point while I was doing that, since I last looked at the problem, Facebook had upstreamed an implementation of the Fisheye 62 distortion model to the OpenSFM project, which is also another Facebook project. So I was able to confirm that my idea of what the distortion function was matched what OpenSFM had implemented, not what OpenSFM had documented, but what the code was actually doing. I got them to fix the documentation since. But the problem is now I know what the Fisheye 62 camera distortion is, but Basalt, the SLAM library, doesn't support that model. It has a bunch of camera distortion models, but not that one. In the Windows Mixed Reality one, Mateo had already done the work to add a new distortion model to Basalt, but it didn't seem really worth it for this, you know, like a lot of work and then a whole extra thing to support that wasn't upstream, perhaps. And it meant that the hand tracking driver wouldn't work because it also doesn't support the Fisheye 62 distortion model. So I either had to implement it in multiple places or come up with another answer. So what I did come up with is using the Levenberg-Marquardt optimization, the nonlinear optimization technique, to take the Fisheye 62 distortion function and calculate a OpenCV compatible set of parameters that could be fed directly to Basalt and to the hand tracking driver. It introduces some subpixel error, but it's okay and it works great, especially for the SLAM tracking. Some weird stuff still going on with the hand tracking, but I don't think it's from the distortion anymore. So that driver is finished, merged into Monado. It does positional tracking for the headset, but we don't have the controllers. Like I said, we need to be able to predict and attach the headset pose to each camera frame that shows us where the controllers are. We need to predict 130 hertz ahead from the last SLAM tracking pose, and we need to deal with the latency of the SLAM tracking as well. Here's what the Rift S controller tracking video looks like. It's fairly similar to the CV1 driver, but it seems to have a bit more noise. The LEDs are brighter, but like you can see a bit more around them, so they're a bit more fuzzy than the precise stuff of the CV1. There's some other interesting differences in that where in the CV1 we get every frame separately, in Rift S we get all the frames together, but it's more likely, I think, that now controllers will be crossing frame boundaries. So we don't necessarily see an entire device visible in one camera. And so, you know, the algorithm I'm using for CV1, it might be good to change the way that works to use like grays out of the camera and collect all of the possibilities across all cameras and try and refine those. Things to explore when I do get to doing Rift S. But I think the general idea is that I could take the CV1 tracking, port it across, and it would work pretty well. There are lots of ideas. I have more ideas than I have time. Fusion and performance improvements, like pre-integrating the IMU, improve the pose extraction. If I can make the observations of each device less noisy, that feeds directly into less jitter. I need to figure out why I get so much jitter from the Kalman filter. It is higher than I expect. I think that is that it's not really well extracting the biases from out of the IMU data. You know, if you hold the controllers, you can see them visibly jittering in your hands, even though you're not moving them at all, and that's just annoying. I've also been working for quite a while now on a simulator a recording mechanism that captures what the cameras see along with all of the IMU data for each device, and a replay utility that can let me test out different fusion algorithms and vision systems without doing what I've always been doing, which is to write some code, compile it, launch OpenHMD or SteamVR and test it and see if it feels better or worse. It's not scientific, and it's slow and an annoying development loop. And then when I've got this working really well for CV1, take all the ideas and the working implementation and apply them to Rift S and WMR controller tracking. Now, I have 6 minutes left to do the second half of my talk. I think, and the goal in the second half was to talk about how do you go from not having any kind of idea about the protocol for your headset to being able to talk to it. So there are several places you can get information. You can look at the drivers on Windows, and you can try reverse engineering the DLLs and extracting their USB protocol and tracking from that, but that I think sucks. You can do what I did, which is to record some USB packet captures and then magically decipher them. Either one of those could be a breach of the EULA for your official runtime, and probably is, but still might be legal in your particular jurisdiction. You will have to satisfy yourself on that front. I'd also note that the log files that these software stacks write to secret directories on Windows can be very enlightening, with lots of little hints. One thing I found recently for the Rift S is that they take the camera calibration and they add half a pixel to the focal length with an entry in the log file that says adding half a pixel to the focal length to compensate for infrared light. But okay, so what I want to talk about is USB packet traces. So you take Wireshark and the USB PCAP add-on for that on Windows. You do a little research with plugging devices into your computer to figure out which USB root device you need to capture from, which for that port you're planning to plug the headset into. And I recommend doing this before you ever plug a new headset in, because it's really great to capture the first time you connect it. Usually you'll get a firmware update from the software stack and get therefore a whole bunch of packets that you might never see again if they never update the firmware again. It's also good to do a capture without a firmware update. So, you know, do a couple of captures, the first connect, the full update, room calibration, maybe pairing up controllers, and then do a capture where you're just plugging in the headset a second time as well. Have a couple of captures. Then start looking at the stack. It's pretty normal that these headsets are using the HID protocol. They appear as a HID device, and you've got get and set reports that are driving the traffic. So that's what you're looking for. You're looking for IMU data coming in on an interrupt packet endpoint. And if you're like the Rift S and the later Windows mixed reality headsets, you've likely got some radio traffic coming in from the controllers. That is often on another USB interrupt endpoint, not where the main headset IMU data is. And those packets will have all the button presses and things in them as well. You've got some isochronous feeds. You've got some video coming in for camera feeds, often, although not for Windows mixed reality, which uses a bulk transfer for those. You have an isochronous output that is usually your headphones and audio out. This is the kind of thing you want to look for in the protocol, just to get an idea about where different pieces generally lie. You want to look for common operations. So look at what happens when you first plug in the device. You can see it doing some things typically, like it'll turn on the screen or turn on the display connection, and it won't appear, the HDMI or the display port won't get connected until that packet has been sent, whatever the packets look like. And there'll be something that turns on the IMU stream at some, probably. You look in the hex dumps for the packets, look for some known values, maybe like here in this 06 packet from the Rift S, you can start to see there are 05A0, a 16-bit value in Little Endian that says it's 1440, and then next to that is a number 2560. Oh, look, that's the resolution of the Rift S. We know it's 80 hertz. There's some other numbers. We don't know what those are, but we can leave those and just log them now, maybe in a few different forms, sort of hypothesize whether they might be 32-bit or 16-bit numbers, or maybe they're just bytes. Take lots of notes. So here, looking at report ID 9, I've got some notes. It's sent right after enabling the HMD. We've got some values in there. Oh, look, and it's good to be able to recognize floating point values in a hex dump. So if you see things like it starts with 0x40 or 0xC0, or ends with it, because you've got to look in Little Endian, you can take that and just try interpreting it as a floating point value. Maybe it'll have an interesting number in there. So here's report 9 from the Rift S, once I figured that out. Then once you've got a whole bunch of these packets written out, and I sort of had looked at 10,000 packets using scripts and filtering and grouping them together and taking notes before I started to do the next step, which is to start replaying packets out to the device. At this point, this is when it's really useful to know which packets might modify firmware and which ones don't. You don't want to be modifying your firmware when you're trying to figure out what a HMD protocol is. So try and avoid those ones. Omit or reorder packets and see what happens. Try modifying values and see what happens. Pay attention to the timing between packets or whether they get repeated. Maybe we turn on the display and then we poll something else until it says, well, now the value's turned to 1, the display is online. Some operations like that take a bit of time. And if you are lucky, you can eventually tease out something like this. So this is the controller reports and some notes that I took along the way for the Rift S and the radio packets that are coming in. They start with a 64-bit radio ID. There's some unknown number that at the time that seemed related to how much of the packet was valid, and in fact turns out to tell you it's a header for each packet, each sub-packet inside the packet that tells you whether it's a valid bit of info or not. Each one has 3 bytes of debug info being sent from the controller, which you can combine together into a console log for the controller. Also, it helps to dump these in real time, because I could see from this that these IMU timestamps, hypothesized values for the timestamps, were in fact ticking up in microseconds, and you can see them clicking over once per second or so on a console log in real time, etc., etc., etc. Tease it apart. By the time I got this far, I think I had looked at 1 million packets from the Rift S. And that was how I got to writing the Rift S driver as it stands right now, and the current status of the CV1. I am a little bit over time, but if people have questions before we go to break, then feel free to fire away.
Thank you very much, Jan, for this nice talk.
Thank you.
We maybe have time for one question from the audience. Is there anyone here? I guessed it. Mateo.
Hello, Jan. Amazing work as always. Super happy that the Pascal thing has been useful to you. I want to ask about the simulator and replaying thing you're working on. Will that be compatible with UROC datasets, or is something totally different?
It is something totally different. So what I do, it's specifically for the CV1, and what I do is I take the incoming frames and I write them out as JPEG to a Matroska file, along with a horrible hack where the IMU data is serialized to JSON and written out as subtitle tracks alongside the video. I did it that way because I wanted to make sure, well, at the time I didn't know about the UROC format. I didn't know whether I would be able to write so much to disk simultaneously at these data rates, but also that it's kind of handy just to have one MKV file I can pass around and then run it through my simulator and get all of the data out of one file. So that's what I'm using right now. You could make it into, you could extract it into a UROC data set, but it is not. It has every piece of information that I wanted to store, which is specific to the CV1 data set.
Thank you so much. And that's it for the talk. Very nice talk. Thanks a lot. And you have a good day, Jan, or good night in your very distant time zone. All right.
Thank you. I will see you all on the YouTube feed and Discord.
Yep.
Cheers.
Let's catch up there. Cheers.
Bye.
working on developing open source virtual reality drivers for VR gloves. And during this presentation, I'd like to give a brief overview of the work we've been doing, as well as some of the challenges we've run into during our journey. To give some background, the project was started back in 2020 by Lucas with the idea of making VR gloves with finger tracking available and perhaps force feedback down the line. I saw this project in its very early stages and wanted to get involved, and so immediately started prototyping my own hardware and electronics and software. I was doing this all simultaneously, so while the hardware was being 3D printed and the parts were being delivered on Amazon, I was prototyping some of the software I needed to go with the gloves. As you can see here, this is a very simple circle I made with a potentiometer hooked up to an Arduino, and set about getting this working in VR games. As you can see here, this is a very early prototype of the finger responding to the potentiometer inputs. But even to get the software this far for this very, very simple demo, there was quite a lot which needed to be done, and some of it was quite challenging. So yeah, to get the software this far, we needed to write the firmware for what would need to be run on the Arduino, and also the PC side of things to read the data from the Arduino and send it through to VR games. The firmware was very simple. It was about 80 lines, and all it would do would read the pin voltages from the potentiometers, scale the readings, format these scaled values to a string, and print them to serial. Now on the PC side of things, it was about 60 lines to get the serial communication side going, and that would set up a serial port and read from it using the Windows API. And while it was maybe slightly challenging, there are plenty of examples and documentation online to get started with it. And then we also needed to pass the string back into a C++ structure to be able to handle it more easily in code. And then to send this data to VR games. To do that, we used OpenVR. And this required us to learn about how to create OpenVR drivers, which turned out to be slightly more confusing than we expected. To give a brief overview, what we needed to create was a way to set up the device properties, which are things like the icons, the serial numbers, what the device actually is, in our case a controller, rather than HMD or some other type, inputs for buttons and joysticks to be supported in these games, and also skeletal input, which was used for hand tracking. What this actually looked like in code was also slightly complex. First, a driver must export a function called HMG driver factory from the DLL, which returns a pointer to a server track device provider. And this device provider lives through the entire session of SteamVR, and from this you can spin up track device server drivers, which are classes which represent an individual device in SteamVR. You can create multiple of these, so we created two, one for the left hand and one for the right hand. And these device drivers in turn call VR properties to set properties about the device, those being setting up the icons, serial numbers, device types, and things like that. And then the VR driver input to create inputs such as the joystick axes, button inputs, and skeletal input. What we also found out was that we needed to create a couple of extra files to get this SteamVR driver set up correctly. The most important files being the driver manifest file, which gives information about your driver, such as the name of it, where it's located, and when to activate. We also need to set up a VR resources file, which contained information about the icons and also localization strings for the driver, and also an input profile, which contained all of the inputs your devices would expose. And then, of course, you needed to create the DLL file, which would contain the actual code for your driver. To get hand tracking working, we used the skeletal input system in SteamVR, which is part of the VR driver input interface. This interface accepts an array of 31 bones, each containing a translation rotation. And the problem here was that our gloves only reported 5 values for finger curl, and our challenge was to create a skeleton from just these 5 values. What we came up with was quite a simple solution. What we did was we captured an open hand pose and a closed hand pose from the index controllers, and then simply interpolated between them. This actually works by taking advantage of how the OpenVR hand skeleton is structured, where each bone is in the space of their parent. And so interpolating between an open hand pose and a closed hand pose has the effect of making the fingers curl. Once that was all working, we had a more functional demo, with all of the fingers working in SteamVR. This is in a game called Half-Life Alyx. And this demo combines the work we did on inputs, such as getting buttons and joysticks working, and the finger tracking we also worked on to provide a more complete experience for the user.
Pull open the drawer to your right and remove the envelope inside. Good. Now reach good. Now tear the envelope open. Inside the envelope is a very, almost absurdly long. Good. Now free me. Or so help me, Oh, who is Friendly Frank kidding? No more guns. I am asking you, as a friend, please, free me. Friendly Frank.
The next thing we really wanted to work on was to have the gloves perform force feedback, which is the act of the gloves restricting finger movement to simulate holding objects in game. And it's best described by people actually trying it.
Whoa! That. Okay, that's cool. Oh, it's thin. Okay. That is next level.
To actually implement force feedback, we did this completely outside of OpenVR, as it provided no interface for games to communicate with drivers. And we implemented this through a name pipe on Windows. The actual interface for this was very simple. It was 5 values ranging from 0 to 1,000, with 0 being no force feedback and 1,000 being full force feedback, which meant the user couldn't curl their hand at all. While we're very happy with what we got at the moment, it was certainly challenging to get to this point. When starting, we found there was very little documentation to help with how exactly to build a fully functional driver. We found a lot of little bits of documentation scattered all over the place, which meant that it was very hard to piece things together. There were samples, but these took a lot of reverse engineering to figure out how they worked, due to being very large and also containing code, which wasn't directly related to what we wanted to do, such as code to support headsets, rather than just controllers. There's also very few examples online for actually how to get skeletal input data into OpenVR. And so this was a big challenge for us to work out how exactly to do this. Another big thing we had to overcome was compatibility for hand tracking in SteamVR games. To give a bit of context, the SteamVR skeletal input system was only introduced in around 2018. And a number of games came out before skeletal input system was released, which meant that developers had implemented their own solutions to provide hand tracking in their games. And these methods were very device specific. And once the skeletal input system had come out, developers never really saw a compelling reason to switch to skeletal input. The notable games are VRChat and Boneworks, which were 2 of the biggest games people wanted to use the gloves for, and so we needed to figure this out. Thankfully, Valve implemented a binding compatibility mode directly into SteamVR, and this worked perfectly for us, and we've been very happy with it. Another issue we found out very quickly was that OpenVR drivers didn't have full access to all of the functionality which did exist in the OpenVR client API. And this was particularly problematic when we tried to get tracking working with the gloves. We needed ways in OpenVR to get other controller poses to be able to track from, as the gloves themselves do not have the ability to track themselves in space. And we could get the poses by calling the get raw track device poses function in the OpenVR driver. But the problem we ran into was working out which controller to track from. The controllers all have specific roles associated with them, and a role being a left or a right-handed controller. But it was not possible to fully get this information through the OpenVR driver API, because some controllers, such as the Vive ones, only worked out what role they would be after the user started SteamVR. The OpenVR client API obviously can, and so we had to spin up a OpenVR client application as another process, as you're not able to use the client API in drivers to fetch roles for each controller. We then needed to work out which controller would be the most suitable to track from, as we couldn't just use the default controllers in SteamVR, as these were our gloves. So we had to iterate through all of the possible devices which we'd be able to track from and figure out which one would be best suited for this. I also wanted to give some information about some of the work we're doing on OpenXR. Over this summer, I was a Google Summer of Code intern working on Monado, where I was working on porting our VR glove driver to Monado's driver interface. and that has now since been upstreamed to Monado. This supports very similar features to what the OpenVR driver does, such as button inputs, joystick inputs, and of course hand tracking. You can see a very early prototype of the gloves working on a fully open source tech stack. Of course, force feedback wasn't originally implemented into OpenXR, and so we wanted to extend the specification for our gloves to be able to be supported in OpenXR applications. And so we've just submitted a OpenXR extension to support force feedback in the OpenXR specification. While it's very simple and a lot looks like our original implementation, it's going to be hopefully reviewed and accepted by the working group soon. That said, while we do have the gloves working with OpenXR applications, OpenXR still doesn't solve all of our problems, specifically because there is no device plugin interface implemented into the spec yet. Currently, devices are pretty fragmented between different runtimes, and this doesn't help by the fact that if you ship your own hardware, specifically an HMD, you're recommended to write your own runtime for it. This doesn't work in the case for our project, firstly because we don't ship an HMD, and so getting support, and so writing a runtime for us isn't really practical, and also the fact that it requires a lot of work, and this is just a hobby project. And so this leads me on to what we're trying to do to try and make OpenVR and OpenXR more simple interfaces to interact with, specifically for people who are not part of large hardware corporations. Might not have the resources to spend a lot of time on it. So for OpenVR, we've created our own samples and documentation. We've heavily based this on the samples and docs already on the OpenVR repository, but we've done quite a lot of work to simplify this to make it more easily readable and more targeted to specific use cases. We've also tried to organize the documentation as best we can to unify it and make it more clear about how to go about implementing stuff into an OpenVR driver. And of course, the code we've written, being fully open source, hopefully provides a good example for how to implement things like skeletal input and button inputs into an OpenVR driver. For OpenXR, we're also looking at joining an advisory board for a device plugin interface, where we hope to make sure that devices like ours are supported fully. Thank you for coming to my talk. Please email me if you have any questions, or get in contact with the working group for OpenXR if you have a use case you feel like needs to be supported in the device plugin interface. Thanks.
So it's not mine. Okay, very sorry about that. Can you shut, please? Okay, sorry about this feedback. It should be fixed now, and it sounds good. Hello, everyone, and welcome to my talk, The State of xrdesktop on SoCs. I'm here in Brussels at the LVRM meetup, and hopefully this live stream works. So today we are going to look at the question, how well does xrdesktop work on various low-cost SoCs? So with the first, to me, I'm Christoph Haag. I'm an associate software engineer at Collabora. And for a little more than 4 years, I have been working on xrdesktop, on Monado, and more stuff. So first, I'm going to talk about what this talk is not about. And that would be x86 mini PCs like Intel NUCs. If you know the Simula 1 headset, it is basically an Intel NUC. The Steam Deck that Luboš presented yesterday or demoed yesterday. And the reason why I'm not going to talk about them is because they have basically the same GPUs as your laptops or as your desktop PCs. So in quotes, they are boring. I'm also not going to talk about Android. Maybe one day xrdesktop will be ported to run on an Android system, but currently we are targeting the desktop Linux stack. So all the Android standalone VR headsets are left out for now. So what is this talk about? First, I will give a very short overview over how we are getting Windows into your XR environment in the first place, because this requires some driver support, and that's where issues can happen. Then I will shortly talk about VR direct mode, about sync, and the last part of the talk will be the main part. How does it actually run on SoCs? So for the first part, the very first thing to say is that xrdesktop requires Vulkan. We render our XR scene in Vulkan, and we submit a Vulkan texture to an OpenXR runtime. So basically, any desktop window that comes into xrdesktop has to interface with a Vulkan driver in some way. If you have watched Luboš's talk yesterday, or if you know about xrdesktop, you know that we have different ways of interacting with xrdesktop. The first one would be interaction into existing window managers. We have integration with Kevin and with GNOME Shell. And if you know these desktop window managers, then you know that they use OpenGL to composite the desktop. And that's where xrdesktop hooks into those window managers. What we get is that every window that these window managers render is an OpenGL textures, and we have to get these into our Vulkan environment in xrdesktop. There's a point about how we do this with our Vulkan library, which is a wrapper around Vulkan. The short version is that you create a VK image, which is a Vulkan texture. You allocate memory on your GPU, and then you get a file descriptor that points to this memory on your GPU. Then you can use this file descriptor to create an OpenGL texture that shares this same memory with a Vulkan texture. This requires some driver support. On the Vulkan side, this requires an external memory extension. And on the OpenGL driver side, this requires a memory object extension. We have a second way of interacting with getting windows into xrdesktop, and that is our new standalone Wayland compositor. It's called WXRD, and it doesn't mirror your windows from your existing desktop. It is a completely new Wayland compositor. If you are a Wayland compositor and you render windows, then you can get these windows in one of three ways. One is simple applications that just write some pixels to an array and tell the compositor to render these. So these are not on your GPU memory, and this is very simple for us. We just have to map Vulkan memory and copy this data there. There's no way around doing a copy like this, and it doesn't require any special driver support. The second way is WLDRM. In my experience, very, very, very few Wayland applications actually make use of this. So right now, this is not supported in our Wayland compositor, but I know only one application that actually results in having these handles. The most interesting one is the last one, and that is a DMA buff, which again is a file descriptor that points to some area in your video RAM on your GPU. That sounds very similar to what we had before, a file descriptor that we export from Vulkan and import into OpenGL. But here we do the other way around. We get a DMA buff from Wayland, from the Wayland client, and we have to import this into Vulkan. Unfortunately, that's not quite as straightforward as the sharing between Vulkan and OpenGL. With those two drivers and frameworks, the importing handles a lot of stuff, low-level stuff for you. If you import a raw DMA buff like you get from Wayland, you will need metadata about tiling modes, compression metadata. You don't need to know them in detail, you just need a Vulkan extension that supports importing these kind of DMA buffs. And that is the image DRM format modifier Vulkan extension. So if that was too fast, here's a summary. Basically, for xrdesktop, there are three main interesting Vulkan drive extensions. Two are Vulkan extensions, one is an OpenGL extension. The first one, external memory, is just about importing memory into Vulkan. That is a very basic extension. If your driver doesn't have this extension, you cannot really do much with our runtime or with xrdesktop. The second one is the other Vulkan extension, DRM format modifier. Basically, our Wayland compositor requires this. And the third one is the OpenGL extension memory object. This one is required by our Kvin and GNOME shell integration. So a short interlude about direct mode. It's very short because xrdesktop is not responsible for doing this. It's actually the OpenXR runtime, in our case Monado, that is responsible for doing this. So if you run Linux on a PC or on a SoC, you usually have some graphical user interface, unless you really want a command line experience. So you are running an X11 server or a Wayland compositor. And if you run an application on one of those, they basically create a window and tell the display server, please render this window somehow on the screen. If you have an OpenXR runtime, it doesn't really it doesn't want to create a window. It wants to control a monitor or a VR headset display directly. But if you run a display server, unfortunately, this display server is owning these resources. So there were extensions created to get one handle to a display directly from this display server. So if you run X11 on your Raspberry Pi and you want to run a VR experience or share your desktop with xrdesktop, then you want a driver that supports one of these extensions, or else you only get your VR view in a window and have to move this to a headset. As far as I have seen, none of the SoC drivers actually support these extensions, but that doesn't bother us much, because if you have a SoC like this, you usually want to have a standalone experience. You don't want to run KDE on it and then mirror what you see on KDE to your VR headset. You just want to connect a VR headset and have only this VR headset running, and only our standalone Wayland compositor that renders directly to this headset. This actually doesn't require any special driver support. Vulkan really supports this out of the box by today. The only requirement is that your VR runtime has DRM master privileges, and it has that if you don't run X11 or Wayland at the same time. There is more info on the website for Monado, which I have linked on this slide. The next topic is sync. Why are we talking about sync? I have talked about the OpenGL extension memory object, and none of these SoCs actually support this extension right now. So there are several native OpenGL drivers for SoCs where you don't get any way to get OpenGL textures into Vulkan. Sync is an OpenGL implementation that runs directly on Vulkan, very vendor neutral. You can run it basically anywhere, and it actually does support this extension. And what this means is that if you can run GNOME Shell or Kvin on Sync, then you can get xrdesktop integration with that, even if your native OpenGL driver doesn't support the OpenGL extension that is required for that. Unfortunately, that is somewhat problematic right now. Sync can actually run many OpenGL applications, but Kvin not really. On my desktop GPU, it errors out. On the Raspberry Pi, it basically looks like this. So theoretically, it probably works, but yeah, you will see something like this on your VR headset. So I'm sure Sync will mature more and fix all these edge cases, but that's how it is right now. Well, let's get to the main part of the talk, which is how does xrdesktop actually run on these devices. on the Raspberry Pi 4. That is very popular, so I put it first. It supports the Vulkan extensions, both of them, and that gets you our standalone Wayland compositor running on the Raspberry Pi 4. It doesn't support, as I said, the OpenGL extension, so the Kvin and GNOME integration. Yeah, you won't get that on the Raspberry Pi. Maybe with Sync once that works, but as you have seen, it doesn't really work right now. Our standalone Wayland compositor actually has two modes of running. One is directly on KMS without X11 running. And the second one is running inside an X11 server. What that gets you is a window from the WXRD, which can take input like keyboard input and mouse input. So it's a nice thing to be able to run on X11. It actually needs a little hack. WL roots requires that this function, drm get render device name from FD, that it returns the name of a render node. On the Raspberry Pi, on X11, this function returns null. So I did a little hack in WL roots. If it's null, then just fill in the name of render node, and it works. So you can run WXRD on X11 on the Raspberry Pi with this hack. If you run it on KMS in headless mode, then you don't need this hack, and it works out of the box. Just wanted to mention that. So how does it look on the Raspberry Pi? Here is a short demo where you can see the Raspberry Pi running. The display output is connected to a monitor instead of the VR headset. One of the reasons is that you can see much better what is going on. The second reason will be on the next slide. And this demo is running on my Valve Index. And what you can see here is WXRD, our standalone Wayland client compositor. And inside that one is running Color Paint, a drawing application. And I used the Valve Index controller to write something inside. It basically emulated a left click. So you can draw inside there like with a mouse. So the second reason why you saw this on a screen instead of the VR headset is that at least my Raspberry Pi 4 hardware is quite flaky. The Index and the Vive have their USB randomly disconnecting. I tried a powered USB hub, but it's even worse. It gets into a reconnect loop. With the HTC Vive, direct mode seems to work, but the display stays dark. With other VR headsets, presenting the swap chain just fails with a Vulkan error. But I swear I have seen it working. With both, with both the HTC Vive and with the Medion Eraser X1000 WMR headset. But then I made the mistake of rebooting, and since then it hasn't worked. So if anyone is a hardware hacker and has the means of supplying arbitrary power to the Raspberry Pi, this might be something to play around with. I used the official Raspberry Pi power supply. I suspect it should be enough, but you never know. So in theory, the Raspberry Pi can be used for xrdesktop. In practice, I'm not sure. Please test it and please figure out why these things happen. There is another one, the NVIDIA Chat Zone. I have the NVIDIA Chat Zone Nano 2 GB here. It's actually almost the same price as the Raspberry Pi 4, but it only has 2 GB of RAM, which is not much, but it's cheap. Including the NVIDIA Chat Zone feels a little bit like cheating here, because you would expect the NVIDIA driver to be the same as on desktops, but it's actually not really the same. So on the NVIDIA driver on the chat zone, you get support for the external memory Vulkan extension and for the memory object OpenGL extension, which gets you support for Kevin and GNOME shell. But right now you don't get the DRM format modifier extension, which means no Wayland compositor. And there's a big but, and that is the official OS that is shipped for the NVIDIA chat zone is called Jetpack, which is based on Ubuntu 18.04. The next version will be 20.04, and there's already a community image, which I tried. But the NVIDIA driver that you get with the most recent community image right now is still, it's called NVIDIA 3261. No idea how that relates to the desktop version, which is currently 5.15. The desktop driver supports image DRM format modifier. So on desktop GPUs, you should be able to run WXRD right now. I should really try this out. But on the NVIDIA chat zone, you can only run Kevin and GNOME shell right now when it comes to xrdesktop. The reason why I haven't tried this out and have a demo here is because our latest Vulkan branch is currently broken. Vulkan is our Vulkan wrapper library. I know why it's broken. I just need some time to fix it. What I can say is that the xrdesktop, we have our own Vulkan example there, which doesn't require any special driver support. It's just a plain Vulkan example, and I know it has worked in the past. So if we fix our current issue, then I'm sure Kevin and GNOME shell will work too. For our Wayland compositor, you will have to wait, but I'm sure that NVIDIA will bring their JetSon driver up to speed with the desktop driver at some point in the future. There are more SoCs. I have a RockPi 4B at home. It uses Panfrost and PenVK, which is yet another Vulkan driver. Unfortunately, at this very moment, it doesn't support any of the extensions that we require. But these are very temporary limitations. With PenVK especially, we can be very sure that we will see more support in the future. So I'm looking very forward for PenVK to support these extensions. There is a very expensive class of SoCs, which has the Adreno 600 series GPU. There is a Mesa driver for it, which is called Turnip, and it actually has support for external memory and image DRM format modifier. There is a reason why I haven't tested this SoC yet, and it is because there are basically two bots from Qualcomm that have this GPU, and they are $450 and $500. And I haven't spent that money yet on an SoC. If anyone has one of these boards, or if anyone knows of a cheaper one, I'm interested. So basically, you should be able to run our standalone Wayland compositor on this SoC. And lastly, for the last driver in Mesa, there is a new Vulkan driver for PowerVR. As of now, it supports external memory, but not image DRM format modifier. So you cannot run xrdesktop on it yet, but it's an interesting upcoming Vulkan driver. So I'm also looking forward to PowerVR. So basically, that's all I have for today. Thank you. And there's an obligatory slide about VR hiring at Collabora. So I'm around for questions if anyone has any questions.
Thank you very much. I'm turning myself to the audience here in Minneapolis. there's any question on my side. Maybe you guys have question on yours. We got one question here from someone in the audience.
Hi, Nova here. If you were to drop DMA buff support in WXRD, would it be supported on more of the devices?
Probably, but there aren't that many interesting applications that don't require it. Anything that renders Vulkan or OpenGL will be a DMA buff. I think Western Terminal would be one example that is just pixels in an array, but really anything with OpenGL or Vulkan will be a DMA buff.
And we have a question here from the remote viewers. Which is that one app you were mentioning that's using WNDRM?
Let's see if I remember. I think it's Western Simple EGL, but I'm not sure. It was one of the examples.
No worries. I recommend you check this out async and probably post that on the channel. There seems to be no one else on our side with questions for now, so thank you very much, Christoph. It was a nice talk, and I believe we are going to welcome Fabien in LVR in Brussels right after. Thank you very much. Take care.
Okay, bye and enjoy the conference.
So welcome, Fabien. You're good to go. So calling in from Brussels, welcome. I give you the mic now. Thanks.
Thank you. So I'll put the timer on. Well, thanks everyone for being here and having me, and for some of you that I had the chance to meet and chat with in Amsterdam about 3 years ago. So I'll do a little update on what's changed in WebXR. If you already know WebXR and work on it, well, hopefully you might get an idea or two, but overall, I think you get it. If you don't know what WebXR is, I'll do a little introduction and show what changed. So I'll start with an introduction of who I am. So that's me, more or less, in 3D, and with a little art for web monetization. And that's, let's say, a dump of my mind, where I put notes on any topics, books I read, cooking lessons, whatever, anything and everything is, not everything actually. A lot of things are not there, hopefully, and you don't want to know about it, but I do like to put my thoughts on the web. And then this is what I do. I do prototyping, mostly on the web and mostly related to VR and AR. Yeah, things that don't have to who never actually become products, just testing if it makes sense or not. That's also a good conclusion of prototyping. If it doesn't make sense anymore, you better move on for something better, and you want to do it quick and on the cheap. And due to this, I accumulated quite a few notes, like thousands of pages, and I felt basically that keeping them stuck on the screen on those 3 millimeters of plastic were not that nice. So I do prototyping. I don't know if you saw the webcam, but I was at the European Parliament just 3 hours ago, and working there. Nothing I say today relates in any way to the Parliament. I work there, I do this kind of stuff, but I don't represent any institution, nobody but myself. But yes, my motivation is this wiki has become unmanageable. So I thought, well, I put a VR headset on. I tried the Tuscany demo, and I was like, well, this is amazing. And then the second thought was like, wow, I could have my notes everywhere, all around me, and then organize them. So I've done dozens of prototypes on that. But I'm not a game developer, and I'm not a low-level developer. So I was trying to pay as much attention as I could before, but I admit it went a little bit over my head, not due to the presentation, but it's not the environment I'm used to. So even something like this, like a Unity GUI to manage, is something I'm really not used to. What I'm used to is like a div or an image. So those little HTML tag that you could use to build your web page. So it started like this with A-Frame. So A-Frame is a framework to make content literally as you can see there on the screen. So you can have a page that will be in 3D and then viewable in your headset, VR or AR headset, and even, let's say, weirder stuff like the Looking Glass, for example, where you have some like stack of display, where you have some kind of volumetric display without needing a headset. But yeah, in those primitives, like a box, a sphere, a cylinder, a plane, a sky, and plenty others. So that's to me is the appeal of one of the appeal of WebXR is that you can stay at a very high level. It doesn't mean you have to stay stuck there, but to get your content out, if you're not used to low-level graphics, that's definitely, I think, an amazing entry point. So that's the falling castle of cards. So I'll do a little live demo of what it actually looks like, and I'll have the headset on. So hopefully now you can see me casting from the headset. And I'll show you the one thing that hopefully it should be pretty obvious that changed since 2019. So again, just to put a bit of WebXR in context, I'm in my headset. that I see pass through, and I see my browser. On my browser, I can just see a 2D page or a 3D page, as you can see there. And in the bottom right, I can enter it and then be in fully immersive mode. So that's the one thing. What you can see now, my hands, I would say, is one of the biggest things that changed since Amsterdam, since FOSSXR 2019, in terms of WebXR, is to be able to not just see your hands, but then be able to manipulate objects. So the little demo, eventually I'll explain after why I care for it. But yeah, those you can imagine being pages of my wiki, or here some of the slides for that presentation and how I can organize them in space. I just insist a bit on this because this is why I spent that one thing, those crazy or those lines of text is why like the last 6 years of my life I've been dedicated to. So it's a little bit humbling, let's say, for me to summarize it. It's just one way, but that's the truth. So I can tinker with it and show you the features, but the one thing related to the specification are those hands that I can then use for all kind of interactions. So that's one of the beauty, let's say, of the change since 2019. And I think that's really something that a lot of people miss. They see a VR headset, they say, oh, I'm somewhere else and it's amazing and I can see stuff. But to be able to naturally or relatively naturally interact with content is really quite something else. Now I'll go back actually out of the VR experience. I'm still back to my OS. And the other thing that also has changed that is pretty powerful is especially for playing with text, which I think is still a super interesting primitive. So I can just remove those, but that's actually, you can see also that some of the text is behind, yet still in terms of depth, you would expect it to be forward, is that one visual that you can see here. So that's also the layer component that's part of the specification. So now if you compare the image in the back and the image in the front, it's way, way clearer because you're going to use layer directly from the compositor without rendering twice and like a bunch of other benefits. But in terms of images, it sounds a bit boring, let's say, using 2D content in 3D, but text is 2D, images, video, all that is 2D. So to facilitate, let's say, the transition from a 2D world that includes a lot of the content we have to a full-on 3D immersive and, again, interactive one, that's a pretty powerful tool. And I think that's it for the live demo. So those two things, the hands and layers are some, in my opinion, of the most powerful new features we have access from the WebXR API since 2019. Another things, so that's another demo with the same principle, and this one is again the same code, but from the AR perspective. So I can enter VR AR. The browser is going to detect that I'm in an AR headset, and then the background then disappears or fades away. I just have again the exact same code actually, but running in VR from AR. So from a development standpoint, being able to not just deliver content from or through a URL, but also being able to use it on not completely different device. You still have a spatial headset, but to go from VR to AR, thanks to the same code, is a pretty powerful value proposition. What has also changed, I want to highlight both the positive and negative things. I have as a little memorabilia a Firefox Reality sticker because that was a browser at some point. Unfortunately, Mozilla had some strategic decision of axing some of the team working in VR and AR, which led basically to the end of the Firefox Reality browser without any team to support it. Thankfully, Igalia, through different hardware partner, took up on the task and then started to develop what's now the Volvic browser. Again, I have to be direct about this. Some of the features, like the hand tracking that I showed just earlier, is not yet present in Volvic. It might become so because, for example, Lynx, so for a bit more context and why it's interesting is Lynx is a French startup, and that is not this one, because this one, the Meta headset is from a quite specific company with a quite specific business model. So Lynx is selling hardware, selling headsets, so basically it's not going to have the same behavior in terms of data gathering and more than a company that just quote-unquote sells hardware. As far as I know, I haven't put my hands on the Lynx yet. I'm waiting for one. I ordered mine, but it should be, so it is a personal position, but I don't like Android. I would rather have a Linux proper or Linux only on it. So it runs Android, but it's rootable. So yeah, you can understand all the consequences of it. But the point is, yes, now you have another some detail on the repository. It's also, I've been personally or professionally contacted by hardware vendors on how WebXR could be supported. So I think it's quite powerful and interesting when we see that hardware vendors do care and want to find an alternative to have a browser running because they understand the value proposition of delivering content through the web. One thing that is quite interesting is all those kind of experience and content can be done just like I've shown on the headset, but you don't have to be alone doing it, basically. It's especially interesting when you do it together, and that's something that comes nearly for free on the web. The web is about connection, and it's about social connection and working collaboratively. And one of the examples that builds on top of A-frame is networked A-frame. So you have different backend for it, but you can use networking in a very direct manner. So you'll have your A-frame library. Those are examples. There are other library or frameworks to do WebXR, like React Fiber or Babylon.js. I'm partial, let's say, to A-frame because I find it quite direct and again a great entry point, but that's one implementation of a framework. So you can also, of course, make your own framework. This is quite direct and popular, and then you can use then WebRTC to do screen sharing, audio sharing, to of course network all the different assets. So the text you saw before in the room could be networked so that anybody joining would see it move. So I think that's also one of the beauty of WebXR. This is not specifically part of the specification, yet adds some a lot of value to experiences. One thing that's interesting on top of both WebXR and then a framework like A-frame and then networking is federation. And I say it because I put it in the title, but the metaverse. I do think it's actually an interesting concept. It's kind of a shame that a specific company tried to appropriate the term, but we can understand a bit still what could be interesting behind it. And I think what's the most interesting besides just direct collaboration, so again, being able to interact with content together, is federation, so that you can make your own for example, avatar or identity and everything attached, or anything interesting for you attached to your identity, but not stuck within a walled garden, basically. Whatever content you build in a walled garden is going to be stay there. And all the time you invest, including in relationship, when you make a friend, is not going to transport to another space. And I think that's a horrible value proposition because we're basically literally isolating each other. So Immerse is proposing to add federation on top of your network experience. what's interesting then is that you'll be able to bring the content and I have some example there. So it's a 47-minute video. I'm obviously not going to play that now. I'll let you watch it eventually. But it's a step-by-step tutorial on setting up your metaverse. Again, I say the term, but I think it's interesting because it's literally the metaverse where you self-host, you control the entire stack, and yet you're not isolated. The same way that this is my personal PureTube server, and it's federated, and you can connect to it. You can either replicate content or make comments if you have your own PureTube server, or if you join one that already exists. So I think the federation aspect, in terms of reconsidering power imbalances from large companies that basically build monopolies, is something that, if we're serious about free and open source software, we need to take into account. It's not just building the software, but enabling the entire stack for people to literally own. So yes, being able to build this kind of experience. And the video is 47 minutes, which is a bit long for now, but that gets you your own instance, let's say, of a metaverse that you can federate with others. So I think as a slim stack for this kind of value proposition, when you actually have a virtual world on a server that you own, can be at home or wherever, not on AWS. So I just put DigitalOcean again, not to have one dominant player, but I think again it's a powerful value proposition. Specifically, I'll go back to it, but I want to highlight a bit this slide on the connectivity in the metaverse. The idea is not like, as you see on the right, you already have 3D or virtual world that are interesting, let's say, but they are stuck in their own space and with their own set of people and rules. And I just think that's a huge loss rather of creativity and potential to connect. Whereas on the left, so you probably familiar with Mastodon or PeerTube, but basically the Fediverse. And the Fediverse doesn't have to be stuck in text or in 2D, but actually works today with Mozilla Hubs. You can have the Immerse stack on top of Mozilla Hubs, or Network Frame at a lower level, or another implementation, even proprietary ones like Frame, which is another WebXR social network, let's say, or social place. But you can have then really different implementation, able to exchange users and whatever is precious to them. So another one thing that is a little bit tricky again on the bad side in terms of WebXR is, so I'm using, let's see, I'm using Linux on pretty much everything I own, from my IoT hub to my laptop, my desktop, the PinePhone and PinePhone Pro, my e-ink device. But WebXR doesn't actually work on Linux anymore. There was some testing built from Firefox in 2018, if I remember correctly, but nothing works now. So if I want to use WebXR on my actual desktop, for example, to run an index, then I have to reboot on Windows. And I think that's, yeah, I'll just leave it at that. That's a big shame. So yeah, there are some progress in terms of WebXR and support, and then some, let's say, hacks on how to try to make it work, but with partial success. So I'll invite as a call to action also people to give a try to this kind of project in order to, or solution basically to see gaps in the stack. A last comment on my own thing. Yeah, I think the why do I show you my own stuff? I think they're way more exciting experience than mine. There are nicer ones, they are more performant, but mine is mine, so it's precious to me. And I think that's one of the call to action again in terms of WebXR and even XR in general is you need to build, you need to make not just tool but content, because otherwise somebody else is going to shape the medium. It's not necessarily going to be either interesting in terms of content that's precious to you, or in terms of power relationships and the more economical aspect. So my content might not appeal to you, but to me that's the whole point of doing VR, AR, an emerging medium, and doing it on an open stack. I can do whatever I want, even if nobody cares for it. And finally, the federation aspect. I've done my own experience. People can play with it, modify it, but if you want to have the federated aspect to it, so that you can connect and bring yourself in a way, I invite you to do so. And I think that was the last slide, but just you can see in the bottom left corner the little Immerse icon, so that I can either connect from my Immerse server or yours, or yours, entirely up to you. So my final call to action there in terms of WebXR and FOSSXR in general is build content and connect that content. And thank you all for all this work, because I think you're at the high level, let's say, with WebXR, but none of this would be able to work without the work you're doing now. So thank you so much.
Thanks, Fabien. You want to take some questions?
If there is time, sure.
All right. We have some time. We have some few minutes. So there's a question from one of our remote viewers here. So it's simple. Where is the Gecko repository?
I'll put the link in the chat. I will also on the slide. I do have slides, as you've seen, and my slide is a series of links. But if you go on the timeline, the timetable rather, you'll see all those links there, and including the Linux patch attempt for WebXR.
All right, we'll do that. And there's a lot of nice comments for you online here, so you'll be sure to give it a look. Is there any question from the audience here in Minneapolis? So we're a bit out of time, but I think that would be it. So thank you very much, Fabien, for your nice talk, and we'll obviously catch up later. All right, so take care.
Thanks a lot. Take care.
Bye. Hi everyone, welcome back to this nice panel discussion. So we're having Olivier and Fabien in Brussels right now, live at the LVRM conference, and we also have Nova here in Minneapolis. So we're gonna be hearing Olivier with some context first, and then he's gonna open up discussion with people here on our side. And so it's over to you, Olivier. Thanks.
Great, thank you for having us and sharing the space between US and Brussels. So I'm Olivier Meunier, more known by the nickname of Olme. I'm actually an artist. I develop some application too, and I'm working with the VR and augmented reality and whole, which is around that for 20 years now, doing projections and live system for art. And so I'm actually also working with some medical companies, and where I give my services as a VR developer and artist. And I've been actually both in this in this endeavor and also in my artist and education roles. I've been confronted to the recent changes into legislation and obvious development of what we are starting to call the metaverse. So this is an introduction about what my experience is and what I can also give as small advices or questions we should ask ourselves. So the evolution of these last years has obviously changes what we were talking about in terms of VR, because now we have internet, we have integrated the internet with it. But what has come with the internet as it was the sharing of data that is really new to our sectors, because this is something that we were not really thinking about in the past. We were needing data, we were gathering data to make the system works, but now we have also something that we need to think about is that we share data, and we share personal data. What is personal data is data that is reliable to you, that is linked to you in any way. It can be street address, it can be phone number, IP address, identifier across a database. It can be a pixel, a special pixel in a web page. But it can be also sensors data, hashes of those sensors data. So what has happened also in Europe, which is our context, in the recent year, is the GDPR, so the General Data Protection Rules, which is a really big legislation, quite complex to understand, and which has actually a really broad range of action. Here are some of the small resume that you could actually gather from reading the documentation or the text, the original text. I will go really shorter than this and just talk about small, the broad principles. So the questions are really about the data that you are gathering, processing, and storing, and the way you have to care about it in regard to the people that are concerned. So these are small sentence that resume it a bit, the whole thing. Lawfulness, consent, childs. It's one kind of questions: the purpose, the scale, what is the scale of what you are gathering as data. Also, the problem of accuracy and storage. We'll talk about it. Security is very important also to all this, and responsibility. Who is responsible? So the question that you have to ask yourself from now, with this kind of legislation in effect, is really about the way you are proposing your services, and that the fact that all your clients or your final users will have to be informed of what you have to do, what you will do with the data, what kind of data they are giving to you, and you have also the necessity to be able to open yourself to rectifications. Also, no child can be taken as a subject without the consent of the parents, which is something also quite complex. And also the thing that you have to think about is that sometimes companies are like to conturn or ease this kind of situation by establishing contracts between the company and the users. These contracts can be a double blade because, of course, it can somehow shield you from some consequences, but it can also be enacted and used by the users to actually make you problems. So other questions is really the purpose, the scale of the data gathering. Why are you gathering all this data? What are you going to keep or get? How often? The details. What also is the possibility to mix those data and to actually cross-reference and actually identify someone without even having a name or something. And the main question you have probably to think about is, why is it so useful that you have to take it? Other responsibility are also, as I said before, accuracy and storage. Is it accurate what you are gathering as data? Are the info about the users correct? Is it also modifiable? Because the citizen has the right to actually modify and change the data there that are of their concerns. So where do you store them, and is it easy to change? Who has access to those data too? This question is both. Do you have access? Does someone else has access? Does someone from your company has access? Or can the public has access or not? So it goes to the security. So who has access? How will you give the access to those data? Do you use end-to-end encryption? What about moderation? That's another question, but it's part also of the fact that we are building social networks. So now the question of moderation, so also the access to the data for moderators is something that is important to think about. And there is also some big problem or question that has arisen lately, is the fall of the safe harbor. So the Court of Justice of the Europe has made a ruling in 2020 that has basically rendered all exchange of data from EU citizens to American companies unlawful, because actually it's a complex fall of events, but there is the FISA laws in US that actually permit the government to go into any company data and get what they want with a secret order. And so no American company broadly can really ensure that the data of EU citizens can be protected against that. It's a big problem because it has a lot of consequences in all the way, and we have to think about twice now what we do with the data and who have we contract with when we work from the EU. So the last question at the end of all this is who is responsible for the data, and actually at the end is the person that put the user in the situation of giving the data. It's the last one in the chain. It's the institution that record the data of his of her users that is responsible for what it is done with the data with the all the contractors that you could have in the chain. So this is a lot of a big burden onto the one in the chain that has to really look up what is done with the user data. So a bit of a conclusion, and what we could think of and look at is basically to avoid risking, because it's a question of risk, of legal risk too. So what we can do is to use the less data possible. It's always good for the performances of the systems, but it's also now really good for the lawfulness and the privacy of users. One of the things that also need to be checked into the development of web applications is what are the parts in the chains. Like, are you sending your user to a company that is from other country without him or her knowing that you are sending it out? Do you still host your data on other servers, other person's server, or are you all self-hosting? So question of end-to-end, what is done, end-to-end encryption, what is done with the metadata? The question of decentralization, how you can have a product that is actually working on the whole planet, but with intermediaries and local people using it. And also even the possibility to have the same system across the world, but with communities that are not linked together, because actually they work, they function differently. They don't have necessity to be linked. So the idea of a limited federation mode, like it exists in Mastodon, is something that we could also think about. One important question, or one important attitude would be actually to get counsel. This is a really complex questions. I'm an artist and a coder. I have some notions of laws, but I'm not able to be sure that what I'm telling you today is absolutely accurate, because I'm not a lawyer. I'm not a specialist in this. It is what only that I've undercover and met with my practice, is that you really need to get a DPO if you have a big institution. You really need to get an audit on your data flow to be sure that not one of your users can sue you. So if all of this is a problem, one of the things really which help is the free software movement. tools, because when we are using all these really complex chain of tools, what we can do with FLOSS, with free, libre, and open source software and hardware possibly, is that we can dig into each of the tools and see what are they doing, what are they sharing as data, and we can make them ourselves. A small list of links from what I've, where you can actually get precise references. We have also here, for example, Not Your Business, which is an organization which is actually fighting for the user to get the right they deserve. And there is also here a link for the general guidance of Europe regarding the best practice. It is still a very heavy document to see and to crawl into. So really, if you have any people around that can help you, just get some some advice from good reference people. Fabien?
Thank you.
Oops,
Thanks
sorry.
a lot, Olivier. I'm wondering if Fabien has.
So I'm also not a lawyer. I still have my EP, my Parliament badge. First of all, our trouble, GDPR, and all the pop-in we need to click all day long. But I'm not representing the Parliament. And like I said, I just want to build stuff, and I want all of us to build stuff. But I think, as I was hinting at about the different economical players and market dominance, we can't be too naive about the stacks we play with. There are political consequences to the stacks we build, the stacks we use, both software and hardware. We have basically to be mindful. I've been annoyed by Olivier a few times when he was giving me some advice, and then of course stepping back, I was like, yes, of course I need to not just randomly add some dependency hosted wherever. But I think it's challenging for all of us. Now it's a new way, basically I think I would say sparked by surveillance capitalism, the way where we extract data to change or resell the behavior of people through basically big advertising. I don't really care for it when it's trying to sell me Pepsi instead of Coca-Cola, but when it's trying to change my political behavior as a citizen, I think it's ridiculously destructive. And yeah, I don't want a VR headset with a higher resolution and better tracking if I lose democracy in the meantime. So this is a little bit maybe pushing it, a little bit alarmist, but I think it goes way deeper than all the tech we play with. It's way more precious. So I think it's really tireful for all of us. Most of us just want to build stuff, but we have to do it right. So I think that's basically the challenge. Again, in terms of the Parliament, I'm not a politician, I'm not a regulator, but if you send me an email, a personal private email, I can try to find either whatever is, I don't know, the piece of the law, the person to put you in touch with. That's also why I'm here at FOSSXR. That's why I care. I don't want to be locked in my silly, fancy, high-tech looking headset if it's in condition that basically take away my privacy and that of everybody around me. So yeah, if I can help somehow, let me know.
I invite you guys to stop slide sharing so we can have a common conversation with the webcam for you guys.
I think maybe switching to Nova on the ground.
Yep, it's good enough.
So we would be happy to actually hear your thoughts about these questions and also the solution that we can find, technical solutions, but also organizational.
It's a word.
Yeah, way to organize and to build systems that are respectful and also manageable for us.
Hi, can you hear me?
Maybe you check on metrics.
Can you all hear me? Is it not working?
Olivier and Fabien, can you hear Nova?
Hello?
I'm
Oh, okay.
not sure.
Okay. If you
Where
can
are
hear
we?
Okay. Yeah. So, hi, I'm Nova. I'm working on Stardust XR, which is a XR system UI, and I have to deal with a lot of data, a lot of direct raw sensor data going through Stardust and distributing to different applications. So, this is sort of in my wheelhouse a bit. And personally, first of all, definitely agree with all of the slides that I've seen so far. It's great, but at the same time, I think that anything we try can be easily undermined because ultimately the entire permissions model for operating systems and the web is entirely based on, do I give this thing access, right? With
Tout à l'heure en route.
with that whole model, effectively, what you're doing is it's
Bon.
oh, can they actually hear me? Oh,
Hey guys, can you hear us now?
Yeah, okay.
okay. Can you hear me now as well?
Yeah.
Nice. So we'll
All realized it?
Nova's gonna restart again. All right.
All right. That's no problem. Yeah, hi. So I'm Nova. I do Stardust XR, which is an XR system UI for Linux. And I have to deal with a lot of raw data, raw headset data, raw hand data, controllers, pointers, all of that stuff. And then I have to shuffle it and distribute it to various applications and also other Stardust clients. So I deal with this kind of stuff. And my project is in early stages. However, I've been thinking about how best to preserve privacy and security. And ultimately, I think that a lot of things that we are doing right now are kind of, I don't want to say doomed to fail, but it's incredibly difficult based on the permissions model for the web and applications that we have now to be able to ensure that. See, normally what happens now is you have a binary choice. The user has a binary choice. Do I allow this application to have this piece of data? And maybe if you're lucky, you get to say while it's running, right? And this effectively locks users into a choice because the programs can basically say, we need this in order to function. And if the user does not trust them, then they either have to sacrifice functionality or they have to choose something that might violate their privacy. So I believe that we need to change the permissions model to more, instead of, do I give you this piece of data, to what data do I give you? This also means that it would radically have to change how companies treat their users, because the users can send data that is a complete lie, right? So, in other words, if the companies want accurate data from the users, then trust has to go both ways. For example, in Stardust, the way that it works is that Stardust clients actually control the 3D interfaces used for a user to interact with any content. So they can change up that input however they want before it actually gets to, for now, 2D applications and eventually XR applications. And this means that those XR applications, they just have to accept the input they've been given. And again, a company will have to trust that the user is giving them accurate data just as much as the user has to trust the company that they will not be misusing that data. So I think that is a good place to start. Oh, and all of the defaults for core essential behavior, like head and controller positions, which if you all didn't know, in around, I believe, 5 minutes, that amount might have gone down. You can uniquely identify someone through head and controller pose data. So it's really important. For that, differential privacy on the actual operating system level should be the default. And that's much easier said than done. I've been looking into how to do that. But yeah, so again, one, make sure that on the operating system level, you have you have your default set to all essential data is differentially private, and two is to change the permissions model to where the user has tools, right, that are built in so that they can lie, and in that way the companies will have to trust them.
What do you guys think about that? Any comments?
Yeah, actually, there is already one company that does this kind of thing. Is the E Foundation for the phone, the E Foundation OS, Murena is called now. They have some parameters that you can set the phone on a really super secure like configuration, where there is a VPN installed, and there is also it's lying in its localization. So any application that is running on it, trying to localize the person, will get some funny GPS info. So that's an interesting way to do it. Yeah, indeed, to give the choice to lie.
Another thing I want to add is that the way that permissions are displayed to the user as to this device will be able to read your location, it does not, like, look, when I see one of those pop-ups personally, right, and I've done UI and UX design and development for XR for 2 years professionally, my eyes just glaze over it, because it doesn't tell me why that's important, and because I want to use that application, it would take too much mental energy to do it. And I don't think we should blame individuals for this, because that's just generally how human brains operate, though. Highly abstract things that are really far off are just difficult for people to understand. And so I wouldn't say that having sort of what does this mean for the user is a good idea, because that is that's a whole can of worms, and it's something that people could easily abuse or mislead or so on. But if we can remove those dialogues entirely through that alternate permissions model, I think we might be able to make it easier for users, right? Because if we create unique XR UIs and we have organizations dedicated to trying to fix this issue on a more fundamental architectural level, that's where the organizational piece comes into play, just figuring out exactly what to do, then we can remove all of the willpower that it requires in order to keep up with privacy, because it requires so much, you know? Because ultimately, companies will find whatever legislation, and they will, in this current situation, they will try and do the minimum in general, right? So I think that the only real way to ensure that they cannot get away with doing the minimum is to make it to where they require the users to trust them before they get the data, instead of the opposite way around.
Yeah, that's the spirit of the GDPR. Actually, it's that normally you have to have the steps to ensure that the user can trust the company. But
Go ahead.
It's my initial reaction also when I hear about permission model and think of permission fatigue is like, oh, maybe we could have like a liquid permission so that if I trust you, then I'm blah blah blah. So a technical solution, that's like my instant reaction, and yeah, could be cool to do, could be interesting. Like I have my network of trusted peers, and they've basically voted for that either headset or experience and whatnot. So interesting, but I think overall, and to go back to, let's say, the spirit of GDPR and company doing the minimum they can, it's more of, in my opinion, from a non-technical standpoint, for that specifically, it's showing people that there are actually alternatives. Like I think a lot of, not necessarily people at FOSSXR, but a lot of people that are using Gmail or YouTube or WhatsApp or whatever, they just don't know there are actual alternatives. Like they are just stuck in it with or due to the conviction, some like learned helplessness, that they're stuck there. So there is nothing else. And I think from, again, I'm not saying the technical solutions are not interesting, but being able to be aware that there is actually a way out, that there are actual alternatives, I think is a very powerful way to start a discussion. Then yes, there are important technical implementation that we need to choose in, and the impact that organizational, it's a hard word, I get it, level, but yeah, being able that people around us, not us, but our own closed network, understand that yes, the cool tech we play with have consequences, and this, if we need to drop a headset, we should.
I agree. We have to, convince the average user, if we can say it like that, but also, convince companies too. Even, at Collabora, we obviously we are all for it, organizing this conference, but also, we don't have a security department. We are not, we haven't been reflecting on this in a formal manner so far, and that's something probably we can probably get ourselves interested in the next few years. But I see that it's not only about getting the people in, but also more structural. It's going to be tough. It's a challenge, getting more people in, including companies in that movement. But yeah, I totally agree with you guys.
I would like to add though that how to put this. So obviously the whole lie to companies thing is not a one-stop fix-all solution, but I think it undoes one of the major pieces of what is keeping this entire system of companies being able to harvest so much data together, and that is that the user only basically has two choices: use the service or don't use the service, right? And have their data collected. And because those cookie pop-ups that you see all over the web now because of GDPR and other similar legislation, again, it's they either trick you into doing it, right? Or they say, sorry, you can't use the service. And it's like, that's kind of not acceptable, because I hate to say it, but people are just going to use the service anyway, because it's just too much fatigue, from a UX standpoint. And so, but obviously alongside that part, finding alternatives and I'd say promoting those alternatives on more open platforms, huge thing. It is a difficult balancing act. See, for organizations like GNOME Foundation, right? They obviously generally promote applications that fit their design style, that are made for their desktop and so on. So having sort of independent organizations come up with lists of applications and alternative app stores and so on, hell, maybe even just alternative algorithms, you could say, for app stores, right? Would be a lot better than having companies that actually, maintain their software centers or are working on platforms doing it themselves. It would lighten the burden on them, and it would also make it easier for people to discover things that have sort of been like encouraged in a vacuum, as opposed to where organizational as platform-based organizational bias could come into there. And separate organizations also mean that some apps that weren't seen because people are so focused on their own stuff are now seen. So I think that separate organizations for exploring those apps and the actual platforms themselves are a good idea.
A quick thing, I don't know how much longer we have. Well, I'll just go then and you stop it.
We still have a few minutes, guys, for some few
So
comments.
just one example that I find pretty powerful and very positive is, I'm not sure how many people are aware of it, but in France there is the Dinum and the Blue Hat setup. So it's part of public institution from the actual French government, and they not just promote free and open source software, but they list like, okay, this institution, this part of the government, this university, blah, 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 use, I don't know, PureTube and LibreOffice and whatever. So they have a catalog of who uses what, and also who recommends, let's say, a company that's going to be able to maintain that software. So I'm just saying this as a, let's say, counterbalance to some of the maybe dread some of us feel that we just give a couple of names of huge corporations that seem to dominate the landscape. But there are some actual counterweight that do promote solutions that are obviously GDPR compliant, that are free and open source. So there are a way to, let's say, distribute the load in terms of both promoting, using, developing, that is actually taking shape and have an economical impact too. So I think this kind of sort of initiatives at a large scale are yeah, just find that amazing, basically.
One more quick thing. So a lot of smaller creators are very concerned about GDPR and such, though, because, like you said, it is a large legal document, though, and it's very difficult to know every single piece of your stack and if you're complying with it or so on. So I'm sure they exist, but I have not heard of them, and I think they could be at least more widely known. Organizations that can help those smaller companies and such actually make sure to comply. Nonprofit organizations that are dedicated to that, because a lot of creators I've talked to are very concerned that, like, I want to create this really, really cool idea and I really do care about privacy, but I just, they're kind of a bit scared that they'll get tripped up on that stuff. So having organizations that could help would be huge. If they don't exist, I'm sure they do.
Yeah, there are some organizations that exist, like NOYB is Not Your Business. It's one of those organizations that is crawling through the legislation and giving advice, and also going to process against some organizations. But these are more for the citizen and the consumer to make their right respected. And on the other side, there are organizations and companies that give counsel to companies, to organizations, and to institutions about the compliance. But these are more like services. It's not free. It's sometimes quite expensive, as lawyers tend to be. I think it would be interesting to see if we could see that we have some more open or easiest to approach way to be sure that you are compliant in the first steps actually of a project, to have some guidelines easy to understand. That would be good indeed.
And also, I'm pretty sure that just, even if it's not legal advice, having nonprofit organizations dedicated to just helping you look over your stack or such, I think that would just really help in the first place, because you know, it's always good to have a first pass. And given how big and complex projects can be, it's insanely overwhelming to check all of your dependencies yourself, even with the tools available. So having organizations that could just help with that stuff would be, I think, really huge. And it could make it to where the people who do care about privacy are able to get their stuff in front of everybody way quicker and way easier. And they have, you know, more time to focus on making their stuff better so that it can eventually become good enough to where people will use it, you know?
So just like super short, it's the actual implementation of the law versus the spirit of the law. So as a creator, apply the spirit of the law, do your best. And the heuristic for this is know what information you take from the user and then get the consent for this. Again, this is not legal advice, not regulatory advice, but that's like the foundation of it. And of course, if a creator actually cares about the value behind it, yeah, that's definitely a good first step. If it's something different, let's say, because they're worried of the potential legal consequence, if somehow something were to blow up, then yeah, the actual legal advice. But otherwise, yeah, spirit of the law and getting consent from the actual information you take.
Thank you, guys. I think this is unfortunately all the time that we had today for this discussion. Pretty interesting, and thank you so much for sparking those discussions and keeping them. You know, we see that you're keeping those discussions alive on the web. So let's catch up on this. So that's it for the collaboration between FOSSXR and VRM. So I wish you guys a really nice evening in your time zone on your side of the ocean. Thank you again and take care, okay?
Thank you.
I'll see you.
Bye-bye.
Bye.
Thank you.
Thank you so much. See you all later.
Hey everyone, welcome to this afternoon session. We have the pleasure of welcoming Nick here present. Hi Nick. And so thank you very much for being here. So over to you now, thanks.
All right, thank you so much for having me. I'm really excited to be here. This is a pretty cool place. So I'm Nick Klingensmith. I work at Microsoft on the mixed reality middleware team. And I'm here to talk to you a little bit about StereoKit. StereoKit is an open source mixed reality engine. It's code first, it's lightweight, it's good as a dependency or for building applications, but we'll get into the details here. I do want to just talk a little bit about myself here first, because I'm kind of like that. So I actually started my career teaching game development, and then later got into like professional game development, indie, mobile, and VR. So I've always been kind of on the performance side of game development, where I focus on like, how does it run on a phone? How does it run on a VR headset? That sort of thing. So, which is actually a really great place to be coming from. Plus, as a teacher, you know, like I kind of have this mentality of like, what does it take to learn something? What does it take to teach something? So those are some nice things that I kind of keep in the back of my mind for just about everything that I do. I also kind of like between game development stuff here and there, I also had a small business where I would build tools and sell them on the Unity Asset Store. So like I've spent a lot of time working with customers to create tools for accelerating game development. A lot of it's kind of like graphics focused and stuff like that. When I joined Microsoft, I actually started working on the mixed reality lighting tools, which is kind of one of my big mixed reality projects, the first one that I did there. And it was all about just like looking at the environment and replicating lighting and stuff like that. Performance and realism and graphics in AR, a fun little topic there. So that's kind of like where I come from, just so that you understand the context of why I made StereoKit and stuff like that. So first of all, we'll get into a few more details about what StereoKit actually is. So this is kind of what it looks like. This is actually what it looked like about 2 years ago. One of the great things that I can say about StereoKit is that it has been around and people have been using it for over 2 years. And so this is a somewhat mature. I don't consider this to be a 1.0 thing, but people have had this in their hands. People have been making products with it. A lot of the development at the moment is more about resolving feedback from developers that are actively using it, rather than trying to like scramble together like a final product. So it's good. It's nice and it's solid. And I'm very happy to say like it looks similar to this, but just better in all of the corners, which is really nice. But as you can see, like it's got these interactions with your hands. It's got graphic stuff that like all of that is taken care of. Like it has file pickers and user interface and all these fun different things. Like all of these things are really easy to do. Every single one of those scenes that you saw there is like, I don't know, 200 or 300 lines of code, and it's just like a single file that you can swap between. So it's nice, it's simple, goes pretty fast. This is a much more recent screenshot. This is from the latest version, and you can see that like some of the things have kind of been polished up. So StereoKit is code first, and it is very much targeted towards C# developers. So C# developers are kind of like this is kind of my safe space, you know. Like I did a lot of XNA, I did a lot of Unity, spent almost 10 years with Unity, and so I'm really good with C#. I think it's a really good safe language to be doing stuff like this in. It's also very quick for productivity, and so these are things that I found were a really good match for StereoKit. Under that, there is actually a native layer. Like the core of StereoKit is actually all C, C++, and it's all exposed through a C interface. So the C# side of things is actually just first-class bindings to that C core. So if you wanted to approach this from C or C++ or any other sort of native language that allows for bindings to C, then you can also do that, which is really neat. But it's the nice thing about having the C# stuff is it ties in with like the NuGet ecosystem, all the wonderful, amazing .NET stuff that has been happening. I don't know if you keep tabs on .NET at all, but it's absolutely phenomenal what we've been doing with some of the latest versions. So it's a good place to be. I really enjoy working with this ecosystem. StereoKit is actually based on OpenXR pretty much entirely. It was in fact kind of like the catalyst for creating StereoKit. Before OpenXR, I didn't think that I could do something like this. So when Microsoft released the 0.9 version pre-release sort of thing, I was like, yes, this sounds great. I wrote a tutorial for it. I fell in love with it, and I decided to build a whole engine on top of it. So StereoKit basically works everywhere that OpenXR does. Like I can't really think of a headset where it doesn't work. I built it first for Windows and HoloLens. I also added Android and Quest support because this is a huge platform. I'm very happy. Moses and Nova actually came in and helped me stand up the Linux side of this. I'm so thankful that they did this because I actually hadn't really done much with Linux until then. These days, now I actually have a little Linux dev machine on my desk now, so I've come a long way since then. But yeah, so StereoKit works basically everywhere that OpenXR does, and I'll be chasing that. I am kind of working on some additional things, like the native code side of things builds to WebAssembly. So I've got WebXR in the back of my mind for some future updates. This might be a really nice place to go to, but not quite there yet. And the examples that you saw there previously were very much kind of like inside of VR. So this is kind of what it looks like in AR. So I do have kind of like this really deep integration with the sensors and inputs that come from these mixed reality devices. So like eye tracking, like that's just one line of code. World understanding stuff like QR codes or world meshing, things like that. If there's an OpenXR extension for it, then StereoKit does this right out of the box. I know not every AR headset has some of these things, but as soon as those extensions get added, you get them from StereoKit, which is really nice. And then I've also kind of, like the stuff that I've shown so far are kind of these like tiny demos, but I just wanted to kind of show that StereoKit can do some really pretty and large, vast sort of things too. One of my hobbies is procedural generation, so I really like making landscapes and stuff like this. StereoKit is the nice thing about being code first and immediate mode is that it's very easy to represent data the way that you want to. Like StereoKit is not very opinionated about how you store your data. So for procedural generation, this is such a joy because you can just like generate lists of stuff and just toss these lists at StereoKit and it just handles it really well. So like you can do stuff like this too. And then working with OpenXR is really nice. So this is actually Quest with the Facebook pass-through extension. I didn't want to build the Facebook pass-through extension into StereoKit's core because it's a little bit weird and off the beaten path. However, I did want to support it. So this is actually an OpenXR extension that's built on an upper layer of StereoKit on top of things. So you can get access directly to OpenXR from StereoKit and test your extensions or add support for extensions that I haven't gotten to yet, which is really, really nice. And then also in this demo, there's kind of like some hand menu stuff. This is one that I've been playing with. It's kind of integrated into the C# side of things. It's basically a really nice replacement for like a file drop-down menu sort of context. And so I've been using that a lot for kind of like these hidden menu sort of things where you can hide functionality. And then user interface. Because this is focused on app development, I spent a lot of time doing UI and stuff like this. So this is kind of just like a little bit of the variety of UI you can see. It kind of started from an interesting place where I wasn't sure if user interface would be part of the core StereoKit functionality. And so this is technically kind of like an optional layer on top of things. But I have over time decided that user interface is really just something that people need to be able to do easily. So even if you want to go and do your own thing with user interface, you can. I've kind of like broken these things down so that some of them are reusable if you want to like go your own direction, but still reuse some of the work that's done for StereoKit. But it's themable. Like I'm working on a theme that's based on our Microsoft mixed reality design language, which is really nice and beautiful. This is something that's upcoming. I'm using it kind of to stress test the theming system, but you can get pretty close there. This was a recent project that I did where I just wanted something like a little bluer feeling, a little closer to the Windows theme. It's kind of like a little launcher shell. One really big important thing is I feel like it's really important for user interface in VR to be integratable with physical objects. So like this is just a GLTF with a couple of tags on it, and I can generate like little layout areas on the GLTF and then place UI like normal, which is really, really nice if you have like a washing machine with a little UI panel on it. And then I also support Unicode. So on the fly rendering of Unicode glyphs. So if you like, I don't do right to left languages, but it does do basically any Unicode thing, which is really, really good. I was very happy about that. It's a little bit more work to do there, but this should meet most people's needs right away. Okay, so that was kind of like what it does. So this is what it looks like. So this is actually, this top one here, this is a full application and just these lines of code. It's like an initialize, load a model from file, and then the main application loop. So inside of this run, this gets called every single frame. So every single frame, it just calls helmet.draw. If you didn't call this on one frame, it wouldn't draw on that frame. That's kind of what I mean by immediate mode. And to do user interface, it's the same sort of way. It's this immediate mode paradigm. If you're familiar with IM GUI, it's kind of very close to that. If you stuck this in this little run thing, this is what you would get right here. So like doing a button is super simple. It's just a write up button with a little label. You could also toss in a sprite to get an image on there. If you want to react to that button being pressed, you just say if UI.button. It returns true on the frame that it was pressed for. So super easy to do user interface. And I feel like that's super important to being able to do this sort of stuff. And the advantage of doing code first stuff, if you've been in like a game engine or something like that, game engines typically have like these game objects, this metadata, a lot of stuff that is not code. And like, you know, if you're like me and you're a hardcore developer who's been doing a lot of code, you're very good with code. You have all these tools for working with code. And so it's nice to be able to have all of your stuff in code so you can like check links, look at the references, see where things are getting used, use linting tools. So like this is a ruler object that's just defined using code instead of like metadata and stuff. So like you can take this code, you can copy it, you can paste it, you can like stick it on a forum, send it by email, toss it in chat, and they can just paste this into their project and it works. Like you don't have to worry about like, how is this represented in the scene? What components are attached to it? Like Code First has so many nice little advantages like this. So I really love the Code First approach. It's not as fun for designers, but with StereoKit, the nice thing is you can actually build tools really quickly. So if you have designers, you build them a tool and then they can get it started really fast. And then you have a bespoke tool that is specifically for your thing. And it should, in theory, actually be better, hopefully. And then documentation. This is kind of something I consider to be a core feature, and it is built into the engine. So like this on the left, this is a snippet of code that is inside of the engine test project. And so like I'm working with this all the time. This code gets run like multiple times every day. And all I do is I just have like these little tags on it. So this is some markdown. It's attached to these pieces of documentation. There's actually like a little screenshot line somewhere down below. And so when I make a release and rebuild the documentation, this actually gets executed, screenshotted, and it takes this live code and you get this document over here. So you can see it for the current version. This is the live code that generated the screenshot. And so you know that this is up to date. You get a nice preview of it. And I can actually use it as kind of like test data. So I can see if these images have changed. Like all of these images are actually in source control. So I can see like little side-by-sides of how they've changed each release, which is really, really nice. So this is the StereoKit docs should be a really good way to learn. It should be a reliable way to learn. So I love the docs. The docs are great. Okay, and the big thing that I kind of wanted to like highlight is that StereoKit is not a game engine. This is, you know, this is the big differentiator between like why you might choose StereoKit over something else. Like it's not designed for games, and that actually means that a lot of the underlying architecture and approach is different. So, for example, like here's a file picker. This file picker is built into StereoKit. You will. This is the fallback one in particular. So. It'll try to pop a native file picker first. If there's no native file picker, it gives you this fallback one, and you can then load any sort of compatible format at runtime. So like you don't have to write your own object loaders or anything like that. This just works at runtime, and it just goes. Like here's kind of some examples of loading something at runtime. So it's a progressive loading system. So it'll load like the metadata first, and then it'll go and process like all the textures. Since this is kind of like a consumer level format, a transport format. These formats are not optimized for fast loading, but they are good for like transferring over the network or like just storing around, having handy. So like decoding PNGs and JPEGs takes a little while. So StereoKit will in the background just kind of like give you as much as it can right away and then progressively load in the rest over time. And so you don't have to worry about, I jumped ahead there. You don't have to worry about things hanging or sticking while you're loading these objects. So this is a big difference. Like game engines don't do this. You have to precompile these assets. You have to like optimize. It's a very different sort of experience. So this, like it may be a little bit slower here, but this is better experience for this type of environment where you're building apps. Shaders are all optimized and friendly. So like StereoKit is designed to have a lot of extra overhead headroom. The shaders are all very, very fast. Like they are designed mostly for fast rather than for fidelity. So like this is a PBR shader. This is what StereoKit's PBR shader looks like. This will work just fine on a mobile headset. Like you can stick this on the HoloLens, you can stick this on a Quest. It's fantastic. Like it's actually very hard to stress StereoKit out. Like it pretty much always runs really low on cost. So everything was designed with this mindset of being like you don't need fancy lighting, you don't need like all this like ambient occlusion or subsurface scatter. Like you're building applications and experiences with StereoKits, not games. And so the focus is on like making the render simple enough that it works really well with the target hardware and gives you extra room to do other things. So like, for example, this is kind of StereoKit's lighting system. Like basically it just uses a single spherical harmonics lookup for the entire application. So this is just designing a spherical harmonics using a couple of like baked lights. It bakes it down into this little math construct, and this is super fast to sample. It looks pretty decent. You can actually like just load up a cube map instead of doing this, and it'll generate a spherical harmonic based off of that cube map instead. And that's a really fast way to get really realistic looking lighting. But this is like, look at that, that's great. Like that's all that you really need for most things. You could add in lighting if you want to, but this is something like, doing complicated lighting is something that's very easy to shoot yourself in the foot with. So for StereoKit, I don't provide those complicated lighting pieces. If you want to add them, if you have that expertise, you can, but it's not the default. So performance by default, that's StereoKit's thing. And similarly, like this is the sort of stuff that I like to extend StereoKit with. So this is like a little browser using CEF Sharp, and it just like, just stick a browser in there. Like you wouldn't believe how many people ask for something basic like this. Yeah, and so it's important to have this category of thing rather than like, oh, let me stick a BSP and whatever. I don't know, like app focused, not game focused. And then this is kind of the other thing. StereoKit makes a pretty good dependency. So I focus really hard on keeping file size down. So like this, there was a point where StereoKit was under 1 megabyte and I was very happy. Now I'm mostly under 2 for the Windows side of things. I think there's still some extra room that I could pick up on Linux and Android, but I'm still not sad about these numbers either. But basically, like I track these things. Like this is important to me. And if you are taking a dependency on something like this, you don't really want something that's really heavy and like weighty. StereoKit builds in like, I don't know, 10, 20 seconds, something like that. The whole engine, like it's really fast and it's easy and it's lightweight. Over here on the right side, this is an example of using StereoKit from C. So, for those of you who would be interested in taking StereoKit as a dependency, you're probably more likely to be using it from C because you want the performance or the interop with some other libraries or stuff like that. And there's also, like I mentioned, it's easy enough to bind this to another language. There's some people in the community, like Nova in particular, is using StereoKit from Rust. So it's totally possible to do those things as well. And I'm going to wrap this up because I'm about out of time. So these are kind of like, when I designed StereoKit, just to kind of set it apart from other things and allow me to create this with limited resources, these are kind of the things that I set down for myself, like focus on mixed realities. Like I wouldn't use StereoKit for things other than mixed reality. Keeping the API simple, like this immediate mode, lack of architecture sort of thing, like letting you define your own architecture. Fun is important to me. If I'm not having fun, I'm not doing it. So like mixed reality development needs to be fun. Like there's no reason for it not to be. Not just for games. Like this is a big key one. Everything else out there is very much kind of like focused on the games side of things, and that's how I wanted to stand out here. Performance by default, and then trivial user interface. And this is all on GitHub, so like you can just go grab this. It's MIT licensed. It's been up there for over 3 years now, and I've had so many lovely people come by with little contributions here and there, and I'm so thankful for all the community and everything. Like this has been such a great experience to work on StereoKit and just work with everybody here. So thank you so much for all of you people who've contributed, and I hope you'll continue using it and all that fun stuff. So that's all I've got for you today. You can hit me up on Twitter. I'm Kojaki there. StereoKit has a nice little Discord. It's all linked on stereokit.net. There's a whole bunch of extra little repositories on the StereoKit organization on GitHub as well. So that's my talk. Thanks for coming. Any questions? I guess we're probably
Thank you so much, Nick. Yeah. So I don't see questions out of now, but a lot of comments, of course, like people like loving StereoKit, of course, like saying like keep it up, and you know there's a lot of excitement. I mean, at Collabora we're using it internally for a lot of demos and projects. Of course, I mean so thank you for your contribution. It's a very important piece of software. I see there's a question from Nova here in Minneapolis. So.
Yes, hi Nick. I am a very dedicated user of your software, and I only have but one question to ask. When blend shapes?
I somehow knew that was coming. Yeah, I kind of have a roadmap towards 1.0, so I'll just talk about it in that context. I've been kind of working towards like what can I call something as finished here? Like when is finished for StereoKit? Like what is the 1.0 where I can like say that I have all the features that I want? And I'm hoping this is going to be something like maybe early next year. I've got a roadmap, so it's on there. I'd probably toss this in like a GLTF conformance testing. So GLTF is kind of like what I founded StereoKit's core model format on, and it informs a lot of the design actually. But I wouldn't call it 100% conformant. Like most of the stuff that you throw at it, it'll get. But there's some edge cases where things are a little bit more complicated. Like I'm not going to get some of those like caustics and whatever that they have in some of the spec. Like that's just a little out of scope for something that focuses on performance. But we'll get there. We'll get there.
Thanks. And a question here from the in-person attendees. Bill?
Yeah, thanks. Nick, I got a question. If whether you've had the opportunity to try or you've put any effort into making it run in multi-threaded mode, say you have multiple screens and you want to render the same world from different perspectives on, on the same computer, same GPU?
So I guess it depends a little bit on the context of this. Are you talking like a multi-app experience or just like multiple views into that same experience?
So multiple views into the same experience.
Okay, so this is kind of maybe something like this little GIF here on the right side. So I actually have a little tool where like you can just render to a texture, and it's pretty easily. I've tossed this output into like a Teams webcam and stuff like that, or like little mirrors here and there. Asking about Cave. So Cave sounds like something that might be more of an OpenXR side of things, where OpenXR would provide multiple different views. I don't really know about that, but you might be able to hack it with some of the render to texture stuff, which you can definitely do the render to texture stuff.
Thanks. Another question here from Ryan.
Hi. You intrigued me by saying it runs on Android. Can you use the C# stuff on Android, or is it just the native?
Yes.
And
right now I have
OpenXR
a little,
on Android.
Yeah, I have a template for Xamarin, and so it currently deploys through Xamarin. I will be shipping a Maui-based template somewhere in the next few weeks. Like this is my current big project is standing up the .NET Maui multi-targeting stuff, which should simplify things greatly from the current Xamarin setup. I don't love the Xamarin setup, but yes, you can do that from C#.
Thank you so much. Anyone else? I think we're at a question for now and out of time maybe. So thanks a lot for this wonderful presentation. Let's catch up later on this, but for now, I mean, take care and thank you so much for being part of this. All right?
Yeah. Thanks for listening. I'll be in the chat if you have additional stuff.
Thank you. Bye-bye.
Hi, I'm Ethan Merchant, and over the past 4 years, I've been setting spatial interactions free at DOFDev. Today, I'll be going over what I've learned, and hopefully get you more interested and invested in XR interactions and getting them open sourced, because we can do better. So, jumping straight into it, I have a sort of example of my own. So, back in 2018, started making a game based on Missile Command, adapting it for VR, as just a way to, get past the hurdle of just making a full game, getting it out there. Because I've done that in the past with other flat screen games. So, trying to get the most out of the VR hardware when there was just like such a core, simple experience. The choke point at that point really became interactions. So for you to get the most out of it visually and experientially, throwing the player in the thick of it, as you can see here, just right in the middle of everything, 4-meter radius of missiles and other things just flying in at you, really made for an engaging experience. But you needed to accurately target points out in space within that radius, which is not something I've seen a solution for as of yet. But because, once again, this very simple core underlying game concept, trying to get the most out of the hardware, and being a bit stubborn, we ended up just iterating and iterating on this interaction. And through that process, and we ended up stumbling upon something that we thought was pretty cool, pretty unique at the time. I ended up calling it a stretch cursor. So any sort of take one step back from there. So once we came across this, it was very clear, in our minds at least, that this is something that we should make more available in the world, and not just lock down and hide it inside our own like private code base. And so that's when we started figuring out, okay, what do we call these things? How do we communicate them to other people? How do we make better ones? How do we make more of them? And it just got the ball rolling for DOF-Dev. So you can see right down here, we have a side view. We'll click through to see it a little bit closer. So this side view really makes the interaction very clear. And to be fair, this is not super advanced interaction. Other people have figured out some other things by now on their own. But as you can see, there's a relationship between these two controllers where we're able to calculate out a delta by subtracting the to vector from the from vector. And from there, we get a direction we can use and a stretch value that we can use to extend a cursor out. Yeah, so just that diagram alone is pretty useful. You could probably just from that reverse engineer it, figure out how to implement it into your own code base. But when you get to more advanced interactions, or if maybe this seems a little bit daunting given your current skill set, then it can be really worth it to make a spatial pattern. That's what we have down here. So a spatial pattern, if you really want to be pedantic, is just pseudocode. But I'm calling it a pattern because it gets away from the word pseudo, like fake code. I'm not really trying to point out that it's fake. And so instead, called it a pattern. So the reason why it's called a pattern is other people, as well as AI, are really good at picking up on patterns. So if you communicate things in that way, it ends up just being a lot clearer for everyone involved. If you're trying to communicate something to the computer as well. So, which in the case of code, that's literally what you're doing. So we have a general sort of structure that might seem familiar to anyone that's done, XR code or game code or any sort of real-time experience. And that is to kind of break things out into input, data, frame logic, and design variables. And I'll go line by line in just a second, but I thought it'd be more engaging if I showed how easy it is to implement this into your own code base once you've put the work into making this sort of spatial pattern. One quick thing I will point out, though, is it is to the day the 4th anniversary of the stretch cursor, which is a little bit uncanny. Yeah, so what we'll do is we'll copy this out. We will switch scenes, hop over into the code, and we'll paste it right above into a commented out section. Now, by yourself, you could just look line by line and get it all implemented. But if you are lucky enough to have an AI assistant, that process can become that much easier. So so far I have the input. It's 2 vec3s, and now I'm getting the data. I have a float stretch value, as well as a vec3 cursor. Now, let me scroll up a little bit. So I've got a pattern on the left. Let me move over to the right a little bit. Before we get to the frame, we'll get the design variables plugged in. So Copilot might get a little bit lost here and there, but if you rein it back in, it'll keep on cranking. So now we have the dead zone and strength variable. And now Copilot wants to get all the frame all in one go, but you can see it gets a little bit confused with some of these shorter formed words that I like to use. And in that case, if you just hold its hand just a little bit more, there's no need to put a comment there that says frame because the function already says that. We'll show it that we don't want it to just use MAG. We'll have it use the StereoKit specific magnitude. Then we'll crank out the stretch value. We'll switch this over to math F. Now, before we move on to the next parts, the magnitude is just we take the delta between those two controllers, or these two points, and we get the magnitude out from there, or the length of the vector. Now, the stretch value we calculate using the magnitude, and we subtract the dead zone design variable from it, and keep it right above 0. And that allows you to bring the cursor all the way in without smacking your hands together, which you might not realize you need to do until later. So having it baked into the pattern can help other people who are trying to implement this interaction. Next, we'll get the direction. Now, StereoKit does have a direction function. It's just not in the version I have right now. And cursor position just takes in all of those things we've calculated so far and extends it out from the vec2 using the direction times the stretch times the strength. Next, for the purposes of this demo, we will draw out some debug visuals. So StereoKit has these amazing immediate mode rendering functions. I'm able to just throw lines up out of nowhere in cubes. As you can see, we got one for the stretch, we got one going out to the cursor, we've got a box rendered out for the position of the cursor, so all good to go. Very painless. And yeah, this is something that I haven't seen other people push, and I see it as a very good way to open source these interactions. Just to reiterate, you should be able to do this with other code bases, other engines, and get similar results. Depending on your engine, if it really doesn't have that much vector math, you may run into issues here and there. But in those cases, I would recommend when you're making a spatial pattern to link to open source references for any code snippets that are a bit more esoteric. That way, there's still a path forward for them to implement it in an engine that has maybe less vector and quaternion math. All right. Let me bring my timer back up. Cool. So, we'll hop back to the spatial pattern. So, if you can tell by the border, this is just an embed, an embedded iframe. Once again, we're really over-optimizing for open sourcing things, so we don't want to be the single choke point of anything if we can help it. And so what this is doing is if you click right up there, that'll take you to the source control. In this case, a GitHub repo with the raw text version of the pattern. That way other people can contribute to this. And that way it's, has source control, so you can roll back things. And that way it's also easy for other people to host and show their spatial patterns in this sort of form. So the way this works is I'll grab this URL up here, and if I go to dofdev.org/pattern, I'm taken to this page. And you can see here, I can just drop in a GitHub pattern URL, paste it in, submit it, and I get an iframe that I can put wherever I want. And it will show up just like this does, which is super handy. Now, we're not against hosting other people's DOFs on our website. If that's something you're interested in, let us know. Also, if you end up implementing one of our DOFs in one of your own pieces of software, we would love to hear about it and add it to a list. Underneath each of these DOFs, we'd like to have like a list of things that it's used in. That way we can really kind of see the impact of it. And rather than it just being like, it might be happening out in the world, we can like really show it. Yeah, just to go over what DOF Dev is relatively briefly. Because once again, we are kind of pushing different ways of doing things, some different terminology. So iterating it is kind of the only way to get that across. So DOF Dev is Degrees of Freedom Development. And yeah, we are an effort to open higher degrees of spatial interaction free to the world. It's me and Niko. I'm on the engineering side of things. Niko's on the design side of things. So if you're looking to know how to think about these design spaces and really start grappling with them and applying them to different things you might have not expected you could do, then I recommend checking out Niko's talk, which is just after mine. Yeah, so DOFs, like the definition of DOF right now is sort of like, a degree of freedom, which is usually used for like robotics. So if you have something that can maybe move in like one dimension or rotate in one dimension, then you're like, oh, that's one DOF. Or if you can rotate in all 3 dimensions, oh, it's 3 DOF. You can move and rotate, 6 DOF. So most people in the XR space are familiar with that word. And so we ended up finding that while that is a very useful word for very like hard and mechanical things, there's also an interesting interpretation of it when you take it from sort of more of a human perspective. And when we did that, it ended up being a very good term for these like principal proprioceptive remappings, these core XR interactions, where you can kind of build up quite a bit off of them. But they have this sort of core, unique sort of attribute or capability that wasn't kind of there in the world before. And yeah, once again, they are distilled into free and open source interoperable patterns. And we have a whole bunch of them on our site here. I do not have time to go through all of these right now. I recommend checking them out and seeing if they could be useful for you or for someone else you know. Yeah, at this point, I will open the floor to questions. Thank you.
Hi, everyone. Thanks for coming to my talk on OpenXR on Android, source included. I'm very honored to be speaking among so many exciting projects here today. It's really been a great conference so far. A bit about myself. My name is Ryan Pavlik. I'm a principal engineer at Collabora, where I do a variety of things related to OpenXR, our Monado runtime, and other things in the XR division. And I also serve as the specification editor for the OpenXR working group. That's an elected position I've held for a while, and I do that through my work at Collabora. They support that. So here's what we're going to look at today. And it looks a little dry, but we've got some front-loaded fun too. We first want to look at sort of the requirements and use cases that relate to using OpenXR on Android, because as you may know, OpenXR on Android was not quite as fully baked at the release of the 1.0 specification as OpenXR on desktop was. Then I'm going to go over what we actually did build, given those constraints and requirements, and how you can use it. And we'll have a little time for questions. I do want to point out that I do not and cannot speak for the working group, for the OpenXR group. But what I can do is I can discuss the things that I kept in mind as I helped lead work to sort of standardize across vendors how you'd use OpenXR on Android. So I sort of fell into the position of leading some of this work, doing some of this development. So I can tell you what I thought. When I say we, sometimes that means the working group. Sometimes that means the Monado community. I'll try to clarify if it's relevant. But here's your dessert before dinner. You can take the same exact Hello XR binary that comes with an OpenXR release. You can take one APK and run it on the Vive Focus 3, which is a standalone Android-based VR headset. And you can run that same binary on this exact phone, a used Pixel 3 that has not been rooted, that is running the fully updated operating system, and put it in a Google Cardboard or some other phone holder device. And the whole stack that lets you do that is designed to be open source and designed to support user choice. So how did we make that happen? There's been a lot of talk about OpenXR. I do want to mention a little bit about the mechanics of how it works. OpenXR provides an interface that lets you interact with an XR runtime, which is usually device specific, in a uniform way. So you don't have to build an application for Oculus or HTC. You build an application against OpenXR and it runs on all the headsets, is the idea. So what you actually build against is something called the OpenXR loader. This is a library that does dynamic loading of the active runtime based on some specifications of where that data is stored. Runtimes all implement core functionality. There are some extensions in addition to that core functionality that end up being required for graphics API use. And then as runtimes and hardware and technology advances, new features are prototyped as extensions, and they follow a pathway towards standardization. So the main requirement, the base truth that we want is we want a single loader library to use on all OpenXR Android devices so that you can build a single APK to run on anything that's Android-based. There are three basic kinds of hardware use cases that I wanted to keep in mind as we were developing this. There's the all-in-one headset. This is probably the most popular one currently because it doesn't require you to tie up your phone like the cardboard did. So it's a device that just does XR and that's it. There's also plug-in viewers These are slowly being released onto the market where they use your existing phone for some compute, but then they serve as a separate display, sometimes integrated with the phone, sometimes not. And then this last one, which I kind of took as almost my pet project, is the slide-in phone holder thing. This is a very, very accessible way of doing XR, VR. And so I wanted to make sure that we didn't leave it behind. So if we look at those use cases, the standalone headset, it's all it can do is XR. So it's going to have one runtime, and it should be enabled by default. You don't want to have to check a box when you pull your Quest out of the box. But the other two, those involve installing software on a device. So the runtime has to be able to be user installable. It doesn't have to, it has to be able to not be on the system image. The user has to have control over what the active runtime is, because if you could install one, you could install two, and then you have to pick. You might have a phone that ships with the default runtime. So like back in the old days, Gear VR came on a Galaxy S8, but you might choose to use it with a Daydream headset instead. So you need to be able to override that. And finally, because we weren't going the route of adding this to the platform and we wanted to bring this up quicker, we want to be able to run on existing platform versions and Android versions. So not waiting for a new version of Android. There are a couple more requirements that came up that are not directly tied to a single use case that are important. The first one is that the rest of the loader on desktop is in C++ and exposes a C interface. It would be really nice if we could avoid having JVM code, Java code, in the loader, if we could just get away with using native code and JNI calling into Java interfaces, which means we can't use something called a bound service to find our runtimes or access our runtimes in the loader. There is binder NDK, but that's more for system-level services. And then there's sort of a cluster of requirements around security and privacy, which I really wanted to focus on. Number one is store compatibility. If in the US, if you can't ship your game on the Play Store, you're not shipping your game. So we have to be able to comply with the security and privacy requirements of various app stores. Ideally, we'd like to not have to constantly be re-engineering things, or at least be able to update older software to be robust to platform updates. Security tends to increase, restrictions tend to increase as the platform matures, and so we want to make sure that we're not doing anything on the platform that's sort of borderline not cool. And then finally, as a general privacy item, we want to try to minimize the permissions needed for applications. So these three together suggest that, unlike on desktop, the loader on Android can't do all the work. We have to move it out into a separate package, which is what that lower left one there is. So these are the same requirements boxes that we saw before. All these green ones we've seen before. Can't use a bound service, user installable. So there's something called a content provider. It's a thing you can do with native code, and that is one piece of the puzzle that solved our can't use a bound service. For user installable runtimes on existing devices with user control, we introduce a installable runtime broker. This is a package, an application that the user can install, and it owns the preference of what the active runtime is, and it is in charge of finding the runtimes and choosing which one's active, or rather letting the user choose. For the all-in-ones, or devices that ship with a runtime, we also need a system runtime broker, because again, you don't want to have to check a box when you take something out of its packaging. And because we want to be able to support the case where a device vendor ships a runtime, but you want to use a different one on that phone, we need to check the installable broker first, and then the system broker. And then for compatibility purposes, we actually fall back to searching Linux-style paths for manifests. So now you know why we built stuff. Here's what we built and how you can use it. We said we need an installable broker. Here it is. It lists runtimes found by manifest metadata. So if you want to make an OpenXR runtime, you mark up your package in the manifest and you provide a specific service. It's all in the loader documentation, and then it appears in the list here. Nothing is checked by default, so the user has to opt in to any of these runtimes being active because of the sort of pervasive and highly sensitive nature of XR device data. If none of these are selected, the loader will fall back to looking at the system broker and then system manifests. We're planning on publishing this installable broker to F-Droid as well as to Google Play. And this is open source. It's maintained actually in the Monado organization. It'll be, when we get it on Google Play, it will probably say it's published by the OpenXR working group. The idea with this is that the vendors do not customize the installable broker. This is solely the user's item, and there's only one of them. If you need to make your runtime discoverable, you either use the protocol that's described or you customize the system broker. So how do you use it? Well, download a release. There will be APKs when I tag a release. Right now, you just download it and build it. Then you install a runtime. You open the broker and enable your installed runtime. It's just checking a box. And you'll get to a runtime. So here's another thing we built, stubs for the system runtime broker. For vendors making all-in-one headsets and devices, this implements everything except the part that says where your runtime is. The idea is that vendors will take this and make this part of their system image, and they'll just hard code the paths in. There's no UI involved. It's just a little bit of code that serves as a here's where your stuff is notice. How do you use it? Well, if you're using a Focus 3 or any newer conformant headset, you're already using it. There's no UI. It just works. If you're developing your own standalone device, just fork the broker repo and customize the system runtime chooser. And that's how you use it. The piece that's application developer facing is the cross-vendor Android loader. Instead of finding the runtimes itself, it talks to the brokers, as we've discussed. One APK will be able to work on all Android-based OpenXR devices. There are some vendors who are early adopters that used a legacy loader, and they're still migrating to using this one, but the cross-vendor Android loader will be the one going forward that folks will use. It's maintained in the same source tree as the desktop loaders, and it actually shares the vast majority of its code. It's licensed Apache 2.0 or MIT at your option for GPL compatibility. And at each release, we publish AAR artifacts, which are basically Android-specific jars, to Maven Central so that you can use them in Gradle. And they're also published in GitHub releases. For instance, I know they recently updated the Unity OpenXR Android plugin to have this used, and they just used the AAR from the release because they're not using Gradle there. If you use it in Gradle, this is what you do. You enable the prefab. That's what allows you to link to a native code library in an AAR, and then you add it to your dependencies section. There is one small caveat that is, at the moment, you need to make sure your target SDK version is not greater than 29. There's an issue we're working on, almost done fixing it. But for now, leave it at 29. We've got binaries. Hello XR, if you go to the OpenXR SDK source repo and click on a release, you will get, you'll have 2 APKs there. They're almost the same, just which one depends on the default graphics API. And the conformance test suite, starting with the next tag conformance release, will also have APKs. So running conformance will just be downloading and installing the APK and following the steps. And that's where you get them. Switching wheeze here. The Monado community has built Android support into Monado. We're not officially compliant yet. There's been no submissions, but it works. It's right here. And by default, it runs in a phone holder, cardboard style mode, so anybody can get started trying out OpenXR on Android. So there's APKs built by CI. Just download and install them, or you can use Android Studio or Gradle, install it, check it in the broker as active, and put on some apps. I'd like to wrap up by thanking folks. This talk makes it seem like this is a young thing, but we've actually gotten a lot of community contributions already, and we really appreciate that. The OpenXR repos, the runtime broker repos, and Monado. Thanks to the working group members for their feedback and code and constraints, and thanks to Collabora for making it possible for me to work on this. Here are some URLs. If your employer is a OpenXR working group member or a Kronos member, please feel free to get involved. Otherwise, the main place to get involved is on GitHub. All these links are also in the presentation materials on the FOSSXR website. Thank you very much.
Thanks, Ryan. So we have time for maybe one question or two. So is there anyone here with questions in the audience? I mean, everybody must be knowing a lot about OpenXR already. So I don't foresee any question, but there is one. Hey, what's this here?
Hi. So I have just one confusion. You mentioned, like, runtime providers must not modify the installable broker, and instead they should modify the system broker. I feel like I might be missaying that. I feel like I don't understand the difference between the installable broker and the system broker.
One of them comes on the system image. The system broker is the one that comes on the system image. The other one is effectively what would be in your settings panel for OpenXR if this were part of official Android. So if a vendor modified the installable broker, then it wouldn't let the real one be installed, and it would take away the user choice. You can only have one package per authority installed. So that's why there's two.
The question here?
If I were to have an all-in-one headset, say the new Lynx R1 that I think ships with that loader, and I went on to install the installable broker, and I selected a different runtime, is it possible that the system could break due to selecting a different runtime for all different apps, especially like the launcher app?
Yeah, it would probably not do what you want. It is possible. There is actually a bug right now that if you put the installable broker on the Wave 3 and have anything checked, it won't be able to load it because permissions and things, but if you leave it unchecked, it's fine. There's probably no reason to install the installable broker on an all-in-one, but there's nothing preventing you from doing it, and it shouldn't be a fatal issue.
Yes, it's worth mentioning that Corajan, I think they got Monado building and running on Oculus Quest, and I think they got the installable broker working there too, right?
I don't know. They've done a ton of really cool stuff. The Monado Discord, we have a really active Android channel with a lot of community members. And then we've got folks that are just dropping by GitHub and GitLab. So there's a lot of exciting stuff going on. I think that's probably all we got time for.
Yep, exactly. Thanks for the very informative talk. And thank you again, and see you.
Thanks very much.
Nope, no, don't do that. cameras up. So for the last like 30 minutes, honestly, Mark Zuckerberg has been trying to not allow you to see this content right here. All right? So just be aware of that, all right? Going into this conversation we're about to have. All right, so what I have right in front of me here, this is a cool little thing. It's a volumetric graphical control interface, or graphical control element. It's the three-dimensional version of a window, right? And you can see that I can, okay, here, look at this. So like I've got my hands apart, and I come over here, I grab my wrist, and then I extend from my wrist. Ooh, isn't that fun? All right. All right, boom, put that over there. And I can grab each corner individually, but I'm gonna grab all of them at the same time. So this is a, yeah. So this is a cool SDF rendering method. We call it an Oriole. That's an architecture term that is kind of like a three-dimensional window type thing. Yeah, and this is kind of an idea for a future three-dimensional interface, three-dimensional operating system. Obviously, you want to be able to go in and out of your experiences at will, launch them wherever you'd like, put them anywhere in space, and choose whether or not you're totally immersed or, you know, playing the experience from the outside. So I can walk around in here, and I can also, whoop. Yeah, cool stuff, right? And so I've got a few different spatial cursors here. Like I was showing you this one I grabbed from my wrist, just like that, boom. Oh, got it on the other hand as well. This one right here, this one uses the twist of my hand, right? So that's converting rotation into position. So I'm using the roll of my hand and using for the scalar that is controlling the point in space, and then the pitch and yaw to be able to, you know, point it around places. Whoop, it's a little messy, but it's fun. And then here is a reach cursor. I plot a point in space and I move from it. And that allows me to spatially manipulate with both my hands at the same time. I've plotted the point right there. Ooh, fun stuff. Oh, can I grab this? Yeah, and I can even rotate just with this one hand while also spatially manipulating. Very fun stuff. All right, I'm gonna take you out of this demo now. And give me 1 second, I'm gonna load up one more demo. Oh, come to me. And yeah, no issues this time, no crashing, because we're using the Quest. And so you can see, like, you saw how much, like, how good I was doing in here, but now that I'm just using this pointer, things become a lot harder. Hey, see? Can't even click on the right thing. Sorry, we'll get to more in just a moment. Oh, am I gonna get it? Very powerful. All right. Hey. All right, now we got some hand tracking. Oh, I appreciate you so much. I don't think you can. All right. Yes, so all right, so right here I've got the spatial cursor that I'm manipulating with my hands, controlling that. Just a fun thing here. I'm gonna show you that a little bit better. Get a longer trail going. Turn down the strength a little bit. Oop. There you go. yeah, fun stuff. Yeah, does this look hilarious? Okay, so you can see I'm controlling the positions using this using my fingers right here, right? Using all my fingers to control this position. And then I also have this little box right here that I haven't talked about yet. And this is a thing where you get position and convert it directly into rotation. Hell yeah. Yeah. Hey, is right. Yeah, so realistically, what we're doing here is, trying to extend our reach into the far field in a intuitive, proper way. And also being able to properly remap different degrees of freedom of our body to be able to control different things, like right here, this is a position to rotation interaction. Obviously, there's no rotation on my thumb right now, but using this interaction right here, I can swipe around, and the tracking kind of goes bad sometimes, but come on. Yeah. And then also that thing in the middle can be a button as well, or you can have a button on the outside. I'll explain the layers of that during my slides. Got you. Yeah, you could also, I don't know if we can manipulate the Oriole right now, but yeah, very fun stuff. Very fun stuff. Here, this is kind of cool. You can kind of draw triangles. I don't know if I'm gonna be able to do it with the way it is right now, but you can kind of see I'm stopping at each individual, kind of like vertice. Yeah. So yeah, we're DOF Degrees of Freedom Development. Me and my friend Ethan. You heard a little bit from Ethan earlier. Here, how do I press the play button? Where's the play button? Control Shift F5 is what I just heard from a wonderful person in the audience. Look at that. Control Shift F5. No. Oh, okay. I thought you're no. Yeah, so Ethan told you a little bit earlier about how we got into this. We found these cool interaction stuff. I just want to quickly tell you about why I'm still doing this and why I think this is really cool. A few years ago, I had a really bad back and neck injury, and yeah, I couldn't really use computers or phones for very long anymore. It was just very painful. The posture that I had to put myself in, always just looking down and keeping my hands up like this, it was really, really too much on my neck and back. And I was like, this VR thing is pretty cool. I wonder if that could help me. And then I tried VR, and I saw, what you guys saw when I was just using the Oculus menus, which is these pointer interactions and all these, and having to go out of your way to interact with things. And I was just pissed. I was absolutely pissed. I was like, we have three-dimensional tracking technology, and I don't think we're utilizing it correctly. And so yeah, that's me. And so me and my friend, we started DOF Dev, which is an effort to open higher degrees of spatial interaction free to the world. Kind of a mouthful, but basically what that means is we are trying to identify and expound on three-dimensional interactions for a future 3D operating system type thing. And we're trying to ensure the freedom of those things as well. So licensing these different interactions to be able to properly protect them and make sure that everyone can use them. Yeah. So yeah, we've got natural extension interactions. That was what you were seeing with how I was just controlling that point in space. Oh, sorry. Move it up. Thank you, Frederic. So yeah, cool. Natural extension interactions. All right, so you saw what, is this cool? All right, am I in? All right, great. Okay, so you saw what Ethan was kind of talking about before, right? You got these 2 points in space, right? And we connect those. Here, I'm gonna use a different one. Bigger. Be that guy. Boom. Boom, 2 points in space, right? Okay, we connect them with a line, or we can see, that they have this distance in between them, right? We want to use this distance to be able to like manipulate stuff and interact with stuff, right? And so how do we do that? Well, it's a very, very simple equation. This is x. X equals the distance in the real world distance, real world measurement. This is a little small, but I'm sorry about that. So that's a real world measurement right there. And then we also, I had to draw it too big, so I'm gonna have to draw a not straight line. Sorry about that. But yeah, this is x times y, and y is just a multiplier. Y is just a multiplier. IER. Cool. And so yeah, what this would look like is, x, it could be 3 centimeters, right? 3 centimeters. And then y, let's say, is 3. So we've got 3 centimeters times 3. What did that give us? 9 centimeters. Am I wrong? So yeah, that is the very, very basic way of thinking about that in 2 dimensions. Yeah, really quick before I move on from that, I have my little stick here, and just another, it has a little bend in it. Sorry about that. So yeah, the 3-dimensional way of looking at this is right, we've got these 2 points in space, which are my hands, right? And as I move one hand closer to the other, the black piece of tape at the end of the stick goes further into space. Very fun. Yeah, it's like a move. And so like one easy way to think about this is, like a broom, right? We use a broom, same way. All kinds of interactions are like this. Yeah, it's very simple stuff. Oh, before I move on from that, oh no. There you go. Okay, so yeah, really quick point. So in VR, you're able to manipulate yourself and the world around you, and so there's not necessarily a need for being able to reach out into the far field. But in augmented reality, that is not the case. You cannot scale yourself or the world around you necessarily very, very easily. And so it is very important that we be able to interact with that far field in an intuitive way. Cool. And so yeah, relationships between points, we just kind of went over that. So the reach cursor, the one I was showing you, I plot a point in space, move from that point. That shows, you can see, right, so you've got another point, you've got a point in space, another point in space, and there's a 3-dimensional graph, there's kind of like a 3-dimensional graph in between those things, or they're inside of a 3-dimensional graph, right? And so one of those things is the anchor, and the other one moves from and towards the anchor and around the anchor. And yeah, and that's an XYZ thing, and so you can get a you can get a position in space off that. My fun stick. This is a cool little interaction. Like you were seeing that Oriole that I was talking about for a second. So this orbital view right here, this would be a fun way to be able to view that Oriole without having to rotate it yourself. So you've got the Oriole in front of you, and it has all your content and stuff in it. Well, all you need to do is just rotate your head, and it will rotate the Oriole along with it, so that you can just view the Oriole from any position, orientation. Sorry, what's that? Okay, cool. And so you can also add a multiplier to that as well, so so that you could just move small amounts, and then it could rotate like the full amount around. Fun. So yeah, That thing on the left, that was the twist cursor I was showing you. Just twist your hand, kind of like a screwdriver type thing. Screwdriver like spatial control. And this is like a little representation of what that trackballer looks like. It's just the layers of it. So at the middle, we've got like a one-to-one rotation around a central point. And then the next layer is this like zero gravity zone, right? So as you're moving around this thing and you're rotating this thing, you can go into the zero gravity zone, right? The zero G zone, and it'll read the direction and the speed as you go into that zone, so that it can just keep that rotation going, right? And that way we can just do that interaction. That's just like that. And then yeah, we can put a select and deselect at the outside and on the inside. And this set of layers can be reversed. So use cases, some fun stuff here. 3D modeling, right there you've got a cool little Bezier curve shaper. I imagine that would be really cool. You could kind of make like a shape with the Bezier curve, and then you could do a select interaction, and it would kind of, as you move the Bezier curve, it could like basically print a line behind it in the direction that you're going. I don't know if that necessarily makes sense, but yeah, it's fun. Construction, that's just kind of a silly GIF right there, but it does make sense. Like you could imagine like, you've got this like big old crane thing or big old thing. I don't know what these chomper things are called, but excavator, let's go with that. So you could control, wait, do excavators have orientation though? Okay, cool. Okay, so you could control the orientation and position of the excavator, through a natural augmented reality interaction instead of, using all these perhaps arbitrary physical interactions. And then, of course, volumetric graphical control elements, which are what we call, which are these things that I was showing you as well. We call them Orioles. I can really quick show you what an Oriole is, but it's all good. And before I move on from there, I'm going to really quick. Oh, actually, yeah, I'm going to show it to you. Screw it. All good. Do I have sound? Sound would be sick. You know what? I'll just close caption it. Hey. Sorry. So basically right here, Brandon J. Law is describing this dev manipulator that he has in Boneworks, right? And it's really cool the way he describes it. He describes it as like the people who created the Boneworks world use this tool to create the world around them. And then he says, and what's really cool is that we actually use this tool to actually make some of the environments. And what you can see, what I think is that this just really well corroborates the idea of like natural extension interactions and remapping and such. It just corroborates the idea really well. And yeah, freaking, I was gonna say something else, but I forgot. Dang. Oh, some more things right there. Some more spatial interactions. Yeah. Like I said, we're DOF Dev, Degrees of Freedom Development. We make some cool stuff, I swear. We don't have a lot of funding or anything like that. We're just two guys, legitimately just two guys. And we've been doing this stuff for 4 years. I think we've outlined stuff really well. Oh, I remember the thing I wanted to say. Like I said, it corroborates the stuff really well. But what's really cool is that I forgot what I was going to say again, and it'll come back in a second. So yeah, like I said, we don't have a lot of funding. It would be really nice if anybody had any opportunities for us, any sort of funding that they could give us. We really appreciate it. I literally work at a grocery store, but I really think this is important for the future of XR. I think this is important for people with different disabilities that maybe they can't use their whole hand or to interact with something. Like I said, I came at this from the point of view of I have a lot of back pain and neck pain, and so I wanted to be able to interact with a computer in a way that doesn't require me to assume a annoying posture that hurts me. And so I think as 3D tracking tech gets better, you know, being able to use these types of interactions at our sides, or being able to use even a camera to track other body parts, and then we can use these types of interactions to intuitively spatially manipulate, would be really nice. Yeah, that's it. Sorry. Yeah, all good.
Thank you, Niko. We're not gonna have questions or time for questions, but please, here in Minneapolis or you know, watching live, please go on the website on our chat room and ask all the questions you want to Niko. Thank you again.
Thanks.
Cheers.
Appreciate you all.
hello, welcome to this talk, and thanks for being here. So yeah, I will be talking a bit about the work I've been doing on visual inertial tracking for Monado, and how I've been leveraging like different research systems from academia and integrating them into Monado. Okay, so first a bit of background for me. I'm Mateo de Mayo. I started working on Collabora last year on July. I started doing an internship, a 6-month internship, working precisely on this, on visual inertial tracking. And the work I did for this internship was also the work for my thesis for my computer science degree at FAMAF, the National University of Cordoba, Argentina. In general, you can find me online as Mateo SSS or Mateo de Mayo, and I let in the slides some links to things like my blog and my YouTube channel that I sometimes upload things related to visual inertial tracking that you might be interested in. Okay, so I'll start by trying to explain what I mean with visual inertial tracking, because there's a lot of problems with terminology in the area, so I will try to distill this a bit. So tracking in general is knowing the pose, which is the position and the orientation of some real-world entity. It can be anything. It can be tracking your eyes, tracking your hands, tracking your foot, or in the case we are looking at, tracking the viewer of the XR experience. The viewer might be the head, if you're using a headset, or a phone, for example, tracking where a phone is if you're using like an augmented reality application, glasses, and so on. So more specifically even, I will talk about a VR headset in general, because that's the thing I'm most familiar with and the thing I've been testing all of this stuff mostly on. So why visual inertial tracking is important? Well, just not so long ago, we had many commercial devices, commercial headsets that came with external sensors, and that was kind of like the mainstream way of doing tracking, like 6 degrees of freedom tracking. You can think of the Oculus Constellation devices, in which you had to put 2 cameras in front of you, or the Lighthouse trackers for the Valve Index. In general, those systems work pretty well. The problem is that external sensors are annoying in many senses. First of all, they take a lot of space, a lot of cables, and like just in the box of the device you're buying. There's also the problem that you need to calibrate them as an user, which is annoying, and also they add to the costs of the devices in general. So right now we are having the kind of like the last years, the industry has been moving forward towards using what we will call inside-out tracking. This is also a term that is kind of controversial, but let's call it inside-out tracking for now. The idea is that you put all of the sensors in the headset, and you use these sensors to track around. And again, we are doing visual inertial tracking. That means that we'll be using visual sensors, those are cameras, and inertial sensors, those are IMUs. So cameras are basically things that take images. As you know them, they are basically high latency and low frequency. You usually have like you can think of 30 frames per second that you get from these cameras. And they're high latency because an image is a very big chunk of memory that you need to pass through USB or something. And compared to that, we have IMUs, which are inertial measurement units. These are basically a combination of an accelerometer for measuring linear acceleration in the 3 degrees, and a gyroscope for measuring angular velocity in the 3 degrees, in the 3 dimensions. And in contrast to the cameras, these are very low latency and high frequency because you only have like 6 numbers to pass for a measurement are just 6 numbers, and usually get like IMUs with about 1,000 measurements per second. So the nice thing about using these 2 sensors is that they complement each other pretty well. So what do I mean with this? In general, IMUs being so fast, the nice thing about having low latency and high frequency is that they react very well to your movements. They feel pretty well in the sense that you don't have latency, but they tend to drift very easily as they are proprioceptive measurements. They add up some error over time when you integrate the measurement over time. And so cameras are kind of essential to counteract this, to be able to say, okay, I moved to this way, and be able to see how the external environment changed, and to have a more precise idea of how did you move in reality. So kind of like the idea is to use the IMU for short periods of time and then correct the drift that the IMU accumulates over time with the camera's measurements. This is kind of like an analogy to what we do in like how biology works. Like we have eyes, which will be like our cameras, and we have a vestibular system in our eyes, which kind of works like an IMU. And the thing of doing this, integrating these two sensors, the way or the name of integrating sensors to estimate the pose is called sensor fusion. And there are two main ways of doing sensor fusion. One way is doing Kalman filtering, and the other is nonlinear optimization. Kalman filtering is very good for sensor fusion in general, but there is a paper, a very nice paper that I link in the slide, that has shown that nonlinear optimization has some benefits regarding computational times. And so the research area of visual-inertial tracking has moved towards nonlinear optimization lately, even though there are still some Kalman filtering systems that are pretty good. But in general, nonlinear optimization has been the way to go. Some terminology, SLAM, visual-inertial SLAM, visual-inertial allometry, structure for motion, all of these have some overlap, and it's kind of tricky to pinpoint exactly what we are doing to being just SLAM, because we are not doing just SLAM. In fact, what I will present today is not full SLAM, because we are not doing proper persistent mapping. It's more like visual-inertial allometry, but we also have some SLAM support. So I'll just say visual-inertial tracking in general, and that's the name I will be giving it. Okay, so the internship project. The internship project was basically, we had some trackers in Monado. We still have the PlayStation VR, PlayStation Move, 3 Degrees of Freedom, the T265 for North Star. That's basically the T265 is pretty interesting because it's basically a device, a camera that has two cameras and 9mm inside, and does visual-inertial tracking inside the device. So you just ask for the pose, but you don't have access to the algorithm that is running inside. We also had Lighthouse tracking for the Valve Index and HTC Vive and so on. But in general, we didn't have any kind of inside-out support for all of these new headsets that have been coming, so we couldn't support them. So the plan was relatively simple. We saw that the research field was very active. There were a lot of systems coming, and I mean a lot of systems out there that do SLAM or visual-inertial allometry. And the idea was to, okay, let's just pick one of those and use it. It should be easy. Of course, it wasn't. There are really too many systems out there. And the papers are kind of course, they're kind of biased because, of course, I'm publishing a system. I will highlight the pros of these systems, of the system I did. So yeah, it's kind of difficult to read between lines when you're new to the area. And research software in general can be problematic. The objective of research software is to publish, is to have metrics for your system. And so you run your system on the standard datasets, and that's kind of it. Sometimes your system might not be very well prepared to new devices, new sensors, and so on. So systems can be a bit brittle, and they can take a lot of effort to just get them to build. Kind of like a summary of things I think I ended up looking at, like key points I try to look for in these systems, I think would be these 6. I looked at how many different sensor configurations they supported. Like, did they support 2 cameras and an IMU, 2 cameras only, 1 camera and an IMU, for example, if we want to support phones, just 1 camera or more than 2 cameras, and so on. Like, how many different configurations is supported. The license is pretty important. There is a lot of GPL out there. The problem is that that's not very compatible with what we want from Monado. We would like to have a permissive license to be able to bring code for the system into Monado, or just in general be able to allow the programmer to do whatever they want with it, even sell the system if they want. Active maintainers, that is super important. So yeah, it would be nice to be able to ask to the project and get a response, like if you have some problems. A lot of these systems get done for publishing a paper and then they get abandoned. Of course, like they do a PhD and the life moves on and the systems gets in the dark. Software quality, again, research software quality is important. It's not easy to find. Performance, it should run fast. Like we are aiming to run hopefully these things in like very small, like very constrained devices at some point. And the tracking quality, kind of very important. We want the tracking, of course, to feel good and to be accurate enough. All of this, we ended up integrating 3 systems: Chimera VIO, Orphan 3, and Basalt. Chimera VIO looked pretty nice. It has an permissive license. Tracking ended up being not too good, unfortunately. Up to this day, it's still very unreliable. You can use it with Monado, but it's very unreliable. It's difficult to get sensors working well with it. Orphan 3 is GPL. Wasn't our first choice just because of it being GPL. But it is the state of the art, at least in the sense that SLAM research goes. There is kind of like a standard metrics and standard datasets, and with those metrics and with those datasets, Orphan 3 is top notch. It's like always the best in general, at least in the latest papers that have come out up to this point. We were avoiding it just because of the license, but we basically had a fork of Monado integrate this to just check out how it worked. And indeed, we got some tracking working. It did have some problems that we weren't aware of until we integrated a new system, but it worked pretty well. And if you're interested in Orphan 3, they have, like in the README, you can see that they have commercial options. Like they have commercial options to change the license if you're interested in that. And finally, Basalt, which was kind of like the system we settled on, is developed by the Technical University of Munich. And it works really well. It lacks some features. I basically wasn't, I didn't try it at first, basically because it just supports one sensor configuration, which is stereo and an IMU. But Jacob recommended it to me to try it again. He mentioned the system to me again, and so I gave it a go after integrating Chimera and Orphan 3. And indeed, it was really good. Like, it feels really good, and it's very stable. It has good documentation, good CI, pretty good code quality, doesn't crash as much. Trust me, it doesn't crash as much, even though it seems it does. Things are worse in other places. So yeah, that's kind of like what we have in Monado right now. There were other systems that were considered. Some honorable mentions would be VIO. OpenVins, DM, VIO, Oculus 2, and SVO Pro are kind of like 5 systems that looked pretty good, but we didn't implement for some reason or another. And I'll link to a repository that is kind of recent. I'm trying to put down my thoughts on reasons why I pick or don't pick particular systems in that repository, so you can read that and even contribute to that if you feel like it. Okay, so Basalt was kind of like the clear winner, you can say. There are some metrics in the blog post. I'm linking it a slide about why I choose Basalt in general. But yeah, it's basically, it was a lot faster. Trajectories felt smoother, felt a lot better. There is also another blog post talking about the feeling of the trajectories, which is interesting, which kind of focuses on why Basalt feels better and why that feeling better is not well represented with current SLAM metrics, and how we need to do better metrics for XR. But in general, work pretty well. Vladislav Usenko and Nikolaus Demel, which are the main maintainers of Basalt, were very responsible. Like, we had plenty of discussions on different topics of Basalt, on how to improve it for XR. So I'm super glad that they were so responsible and super thankful to them. And it also has few external dependencies, which is awesome. But it's also listed in the bad parts. So having few external dependencies is super good, but that's so that you get an idea. OpenCV is only used in one call for feature detection. It's the only thing they use OpenCV for in the VIO pipeline. Everything else, optical flow, whatever use image manipulation, everything else is implemented in Basalt, and even the optimization, like the main optimization, like the main factor graph optimization, is also implemented by hand in Basalt. This is kind of unusual. Orphan 3, for example, uses the G2O framework, and Chimera uses the GTSAM framework. Basalt does it by hand. Again, I think this is good because it shows how well they know what they're doing. And it probably has some performance benefits, but it is also something to keep in mind because it's more code to maintain if we want to maintain it eventually. It is not a full real-time SLAM pipeline. you just get Visual-inertial odometry for now, at least in real time. They have a bundle adjustment that integrates the entire map, but it runs only offline, and we need to work on integrating that into the real-time pipeline. But for now, we don't have that, so it tends to drift over time. Like after some time of operation, you will notice that you're in a different position virtually than from where you started physically. It had and still has some problems with non-overlapping cameras, and it only supports one sensor configuration, which is stereo with IMU, compared to Ars 3, for example, which supports a lot of different sensor configurations. Okay, regarding the Basalt pipeline, I will not talk about it. Basically, it is not that. I mean, you probably don't want to hear from me about that, and the paper already does a very good job explaining it. If you just read the introduction, you will get a very good picture about it. It's probably not worth for me to talk about it in this talk. I might talk a bit about it for the demos, but not that much. The Monado architecture, on the other hand, is probably more interesting. Like if you need to implement a new device and try to use or slam stuff. Remember, this is not just Basalt, but any other system we might integrate in the future, or Orphan 3 or Chimera. So the pipeline in Monado looks something like this. We have an OpenXR application that requests a pose at a particular point in time. And on the other hand, we have the physical device that is streaming IMU and camera samples to Monado. So we usually have some kind of hardware interface, like if we are doing low-level stuff, like in the reverse engineering drivers, we will use just lib USB, but we might have like the RealSense SDK if we're using RealSense, or the Depth AI SDK if we're using Depth AI cameras. This goes into the device driver. The device driver usually has a frame server or source of data that can stream IMU and can stream frames. These frames go into what we call the SLAM tracker, which is basically a wrapper that has all the functionality that is generic enough to any SLAM system. This is implemented in Monado. It has things like prediction, filtering, extrapolation, and things like interpolation and things like that, and some debug utilities. So there are some data sinks here that the frame server streams to, and these data sinks redirect the camera and the IMU streams into this SLAM header. This is just a header file, a C++ header file that I designed as I went. So it has some problems. I will talk about them in a moment. But basically, it's just a header file that in Monado we only have the header file, and we have the implementation in a fork of the SLAM system. This implementation is just something that knows how to interact with the entry points and the output points of the SLAM system itself. And then you get the pose back. You usually get a pose for each frame you send, and you just get the pose back. You do some prediction, some IMU integration, because you want to keep using the IMU data, the latest IMU data on top of the latest estimation from the system. And there is also some filtering for smoothing the trajectory, but that's usually disabled because it adds latency, and it's not like it's probably usually not worth it to add filtering on top of that. And then it goes back to the device, to the OpenXR runtime, and eventually it goes to the application, and the application can know where it's located. Okay, let me see. Okay, so I will talk briefly about this. This is the main idea of the SLAM tracker header. Like the main thing that goes here are these three methods, which are basically being able to push an IMU sample, push frames, and then being able to dequeue the estimated poses from the SLAM system. This is what Monado uses internally. And in general, there's none of the forks are restricted to Monado, so technically you could use them. You could use the forks with this header in any other project. The thing that I want to point out is that this re-implementation of being able to recognize the entry points of the different systems, or of being able to recognize the output, where the outputs are, and how to wire them together to get useful interfaces, has been solved so many times from so many different people. Elixir needs to do the same thing, SLAM Bench needs to do the same thing, Gia SLAM needs to do the same thing, and I know at least 3 other people that needed to basically do the same thing as this, which is basically spend weeks just seeing how to get camera images, IMU samples, and how to output poses from the systems. It would be awesome to have a standard for this, and we talked a bit with this. We talked a bit about this with the Elixir consortium, but for me at least, or for Monado at least, it's probably too soon to standardize this. Right now, this interface has some issues like using OpenCV matrix as the frame input and stuff like that. So in general, this interface is still very prototypical, but a standard would be awesome at some point in the future, so that new SLAM systems can implement this standard and be automatically supported in SLAM Bench, Elixir, Monado, etc. Okay, so some drivers are supported. I will probably not go into too much detail because of time, but yeah, the first driver was the RealSense driver, basically the D455 camera. This is kind of like a T265, just it doesn't do a SLAM inside the device. Technically, we should be able to use the T265 and compare our SLAM to the T265 SLAM, but I haven't had the chance yet. Then the first headset I implemented, thanks a lot to Thayton for the reverse engineering work and for helping me with it at the time, was with the Odyssey Plus, in particular for the Windows Mixed Reality driver in general. So right now, any Windows Mixed Reality headset should work with inside-out tracking. Of course, it should be tested and probably some tweaks should be done, but in general, it works. The Rift S, as John Schmidt commented today, Thayton, earlier this morning, yeah, Rift S works now since like less than a month. That driver is integrated into Monado, and today was the first time I saw here in FOSSXR a Rift S working with this SLAM. That was amazing. Valve Index, I recently implemented some partial version of inside-out tracking with Valve Index. It's still not super polished, but it's kind of cool. Like you can now use Valve Index without lighthouses and get tracked, which is pretty cool, I think. And DepthAI, for Northstar, this was implemented by Moses here in FOSSXR. And here on FOSSXR, I also saw for the first time a Northstar running this SLAM, this inside-out tracking, which again was awesome. And finally, there is an EROG driver. For some reason, it's a driver, but it's basically, EROG is a standard dataset format. And it's very useful, like if you're planning to implement a device, you should probably check out the EROG driver to see how to do datasets to test that the samples you have are good enough or will work on our SLAM systems. Okay, now it's show time. Let's see if this works. Okay, so Moses has lent me for a bit their Northstar. So in FOSSXR was the first time I had the opportunity to test this. Let's see if this works. This and this.
You didn't have to restart the demo. You started it before OpenXR started.
Oh, I didn't notice this. Okay, thanks.
Just wait a second. Don't start.
Sorry.
Don't start.
I didn't.
Okay.
I didn't want to.
You have to start the demo app well after you start the demo.
Okay.
That's all.
Okay, cool. Let's put this. Sorry. Okay, cool. And let's like this. Okay. Okay, so yes, it's working. Let's put this on. Okay. Okay, are you seeing everything great? Awesome. So yeah, we are running here the some StereoKit application with the Northstar headset using a DepthAI camera, and this is running Basalt. And as you can see, basically we have positional tracking and rotational tracking, which is everything we want. And I can inspect things, and hand tracking works as well. Of course, the hand tracking Moses presented today. and things are working, and everything is free, permissibly licensed, and running totally open source and in Monado. So I think that's pretty cool. Okay, I guess that's it for the demo. Yes. Yes, oh yeah, I want to show that. Yeah, so let's see the Basalt UI. So what is happening here? Let's see.
Do you want me to put it?
No, it's okay, it's okay. Okay. So do you see? Okay, so here we have the camera streams of these two cameras, and the cameras are basically detecting different points of interest in the 2D images. Those 2D images, that gets done via feature detection, and then those the different features get paired between the two cameras through feature matching, and that feature matching, that detection, you can then triangulate into 3D points that you can see here, hopefully. Oh no. Oh no. Okay, I maybe had needed the mouse. Oh no. Ow. Okay, yeah, there it is. Okay, kind of. Okay. There are some blue points in the 3D view that hopefully you're seeing. Those are the features triangulated into 3D. And with that information, together with the IMU data, everything gets integrated into the bundle adjustment optimization, which is basically a nonlinear optimizer running Levenberg-Marquardt optimizer. That is basically doing everything and estimating the pose finally. As you can see, there are some blue cameras, some blue kind of frames that are in the kind of like letting a trail. So I mentioned Basalt was a VIO pipeline, so it doesn't have permanent information of the map. That means it only keeps a map for the last 7 keyframes it is seeing. So what this means is that, for example, if we are running the, okay, let's see, are we still running? I will run the application again to show you something, which is kind of like one of the problems of Basalt. So now it works pretty well. The problem is that if I like make the cameras, if I block the cameras and move, as you can see, okay, let's see. I'm blocking the cameras, so there are no features. We are drifting because of the IMU stuff. And we're in the same physical spot, but the things have drift. I mean, it's recovering because, okay, it's recovering because I didn't let enough time pass for the keyframes to get lost. But you get kind of like the idea. You drift a bit, and then, okay, I lost it. Like the panels are in other place that they shouldn't be. Okay, you get the idea. That is kind of like the main problem we have with Basalt right now. But in general, it works pretty well. I mean, for the normal way of operation, it works pretty well. And okay, cool. I'll let some videos.
Can you stop?
Oh, okay.
It might, there's a chance that it's not worth it.
Okay, yeah. Okay, I'm being told that there is a memory leak here, so I needed to stop Monado. Okay. So I will let some videos in the slide of other headsets, other devices working, the RealSense camera, Samsung Galaxy Plus, and the Valve Index, if you're interested in those. And okay, how much time do I have left? Okay, cool. Okay, so after seeing the demo, what I want to talk about is more directed towards people that want to use the underlying inside-out tracking for new devices. So I just kind of like give recommendations as stuff to watch out for. So the first recommendation I have for you is to use the UROC recorder and player utilities that are in Monado. UROC, again, is a dataset that can record images and IMU data. So if you're able to record the data of your device and play back the data and the tracking looks good, then you're most of the way, kind of, like into getting a usable system, a usable device with inside-out tracking. So that's kind of like the first step you should be doing. Then things that you need to consider in general are you will need to have calibration data. You will need to have the calibration data. Basically, you have the extrinsics of the sensors, which are the different the poses relative to each other between the IMU and the cameras, and between each camera, and also the intrinsics of each device, of each sensor model. Like you have the different camera models, you will need the parameters for those camera models, and the IMU model, you will need the parameters for that IMU model. There's only support for one type of IMU model, but it's fairly common. I haven't seen any other IMU model out there, so it's will probably work for you. Shutter type. So the shutter of your camera should be global. That means you shouldn't have, like all the pixels should be taken at the same time. Otherwise, you will get like the rolling shutter effect. I didn't put an image, but it's basically when you have some things that are moving very fast, they will get distorted, and that distortion will destroy SLAM for fast movement. So you don't want a rolling shutter in general. Exposure and gain adjustment. So you don't want your images to be overexposed or underexposed. They need to be in the perfect level of the histogram, of the color histogram. If you have the possibility to adjust exposure and the gain of your camera, there is an auto exposure and gain module implemented in Monado that should help with that, and it's being used in the Rift S and the Windows Reality drivers. You might need to tune some tables of values, but it should work. The camera and the AMI frequencies, you should aim probably for 30 FPS to 60 FPS camera for the camera images, and for the IMU, it doesn't matter that much, but we usually use between 200 and 1,000 hertz, at least the drivers that are working right now. Something that is worth mentioning is that Basalt is pretty fast, so it will handle pretty well, like 60 frames per second, and it will improve significantly the tracking at the cost, of course, of more processing power being needed. So the trade-off there, you will need to do it based on the computing power you have and the sensors you have. Unified IMU measurements. So hopefully you don't have an accelerometer and a gyroscope in separate streams. Hopefully they are in the same stream and unified. Otherwise, you will need to do some interpolation there that, because I'm lazy, I ended up not implementing in Monado. It should be easy to implement, but it's not there. So keep an eye on that. Hardware clock synchronization. Yes, you will need all of your clocks to be pretty well synchronized inside the device. The exposure, the 2 frames you get from each camera should have the same timestamp each time, and the clock of that timestamp should be in the same clock as the IMU, as the IMU sample. So you will need a device that has clock synchronization, of course. And another clock synchronization you need is being able to know the offset between the hardware clock and the host computer clock. There are some tools in Monado to help with that, but they are still not perfect, but they're there and they kind of work decently enough. And lastly, or kind of lastly, but more annoying, is our coordinate spaces. There are too many coordinate spaces in a system like this. You have the sensor coordinate spaces, you have the IMU measurement coordinate space, you have the SLAM system coordinate space, you have OpenXR coordinate space. You'll need to deal with that. Oh, and you also have the, oh no, I said that already. Okay, you will have a lot of coordinate spaces, and we are hoping to, basically the idea for the future, right now it doesn't work like this, but the idea for the future is to have sufficient tools to transform all of the drivers, all of the internals of the drivers to OpenXR, and so that we can ensure that the SLAM system gets OpenXR coordinates, like OpenXR formatted coordinate stuff, so that we can also output OpenXR poses. For now, we don't have that, and it's a very manual and tedious process, unfortunately. And lastly, hopefully you have an IMU to ICE transform, because otherwise, it depends on the headset, but for example, for the Valve Index, we don't really have that very well, and like the thing we have is not very precise and it feels off, like because the SLAM systems estimate the pose of the IMU. You will need to be able to correct to your eyes for the view to look okay. Okay, contributions. So some contributions that came out of this, contributions to Basalt in particular, that came out of this work that made things work a bit better, were basically, Windows Functionality had a camera model that is a bit weird. It's similar to OpenCV, but it's not exactly that. And it wasn't supported by Basalt, and so I tried to implement it and upstream it to Basalt. This merge request was opened like for a couple of months, and the reason of this was because it had a very weird problem. So this camera model is not injective, meaning that if you're seeing a 3D point here and you project the 3D point into 2D, you start moving around in 3D. The point moves around in 2D in the camera, but at some point, it falls back into itself. And that means basically this point can be projected like here or here. Like it has more than one point that it can go into. And that's super annoying because that makes some point not work. In the commercial solution, or at least for factory, Windows Functionality calibration data comes with a thing called metric radius, which basically describes the radius in which the model should be injective. But we didn't have this in Basalt, and we also, I mean, it would have been nice to, it would be a good idea to, like, if we're upstreaming this, it should support any other camera that has this model. So something interesting that happened while the merge request was opened was that some people from Kidware released a paper addressing that exact same issue and bringing attention to this issue that hasn't been really discussed before, or at least the paper claimed it hasn't been discussed before. And they solved the issue for a simple model with just 3 parameters. And I was able to grab that paper and extend it to solve the issue for our 8-parameter model. So that was pretty cool. Like, I kind of felt like, oh, I'm doing research. That was pretty cool. Okay, and then the 3 minutes. Okay. Let's see. Oh, 3 minutes. Okay, I will not talk about the next one. Let's just go to the conclusions. Sorry, the second contribution was just basically a better feature, like better features for the right camera. Basalt had some problems with non-overlapping cameras. I just improved that. And okay, conclusions and future work. The nice thing about all of this is that we have now some headsets working in a totally open source stack, getting tracked and working. That is kind of cool. That is very cool, I think. Don't get your hopes too high. There is a lot of work to get closer to commercial solutions. Keep that in mind when you use this, but we have something. My plan right now is to fix the rough edges as soon as I can, like add more documentations, fix crashes, fix usability issues. I've been like delaying these kind of things, but I think it's like enough people are starting to use this so that I should probably focus more on that. So I'll do it. The next thing I want to do is to keep improving Basalt. It has been a very good system as of now, and I think it's a very good baseline to start working on top of, to also understand better the problem. I'm not yet an expert by far of that on SLAM. This is a very big field and kind of complex in some ways. So Basalt is a very nice way to start off from something that works pretty well and start implementing and trying ideas and learning from that. And meanwhile, we will still keep looking for new systems that come out and be prepared for integrating new systems into Monado every now and then that might be worth integrating. Some things that are very cool is that there is an entire pipeline of metrics implemented in Monado right now. You can see the XRT SLAM metrics repository. Basically, we have a pipeline for measuring different aspects of the pipeline, the accuracy, the performance, and stuff like that, which is very useful for implementing, like the 2 features, the 2 contributions I mentioned in the previous slide. I was able to say, okay, yes, these contributions are really improving things, and that helps upstreaming stuff, and that helps like being sure that what you're doing is improving things. Tracking sometimes is a bit subjective how it feels, so it's good to have metrics. But we need more metrics for XR. Like right now we're using metrics that come from like the regular metrics. We need a lot of work to get metrics that are specific for XR, that really represent the feeling of the user, that represent the I don't know, the wobbliness, the ghost effects, like all of these things that we experience when tracking is not working well. We need metrics to represent these issues. We also need datasets. Like the datasets we were using were from the standard datasets, but they don't really represent the XR usage. And we are kind of working on doing datasets with lighthouses specific for VR. That's why the Valve Index now has SLAM. And at some point, I will, once I have those datasets, I will publish them to the community because I think those don't exist, in general. And I think that will be a good contribution. And in the midterm future, I guess there are many things I want to do in Basalt or in the system, in whatever system. Things like handle the dynamic objects, like when you're in your room and things are static, it works pretty well. But as soon as someone enters into the room or you start putting your hands in the cameras, things get crazy, which is annoying. We should really detect dynamic objects and handle them in some way. Synthetic datasets, I think, would be amazing at some point. Even having a tool that integrates SLAM synthetic datasets with hand tracking synthetic datasets could be very useful at some point. I'm thinking at some point also having a joint bundle adjustment with hand tracking, for example, or with having a very big optimizer that does everything. I think would be very useful to have. It's probably a bad idea to have the different tracking things separate. In the sense, at least we would get a lot more information and a lot better accuracy if we integrated all of the tracking in some good way that was modular enough. And online calibration would be amazing. Right now, calibration is tricky. You need to rely on the vendor providing the calibration data, or you're out of luck and you need to calibrate yourself, which is annoying. Even though Basalt has a nice calibration tool, but it's still annoying. The last word is that the infrastructure is there, I think. We have the entire pipeline. We just need to keep iterating on it and keep improving on it and getting the tracking to be better. And that's it. Thank you. Oh, and we are hiring, of course.
Thank you, Mateo. Pretty impressive work. We have time for one question. Who wants to? Right here in the audience.
Hi, I'm Moses. I'm the hand tracking person. For people watching at home, so you said the joint hand tracking optimizer. One question: are there how many different optimization things are you doing in SLAM, and how often do you run them? Once per frame, once per IMU sample?
One per frame, yes. One per frame, and the IMU stuff gets pre-integrated for each frame.
Okay, thanks.
Okay.
That was a short one. We have time for another one. And let me check on the channel. Okay, there's one here from Ryan, and we'll wrap this up.
So when you were showing off how it kind of loses track and drifts because it doesn't keep very many keyframes, is it doing sort of a form of loop closure in sort of those past 7 keyframes, or does it not really have a concept of loop closure?
It doesn't have a concept of loop closure, but what happens is that having those 7 keyframes gives you a map, so you can, if you are still seeing the same points of that map, you can be aware and be able to place back, but as soon as the last keyframes go away, you lose that map and you won't get that nice going back again.
So there was no information, it just went back.
All right. Thank you so much, everyone. I invite you, if you have more questions, to ask online or physically. I mean, we've got Mateo here in Minneapolis, so thank you again for all of your very good work and today. So take care, and we'll catch up later. All right. Thank you.
That's awesome. You did great.
Thanks.
That was.
live. So I'm presenting Godot Engine. We've seen today a number of amazing demos today and yesterday with like hardware stacks and firmware and really cool like tech for driving these headsets and tracking devices. But how do we make content for XR? So I'm here to present a fully open source stack for building the XR content that we're going to be using on these devices. So yeah, what is Godot? Godot is a game engine. So as opposed to StereoKit, which is aiming to provide a really simple, easy to use code infrastructure, this is trying to provide the full like game engine environment to build a game and all the content you'll need. So it's got your node tree, it's got inspector, it's got a scene. So it's a 15-year-old game engine. It's been in development for a long time now. It's kind of starting to reach that level of maturity that it can compete with Unreal, Unity, and GameMaker. So the Godot development community is fully open source. All the development happens in open. There's GitHub used for issues and pull requests, and actually a separate GitHub repository for Godot proposals. And that way you can sort of create issues on things that don't exist yet and propose new features. And using the system, basically any PR that comes in, you can say like either it's fixing a bug or it's addressing a proposal and implementing it in some way. And that makes it really easy to review stuff and keep the code base clean of bloat. And weekly meetings to make sure that the PRs coming in are actually what the engine wants and the direction it's trying to go in. So for things that don't make it into engine core, there's asset library where you can publish your own assets in GD extension and other ways of hooking code in. Of course, it's open source. So active Discord, lots of community help for people who want to play around with the engine. And a lot of developers are active there as well. And of course, Rocket Chat and Jitsi, which is like the core development if you want to get more engaged into the engine core. And according to a recent game jam, it was the fastest growing game engine. So a lot of momentum behind it. So Godot, it has the 4.0 version comes with a Vulkan native renderer, which can of course run on Mac with Molten VK. It's got a Direct3D 12 implementation of their rendering device API in PR currently. Wayland supports in PR. It's got really good USB, Unicode, harf buzz, right to left. It can do emojis. It can do pretty much all the Unicode stuff you'd expect from a modern system. And it has MSDF text, so it can actually have pretty crisp font rendering in a lot of different scales. It also has compatibility for non-Vulkan devices. It can run with WebGL2 and OpenGL ES3 and WebXR. Though caveat that WebGL2 and WebXR are still, this is all still in development currently. Godot 4 is in beta, I didn't mention that. Not released yet, but hopefully soon. And yes, it supports BSD. Okay, yeah, this is from their homepage. So Godot provides tools, provides import, it provides resources for, which are like data. So anything that's data, for example, you got scripts, meshes, textures, these are all different types of resources. Separately, there's a node tree. So the entire, as opposed to an engine like Unity, which has basically scenes that contain game objects and components, Godot is actually a really simple architecture. Everything's nodes. So it's just a big tree of nodes. You can serialize those trees of nodes into a pack scene resource that gets saved out. It's called a T-scene if you ever use Godot. And the other thing the engine provides, of course, is exporting builds to a variety of different platforms, including Android, iOS, web, and various PC. So yeah, scripting language. One thing that's potentially unusual is it actually created its own scripting language. It looks a bit like Python, but it has its own built-in script editor, and you can basically type out scripting code within the engine. It has a lot of features in the scripting language to make it easier to integrate with the engine. So on top of that, you can also build extensions. You can write C++ code. You can compile C++ code into the engine or separately as a shared library. You can also, of course, modify the engine code. It's all MIT. Just go mess with the engine if you want. It has C# natively, .NET 6. in Godot 4. Godot comes with a 2D engine. You can use it to make GUI apps. It's a full UI toolkit built in. Here's an example of Material Maker, which is a application kind of like Substance Designer. You can go and make shader-based materials, and this was all made entirely in Godot. 3D engine, it comes with its own physics, both for 2D and 3D. Again, it's the 3D is based on, in 4.0, based on the rendering device API, so it has a really strong foundation. You can actually go and directly run essentially equivalents of Vulkan commands, but they'll be ported to the native layer on each device you're running this on. For example, running compute shaders. It has skeletons, 3D scene graphs, and of course OpenXR, which I'll get to in a bit. So yeah, content is probably the most important thing in a game. So Godot has a very big resource importer system. Again, it can handle audio, like many different audio formats, images, many different formats. You can basically just drag these into the project, video, text files if you want. And of course, you can import like raw OBJ meshes. On top of that, if you want more complex content, like you can import a GLTF file. So GLTF is we've heard about it a few times already. It's a standard that has basically permeated the industry at this point. It's finally the open content sharing ecosystem we've all waited for a long time, replacing the likes of Collada, which was annoying to use. And it means we don't have to use FBX and all the stupidity that FBX comes with, like proprietary SDKs and buggy importers and exporters. So GLTF supported in Blender, of course Godot. It's a standard now, finally. So it's an ISO standard, which means more industry people are hopefully going to adopt it. And Unity is developing their own first-party importer. And it's a growing, thriving ecosystem. And it comes with PBR, so you can finally, unlike FBX, where you'd often have broken materials when you imported stuff, you can import a GLTF file and it'll look pretty realistic. I just put an example of it. You can't really read that in the projector, but it's a GLTF file, like the entire JSON for the GLTF file there. It's pretty readable. You can open it in a text file. It comes with a binary file for the blobs, like the mesh data. So yeah, Godot, of course, you can import GLTF. It'll import all the stuff that GLTF has you import. Godot has an armature system, so when you have GLTF, it's just nodes. But when you import into GLTF, it'll actually create a skeleton, very similar to how Blender has armatures. And in fact, if you export a file from Blender with armature, as of Blender 3.2, it will properly preserve the exact armature when you import it into Godot again, which is nice. It also has an exporter, so you can take content in Godot and you can actually export it back into GLTF, and I'll show an example of that in a bit. You can write custom plugins with GLTF with DOM access as well. So yeah, GLTF in Blender. Blender's been rapidly improving its GLTF support, and they've had a lot of really good bug fixes in 3.2 and beyond. Godot, so GLTF has usually 3 different options when you export it. There's one called GLTF binary, there's one called GLTF embedded, and there's one called GLTF separate. GLTF binary is all one big document that's called GLB. It's got basically like a length followed by JSON and another length followed by binary data. And it's great for just packaging up your 3D scenes in one nice file. You can ship that around the internet. The issue with that, of course, is it's all in one file, and if you want to go and mess with textures, it's a little bit hard to do that. So Godot actually recommends using GLTF separate, which is using a separated GLTF JSON, the binary, and then all the image textures, and you can then change the import settings in each one. All right, so a new feature in Godot 4, which is really fun, is called animation retargeting. You can actually import a model import a GLTF document as a model or as an animation library. And that goes for all the formats, including FBX or other formats that have armatures. So it has a built-in support for humanoid models. If you've ever used Unity, it's very similar to Unity's humanoid importer, but Godot also allows making custom profiles. So you could actually make like a animal or monster and then make animations for various types of animals and monsters that are all compatible with each other. And you can download animations from Mixamo with a little asterisk that Mixamo has a bug right now with the way FBX files are converted to GLTF. We'll try to work on that. You could recommend to go through Blender if you use an FBX for now. And yeah, you can build animation trees. So animation retargeting is a lot of fun. You can basically take an animation and play it on all your characters, and they'll all do the same thing. So it's... Oh. I guess I'll have to play this one more time. So GLTF is extensible. So one of the really cool features about GLTF is it's JSON, easy to read, but also it has an official extension system. And on Chronos GitHub, you can actually go and submit PRs with extensions, and you can see lots of vendor extensions that have already been approved. And basically, it provides a sort of framework where you can come up with new ideas for what to do in GLTF. And I'll get to a few of those in a bit. So Godot implements an API to allow you to customize the import and export process. In addition, Blender, GLTF Blender IO also supports this, and there's some command line tools like GLTF Transform that also have a way to extend with extensions. So one of the groups working on building extensions for metaverse applications is Open Metaverse Interoperability Group, and they have a working group that meets weekly right during this talk. It just happened. You can come in a week or something and check it out. But they basically develop, right now they're working on audio, some physics collider extensions, but there's still many other extensions up in the air that would be awesome to have for metaverse applications. VRM is an extension you're probably going to be hearing in more and more in various like social VR metaverse type applications. It's a interoperable standard for avatars. So whereas you can actually import GLTF files that have armatures in them, VRM standardizes the humanoid rigging. So it has a standard way of specifying this is the head, this is the leg, this is the arm, and so on. It has physics bones built in called spring bones. It has, the new version of VRM has constraints. So you can actually do things like define one joint to rotate half of another joint, or there's cool things you can do with that. It has a built-in toon shading, so you aren't forced to use only PBR. A lot of people like cartoon characters or anime style. You can use toon shading as part of the mtoon shader that comes with it. And it comes with built-in support for various mappings from like happy, sad, like different vowels into different blend shapes so that you can have all the characters speak and not have to like write custom code for each one. And it's got plugins in a lot of engines, Blender, Unity, Godot. So the Godot VRM add-on is still work in development. The VRM just released a 1.0 version. Godot's does not support that yet, but we're working on it. Yeah. Here's an example of the spring bones. They're a lot of fun. And you can see that it's hard. You can't really see in the projector, but you can play the different morph shapes for the mouth. So yeah. Another project that's kind of separate from GLTF, but a project that we've been working on in vSakai is, I'll get to what vSakai is later. It's a Unidot importer. So basically this allows you to take a Unity package and import it into Godot. And it'll go and like parse all the YAML and figure out, it also supports like nested scenes and prefabs. It'll convert them all into Godot T scenes. So you can then play around with it in an open ecosystem. And one of the fun things you can do with, oh yeah, I'll show this. So like you can go onto a store, like this is booth.pm. A lot of people sell Unity content there, sometimes for VR chat or other social VR platforms. And you can go and save the Unity package, go and import it with Unidot. Here you go. It's in Godot now. So of course, it's not perfect. There's a lot of issues still. It's a complicated thing. But the fact that I can get it to looking okay from the original, it's possible to actually import content. Whereas otherwise you just end up with like a bazillion FBX files everywhere and like no way to position things. A lot of times these creators will just like position things manually in Unity, and if you just were to take the raw like files and try to get them in Godot, you have no chance of getting things in the right place again. So this kind of solves that part of the problem. FBX to GLTF, I mentioned Godot does support FBX, even though FBX is a terrible format. The way it's doing it now in Godot 4 is by using this very beautiful program written by Facebook back when it was called Facebook. And they did all this hard work, and basically it's a single command line program. You stick an FBX file in, and out comes a nice, beautiful, interoperable GLTF that you can then use wherever you want. Godot will run this for you, so when you put an FBX in, it'll just create a GLTF in version 4 at least. Yeah, so it's very cool. Finally, the part we're all excited about, OpenXR. It's a wonderful standard, and it's actually integrated into the engine core. So no more like installing a plugin just to get XR to work. You just open Godot, and you can just use XR with OpenXR. So it's really great. Of course, it uses, for Android, it uses the OpenXR loader. And if you're on Quest, and hopefully someday Meta will fix this, but for now you need like some .aar blobs copied into certain places in your project to get it to work on Quest. Someday that'll get fixed, hopefully. And then there's a weird thing. Khronos makes Vulkan. They also make OpenXR, but when you use both together, they didn't think very much about how that's supposed to work. So you have to initialize Vulkan with OpenXR, which means you can't like toggle it on and off dynamically. Like if you use any other graphics environment, it actually is much easier to use. But it's hopefully they'll address this someday. But for now, you have to like run Godot with a command line option to like force XR on or off. Anyway, it's a caveat. If anyone knows how to fix that, that'd be awesome. But, so yeah, to enable XR at Godot 4, I'll show a demo in a moment. If there's time, how much time?
Yeah.
Like, how much? 15. Okay. I think we'll have time. So yeah, I create an XR origin, camera, and controller nodes. You have to go enable it in the project settings, and then in script to actually turn on XR, you say get viewport.x use XR equals true. I'll show a demo of doing that in a moment. So tons of add-ons that we're working on in the community. Visual-inertial is kind of this development community that trying to make all the tools you need to build social VR infrastructure on top of Godot Engine. All the stuff we make is MIT license, and we have some add-ons for like VoIP. We have integrated code for HRTF as a engine patch right now. It's unclear if that'll get fixed by Godot 4, but 4.0, maybe it'd be closer to 4.1. You might need to patch the engine to get HRTF working reliably, but that's an option. We have a lasso system built by Melon, who it basically lets you like grab objects that are far away and sort of bring them towards you. It has like a snapping pointer thing. I didn't have time to put a video in here, but some other add-ons as well. Visual-inertial, the goal of this project is to build a fully MIT licensed social VR stack on Godot, and all our code's on our GitHub, Visual-inertial. There was some code that wasn't open source. It's now all open source. Let's see. So yeah, I've already mentioned a lot of the stuff it has. But yeah, basically it's trying to fill this void of what people currently use Unity to make VR content for. It's like Unity makes this nice environment to build demos, and a lot of people use it for that. And then of course, a lot of social VR platforms that are built on Unity. We're trying to make sure that you can do this in a fully open source ecosystem. So future, Blender has seen an amazing trajectory in its 20 plus years of being alive. Godot has been alive for 15 years, and I really hope it's going to start following this trajectory. So I think it's not quite there yet, but I think 5 years down the line, I think there's a good chance it'll start to be something people converge on as far as these monolithic engine designs. And Godot has a ARM, not really an ARM, but people working in Godot also work at a company called W4 Games. They provide sort of the commercial aspect of maintaining Godot projects, and that should allow for better console support as well as some of these proprietary APIs. But Godot itself is always going to be free and open source software. And finally, Godot 4.0 doesn't have very good WebXR support because of this whole like OpenGL, WebGL2 conundrum. Soon, WebGPU is going to be everywhere. I think that's probably 1 or 2 years down the line, but once that happens, it should be really well supported on Godot. So that's kind of the goal. There's also, of course, other very good platforms made for web, 3JS-based stuff. Hopefully, Godot will be a contender in that space as well once WebGPU gets more stabilized. And, well, I have that there, but I actually wanted to do some demos. So let's see if I can get some demos to work. OK. Let's see what I got. So there we go. All right, so I'm going to try showing how to make a project in Godot. We're going to get this project to do XR, hopefully in a few minutes. We'll see if this works. So I'm going to create a new project, create folder first, then create an edit. See, the engine starts relatively quickly. Maybe. All right, so yeah, what do you need to make a simple like demo for XR? Well, you need a player. So let's go create a player. So I'm going to do here another node. There's a node called character, character body 3D, and that's what sort of uses the basis for a controllable character. I'm going to create a character body. I'm going to go and you have to add a collision shape. So this is how it does physics interaction. So you always, there's a little warning that tells you that as well. So you need a collision shape. I'm going to go assign a capsule. It's usually used for players. Capsule shape. We're going to set the size. That doesn't really matter. Just set it to 0.25 radius and 1.5 height. Set the Y to half the height, 0.75. There we go. We're going to add a little mesh instance with, what do we put here? Prism, maybe? Okay. It's our little player object. You won't really see it anyway because it'll be first person, but you know, something. Move it back a little bit so it doesn't block the view. And then let's go add a XR origin. So we're going to, so usually, at least the way I've done it is you put the XR origin actually in the player. It's actually telling you here that you need an XR camera as a child. So we're going to add an XR camera. So this is sort of the plate tracking space. And then you add the camera and you can add, that's not what I meant to do. You can add the controllers. Let's add one for the left hand. And we'll just name it left hand here. Let's make this a bit bigger. And we'll add one more for the right hand. And we'll name this one right hand. Okay. And then we'll add a mesh inside each one. And let's make this one like a cylinder. It's uneven, like an uneven cylinder. So let's do like 0.05, 0.025. If all goes well, those will be the hands. Make the height smaller as well. And I'll just go copy that, paste it here. So we got one for each hand. Also, the other thing is to play in, it's good to have the default position for the camera to be reasonable for when you play not in VR. All right, so we'll save this. This is our player. And the next thing we're going to do is go to the character body, and we're going to add a script. So let's make a new script. We'll call this player, the default. It gives you a nice template for movement. So we're going to go and use that. And because we're a little time constrained, instead of typing this out, I'm going to copy some code that I already wrote. It's a few lines. So what this code does is exports a variable in radians. That's rotation speed. This is like how fast you're going to rotate with the mouse. This is just so you can like test it. It makes it useful. We're also going to export the camera node, and this allows you to do mouse movements, so you can test it a little more easily. And then the other thing this function does is it has a ready function, printing something, and then basically if the OpenXR runtime is initialized, we're going to set use XR to true in the viewport, the line of code I mentioned earlier. So I'm going to save that. And now we're going to create another new scene. This is going to be our world. So this one's going to be really simple. We're just going to make a plane. So let's do a mesh as a plane mesh. And we're going to create a static body. So static is to create a, so it's That's to create like static colliders. This is so you don't fall through the world. And the shape, we're going to make this a box shape. Let's make it like 20 meters x and 20 meters z. Y is up, so we're going to move it down by 0.5 meters negative. All right, so here we go. We've got our world. Let's add an environment to it. Otherwise, it'll all be gray. So world environment is how you specify the skybox. Let's make a new environment. Background, mode sky. Sky, there's a lot of clicking for this, unfortunately. Hopefully it'll get easier someday. So go to sky, then make a new procedural sky material. And then last thing we want is a directional light. So we have some light source. So add a directional light. It'll be easier if I show you what's going on. So we'll move the directional light a little bit like that. Okay. And then let's add some objects. We have some reference point. Let's add like a cube. New box mesh. We'll just stick it up in the sky. Let's make this thing a little, this is the ground. Let's make it a little bigger. 20, 20. All right. So save this. This will be our world. And then finally, let's make a scene for our game. So new scene. Again, make it a 3D scene. Let's put our player in. Whoop. Let's put our world in. Whoop. Maybe let's move our player a little bit so it's not the same point as the box. All right. And there was a warning I missed. If you went here, if you're astute, you notice there's a warning here. This warning is telling us that we forgot to enable XR to project settings. So let's do that. Project settings, XR. We will turn on OpenXR and make sure also to turn on the shaders. You have to turn on both. If you turn on only one, it just won't work. So a little bit of a caveat there. So we'll do that. And let's see what happens. And select the, yeah, this is the game scene. Select this as our main scene. So we'll see what happens. Let's see if I can get the, taking a little bit of time to start up, so I don't know. Well, it's definitely not. That's true, but actually when you hit play, it starts in a separate process, so I usually ignore that. It doesn't need to be restarted. It seems like it's, oh, it broke on a breakpoint. Look at that. Trying to follow a function. Oh, I know why. It's because I didn't assign the camera. So we go open the scene again. We're going to go to our script. Remember, I put a variable. I didn't show it very clearly, but I typed export var camera : XR camera 3D. The exported variables have to be assigned in the inspector, but I didn't do that. So let's assign the camera. There it is. So our script knows where the camera is. You could also hard code a node path, and some people do that, but I chose to make it a variable. Let's try it again. Yeah, we have to check when it's broken. Let's see, is it using VR? I don't think it's using VR. Headset's off.
No, it is. There we go. Yep.
There we go. Yeah. And let's see if it, I've got controllers, that's why. There we go. Yay, wow. VR.
All right.
And if I'm crazy, I can go on the Steam Deck and use the joystick to walk around, I think. Maybe. Oh, am I not? Let's try using the arrow keys. Oh yeah, there we go. I can also just run around with the arrow. And then this, but I did make a mistake in this code. I didn't offset the XR origin by the XR camera's position. So what you want to do is, it'll take a little more code to do that. You want to make sure to recenter the XR origin so that you don't rotate around the play space origin, which I'm just doing here. So yeah, not a perfect demo, but anyway. How much time do I have? Can I show?
I'd say just wrap it up.
Okay, I do want to show a little video. It's like 20 seconds.
Cool.
Let's see, where is this? Let me close this so I don't run out of memory. This thing does not like running out of memory. Stop. Okay. I should have a video in the home folder somewhere. Oh dear. Oh dear, oh dear. Where is this thing? There it is. So this is a project that I've been working on. This video is actually 2 years old. This was made with OpenGL version of Godot, Godot 3. But this is kind of what we're trying to make. So it's a fully open source, interactive network social VR platform with custom content, custom avatars. So yeah, that's what we're trying to do. And yeah, I'll just leave this playing while this is, games. This one's a bit more fun. They just released new showcase videos today. This is new games that are just made with Godot 3 this year. But yeah. I guess, yeah, questions, or is there time?
Thank you very much. We'll take one question maybe from the audience here. Who shall ask a question? You want to ask a question, Moses?
This one might be too esoteric, but the RenIK library, do you know how much it depends on Godot's core or external dependencies? How easy would it be to like pull out of Godot and stick it in a StereoKit app, for example?
Ooh, good question. I would say it probably depends more than it should be. It's always this problem with the math libraries. So it probably is using Godot transforms and stuff. But Melon, who's actually the developer who created the RenIK library, is pretty active. I could get in touch with them, and we could probably, I think it's doable. There's another library, which is the EWBIK, which might also be interesting. It's the Everything Will BIK. That's also an interesting one. They actually already sort of isolated out the Godot math libraries because apparently there's two types of quaternions, and the original developer uses the other type of quaternion. So that one might be a little easier to sort of extract. But yeah, it's totally doable. I'd love to get in touch about that. Join our Discord. You did.
Thank you, Patrick. That was really impressive demonstration of Godot. So big shout out to you. And thanks.
Thank you, everybody. Thanks for staying for the last talk. I'm going to be talking about a tool for virtual reality called ParaView. Actually, the tool is for scientific visualization, which we're in the process of adopting to virtual reality. And it's an open source tool, so it fits with the conference. I also extended my talk to include a couple of other little topics at the end there. Just a little bit about myself. I've been doing VR for 31 years and computer graphics for another 6 years on top of that. I have a master's degree from the University of Illinois in computer science. And at the bottom, you'll see I'm also in the process of getting my PhD some 30 years later. I work presently for the US government, the National Institute of Standards and Technology. So we participate in like the OpenXR and other standards efforts. Really like open source software. Before that, I worked at mostly academic places. So I worked at Indiana University, the Desert Research Institute, which is kind of a part, it's kind of a sister institute to the University of Nevada in Reno. And before that, the National Center for Supercomputing Applications at the University of Illinois. I've been teaching VR off and on for about 20 some years, about 10 times because I don't teach it every year. I've authored or co-authored 4 books on VR. And I have my own VR effort, that open source library that I've been developing for about 24 years. A little bit about our group at NIST. It's the High Performance Computing and Visualization Group. So we're really focused on getting science into computer graphics. Usually our group aims for virtual reality if it makes sense. We don't, we're not married to virtual reality, but if it makes sense, we like to do it. And so we like to also, like I said, we're a standards organization. We like to promote standards and especially open standards. So we participate in Inari, which I'll mention towards the end of the talk, OpenXR, of course, and then ParaView is an open source tool that we are promoting. So we're doing our work on ParaView with a company called Kitware. They are the maintainers of ParaView, right, and VTK, which ParaView is built on. In particular, we've been working with Scott Wittenberg, Corey Quammen, and Ken Martin on our current effort. And then like 10 years ago when this project began, we were working with Ashish and Nikhil. So one of the things we like about virtual reality is it lets us combine the physical immersion where you can actually walk around, see things in first person, interact with things in 3 dimensions with the ability to visualize your data. And so we feel like putting those things together, it's even better. A quick kind of definition of immersive, what we call immersive visualization, is just taking scientific visualization techniques to an immersive interface. And in other words, for another word or phrase for an immersive interface of virtual reality, or now extended reality. Right? One of the things that people question, right, how does VR benefit your use of that interface for science? And so there have been studies done in the past that have kind of experimentally determined that VR does in fact improve some tasks in visualization, including one chapter that's written in this book here, which I'm the editor of. And then we have a lot of anecdotal things, right? And so you might think of anecdotal meaning it's not very scientific, but if you kind of flip it, it is a proof, it's a negative proof of a negative, right? So you can't say that immersion doesn't help scientific visualization if there's at least one example that proves that wrong, and there are several examples, including a few here, which I document elsewhere. So the other motivation then is we wanted to make a tool that wasn't just for our lab, right? Actually, this effort started when I was working for Indiana University, and we didn't want it to just be for us. We want to be lots of people. We want community, right? Which is how a lot of open source things work. So we wanted to build off of open source software. And so we chose ParaView and the VTK platform on which it's built as our source. And for a little history of VTK and ParaView, VTK was started in 1993 by some researchers at General Electric in the medical visualization group. And they wrote a book and then actually formed their own company called Kitware a few years later. And then a little bit after that, VTK was just code, right? So you wrote C++ and you accessed the VTK API. And back then, I think they also had a Tickle API for it. And so it was basically a code-based thing. So it wasn't really for people who want to just do desktop visualization. So a few of the national labs got together and teamed up with Kitware and wrote a tool called ParaView The para portion of that means it's parallel, so you can do parallel rendering on big machines because a lot of the national labs have very big computers. This started 22 years ago, and then it was actually released only about 15 years ago, but it has a really wide user base. On the history, on the VR side of things, people have been trying to get VTK to work well in VR since 1997, and I've just documented a handful of independent efforts with varying degrees of success, right? And then the same for ParaView. So I mentioned about 10 or 11 years ago, we started a project when I was in Indiana University, teamed up with Idaho National Lab. We worked on that for a couple of years. The money dried up. We stopped working on it. My current organization learned about it a few years ago and said, hey, we want to do that. And so that's where I ended up, and that's what we're working on. There's also another effort that someone else was paying kitware to do a head-mounted display-based thing, because in the interim, of course, head-mounted displays became a consumer product that was easily usable. So Ken Martin started some work on that. So you can interface all this, you can interface the head-mounted display stuff with VTK, and then because it's in VTK and ParaView is built on it, you can also do ParaView. So there are now two independent ways you can do VR with ParaView. One is what we call this cave interaction system, which is what I was demonstrating upstairs. The other is the XR interface, formerly known as the OpenVR interface. It actually started as OpenVR/Oculus. The Oculus thing went away, and then NIST, as a standards institute, we said, how about you add OpenXR to that? So we paid them to do that. So now it has OpenXR in addition to OpenVR, and here's some code. So this is Python code, because they switched from Tcl to Python because that's the way the world went. And basically everything they had done for OpenVR, they just made a class level, made it work for OpenXR. And so these highlighted lines of code are the only bits in this Python that are really OpenXR related. Everything else is create shapes, turn your data into meshes, things like that. So these 4 lines basically take your Python script and make it work in OpenXR. There's a little panel that's on the side of ParaView, and it includes the option of doing either OpenXR or OpenVR if you still prefer. The OpenVR one actually has the models of the controllers in it. The OpenXR one just has these little triangles in it. So still working on improving that. So you can choose which one you want, whichever runtime you have running. If you have used it in the past, we renamed it to XR interface because it was a little unclear, especially once we switched to OpenXR. If you kind of understand some of the way desktop software works, the way this is implemented is it basically duplicates the world that you see on your desktop. So your desktop still exists, the world gets copied over to the XR. That has an influence on the fact that ParaView sometimes has time-based stuff, and the time stuff has to be copied over every time. So it's a little clunky that way. It works on Linux and Windows. You can use SteamVR on either of those, kind of on Linux, if you can get SteamVR to run on Linux, which we have done in the past. We run it with Monado, though. It works with Monado, so using the Monado open source runtime, OpenXR runtime, sorry. And then there's also a collaborative interface. So somewhere on this, I don't know if, does my mouse work up there? Yeah. There's a little collaboration section here where you can go to an MQTT server and just connect with people, and then you have simple avatars that you can point at certain data and talk to people over the server. Here's a little picture of what it looks like. This is OpenX. Oh, I was pointing up thinking you were seeing this slide, but you weren't. So there's the controllers that I mentioned in the last thing from the OpenVR version. So this is running OpenVR. On the Cave side, it creates several windows, several processes that are rendering for each of your screens. Typically, a Cave has 2 or 3, 4, up to maybe 6 sides. Upstairs, I just have 1 side. So in the spirit of ParaView, being parallel, it renders all those in different threads. It used to be called the VR plugin because that was the only plugin that did VR. That became confusing when people started using head-mounted displays with it, so it's been renamed the Cave Interaction plugin. It works on tiled screens as well. There's a special format for laying out how the screens work. And really, ParaView kind of separately does the screens versus the Cave Interaction. Right. So one of the differences between this and the VTK version is that because it's doing parallel rendering, when you're doing time-based things, everything is doing it at the same time. So the time data works a lot better in the cave interaction. We're hoping to kind of improve it on the other side, on the head-mounted display side, but right now for time-based things, the cave interface works a little better. And again, works on Linux and Windows. So just a little kind of some of the features that we have. This, like I said, we started the project 10, 11 years ago. It kind of lay dormant for a while, so we've been reconstructing things. We actually discovered that stereo had broken in ParaView in the interim, so we had to have that fixed. There's some issues with GPU rendering where it doesn't work quite well. GPU rendering for the desktop, it does, here's your perspective, but in VR, when you start walking around it, you still see this kind of flat plane over here, which is not, of course, what you want. So we're working on that. We have a thing where we're doing multiple coordinate systems. So you have your head coordinate system, you have your world coordinate system, you have the controllers. ParaView wasn't designed for that, or VTK wasn't really designed for that, so we've had that added in. Then the Python interface is kind of one of the big things where we want to be able to make it so that anybody who starts it up can kind of do little scripts and get things running, much like a lot of other software has done. And we want to make it interoperable with especially the collaboration feature for the XR thing. As kind of a small update, the Python interface is mostly working. We're not releasing it yet, though, because we're tweaking it a little bit. The coordinate system stuff is almost working. We have to do some debugging. But here's the Python interaction style. So this little portion in the lower left here, or the lower left of the screenshot, is the VR interface. And you can create new interactions, which I'll show an example of in a moment. In the past, what we've done is we've written a little C++ code to, say, do the tracking, C++ code to do the grabbing and moving things around, and then you build that into the plugin. It's all plugins, so you can load them on the fly, but you build the plugin prior, so you have to do your C++ coding and do some compiling. We're working on we're still figuring out how we want to name the variables for this. I'll talk about that in a moment. So there's where the Python code is in this example here. And here's kind of a blow up. You can also click and edit the Python code in a separate window. So here's the Python code for doing tracking, right, including a debugging print statement. So basically you want to know, am I the head sensor, in this case sensor 0? If so, I want to know where the view is, take my tracking data and put it into the view and then render, right? Basically that's the Python code for that. The code for doing the grabbing, which is what I'm running upstairs, is a little more complicated, but it's only, 25 lines of code here. So there's a thing where whenever you click the button to say I want to grab it, what's my wand matrix at that moment, right? And then every future moment in time when I'm still holding the button, here's the original matrix, here's my new matrix, and I just do some matrix math and figure out where the object should be. And then on the button side, there's a little separate thing for when do I push the button. And for those of you who didn't get to see the demo live, and here's actually with time moving. So this is some climate data from one of our clients that we're working with over the Baltimore, Chesapeake Bay, Washington, D.C. area. The purple stuff is carbon dioxide in the atmosphere. The darker isosurface is kind of where there's more wind turbulence, and then there's a couple of layers where we're showing the airflow with those arrows. So that's kind of what it looks like. So this is with a camera. The camera's being tracked as the head, right? Oops. And here's another example of some data where we're actually studying some medical devices where you put like a transmitter and a receiver on each side of the body, and you're trying to measure the fluids in the lungs. So you can see the streamlines, those blue streamlines are kind of showing that data. And this one, I'm showing the grabbing as well. All right, so I mentioned I'd talk a little bit about Inari. So Inari is another open standard. It's not necessarily open source, but there are open source implementations of it. It's basically for doing better rendering. We're showing science here, but it's not necessarily limited to science. That's just what we do. It's a high-level API. You describe objects in the scene, and you say render and give me an image back, basically, right? So much like we have the same chart for OpenXR, right? It used to be you had to write this for that and this for that, and now you write it to this one API, and you can render it on any computer. Here's three applications. So ParaView is going to use it. Visit, which is another visualization tool. VMD, which is a molecular visualization tool, are all using it. Again, in my career, I'm kind of science focused, so that's what we do. It's a Kronos effort, so it's on the Kronos webpage. And we're still in a provisional spec. It's not the official 1.0 spec yet, and we're hoping to get there next year. I've also ported Inari to VR. Of course, I started with the Cave. And so Inari, one of the nice things about Inari is it has some ray tracing built, backends already existing. So if you want to do some fast ray tracing in VR, it's a good way to get that done. But it doesn't really render to the OpenGL or Vulkan context, right? It renders to a frame buffer. So you have to then take the frame buffer and somehow get it into VR. In this kind of little example, basically what I do is I render to a texture map, and then I render assuming the head is in the middle, and then I move that texture around when the head moves around, which is what those images are kind of showing. Here's my colleague Simon in the Cave on the bottom picture, and then the top picture is it running in head-mount display using Elixir. So I also wrote an Elixir plugin to run Inari as well. All right, so one of the issues, so for those of you who aren't familiar with Cave rendering, is when you normally look at a desktop, you're sitting in the center. If you do stereo, it figures your eyes are kind of looking like this. If you're in a cave or if you're see the screen upstairs, if I walk to one side, the thing is still rendering for over here unless I tell it I want to render out like this. But if I'm not staring at the center, we call that off-axis perspective. In the old days, a lot of graphics libraries didn't consider that as an option, and so you're kind of stuck. It didn't really work very well. So one of the things we had to add to VTK and thus ParaView was this ability to render on the side. And so Inari kind of has that ability. At the moment, though, I'm just kind of cheating and rendering right down the center and just moving the picture around. So that's a quick overview of Inari. I want to talk about my little display upstairs. There'll also be some videos for those of you who aren't here in person. I called it portable VR. Ryan said it's more like transportable VR, right? Because you have to move all the equipment and then you have to set it up. It takes about an hour and a half to do. It's actually part of a series of efforts. So this is another thing I started maybe 12, 13 years ago. One of the ironic things I feel like is that it's not cheap, right? We're talking $9,000. It used to be that the tracking, which in this picture in the middle, there's a little bar on the top of those two screens. That was $7,000, and that did your tracking for you. And it wasn't all that great compared to the Vive, right? But the Vive didn't exist at the time. And so we paid $7,000 for tracking. We paid about $1,000 per screen. And those are passive stereo screens. And that's running that's running some Vrui software, but some more visualization. So we're like cutting through a skull there. Anyway, 10, 12 years later, it still costs about $8,000, but now it's because the screen costs me $6,000, $7,000, and the tracking is like $300 or $400, right? Depending on how much, if I just take my tracking I buy a Valve Index, and I just use the tracking, and I set the head-mount display aside, right? So upstairs, I have a $6,000 projector, a $1,000 screen. If you just use your wall, you can save $1,000. And then the tracking from the Vive. And it's all running open source software. And my next slide, here's a little video of this running in my house. So this was before I brought it here, set up. And so there's two Vive trackers on the projection stand, old style Vive lighthouses. And then I'm using an old style Vive controller as well. And I have you can't see it because I have a counterweight on my left side, but on the other side, when I turn my head, you might see that there's little nodules of a small Vive puck stuck Velcroed to the glasses. Anyway, this is the setup. There's a projector on the floor there. And so we can do low cost cave style VR. And I wanted to talk a little bit about open source software, since that's what this conference is all about. And so all that stuff that I'm running is open source software, but there's actually several layers of it. But before I get to that, I want to talk a little bit about the history of some of the open source software, especially from the Cave perspective, from my perspective. So this is a couple of slides that I repurposed from a talk I gave in 2015 that Ryan's old boss organized when he was working for a different open source company for VR. And we gave this talk at the IEEE VR conference, the academic VR conference, and we were talking about open source software. And so part of my talk was the Cave library existed when Caves came into existence, which was 1991. And I really pushed them to open source it, but they had dollars in their eyes, and so they licensed it to another place. And so that kind of thwarted, to a degree, that, right? And so from that point on, all the other places that were building caves, everybody started writing their own stuff, right? Because nobody wanted to pay for it. And they all had PhD students that they could pay instead, a lot less. So, so we had this diaspora of VR libraries. So these were all open source libraries from the 90s. This is semi-geographically based. So Dive is from the UK, MRT is from British Columbia, Covice and Avango are both from Germany. Over on the other side, Panda 3D is from Disney in LA, CalVR is from San Diego. And I have arrows because Covice went to Illinois and then it went to San Diego. Covice actually morphed into CalVR there. FreeVR, which was my library, started in Illinois. I took it to Reno. Then I took it back to Indiana. So these are kind of, these libraries all over the place and just kind of, like I say, a diaspora of libraries. And I was really upset about that, right? I mean, it doesn't make me happy. We had, at some point, we were sharing applications and people could write one app and run it in someone else's cave. And you know, if there was some killer app out there, you were just kind of out of luck. And then I mentioned in a conversation here, one of those tools, and you know, someone might get upset if they hear this talk, is VR Juggler. And I tried to get VR Juggler to build, and I was not able to get it to build and/or can be configured. And so it's just like the people who wrote it are the people who used it, right? And so other people share that pain. And so, you know, it was just a mess, right? On the flip side of that, there was an application called CaveQuake 3 Arena, right? So CaveQuake, or Quake 3 Arena, was this, you know, multiplayer version of Quake. Someone had figured out the file formats, and so there was an open source library for reading the file formats. The guy in this picture, Paul Rylick, took that and put it into the VR experience. He first wrote it for the Cave library, the CaveLib. And then, as other libraries were out there, he wrote it and ported it to these other libraries. So if you get the CaveQuake code, which is out there, you can see the free VR version, the Juggler version, the CaveLib version, the Vrui version. BoxLib is the company that Paul started, so he has a company called VizBox, and then also kind of standard desktop stuff like SDL and Glut and stuff. When I gave this talk in 2015, I said this is what we want in an open source VR library. I'm not going to read that list to you. I'm going to talk about two of the ones I'm using upstairs. The first one is the one I wrote, FreeVR. So it was from, like I say here, a much simpler time. We didn't have Vulkan, we didn't have shaders, in fact. We had a couple of VR interface input systems, VRPN, or we wrote it ourselves. It's a project I began when I was at the University of Illinois at NCSA 24 years ago. And like I mentioned earlier, I was hoping not to have to write it. I wanted the original library to be open source and make a go of it that way. But that's the way life goes, right? So I wrote my own thing or worked with some people. One of my favorite things about it is I type make Linux, it's done in 10 seconds, right? I can run it on Linux, Mac, or Cygwin if I must. In addition to running VR apps in caves, it kind of has a lot of other tools that come along with it. So if you see it running upstairs, I can take the input data from it, feed it to Monado, right? So now I can do kind of some OpenXR. I can get Vive tracking. I can get, you know, tracking from 20 years ago. My library will read it, and then I can output Monado's remote inputs. It'll read from Vrui, which I'll talk about in a moment. And Vrui right now is the only way I know to get full 6 degree of freedom tracking out of Vive's lighthouses, you know, nicely, right? So, so I use Vrui to read that. FreeVR can read the Vrui. FreeVR can output to Monado or it can output to VRPN. ParaView reads VRPN. It's kind of an odd stack, but that's the way it goes. It has a little live view in the simulator, which I'll show in the next slide. I have lots of tutorials and example applications, but they're kind of out of date since everybody does head-mounted display stuff now. I have, you know, the ability to handle multiple users is all built in, a lot of stuff. In the upper right there is a statistics display, so you can see kind of rendering speeds and interaction input speeds on it on this while you're running it. It has an in-app help system, which is this one in the lower right rather. That little box in the middle tells you what all the buttons do, and you can turn that on and off. This box here is an old Tickle TK thing where I can actually control things and see how things are running while it's running. And then on the left here is my little simulator view where you can see what's going on as well. You can also, in the simulator view, move the head around, move the trackers around, and use that while you're testing your actual applications. So that was FreeVR. I got one slide on Vrui. So Vrui is another VR library built for caves, designed for scientific visualization. Because it's designed for scientific visualization, it has this notion that the data floats in front of you. So it's wasn't necessarily designed for kind of traveling through space. FreeVR basically has X11, I think, is the only thing you need to build it. So it has one dependency. Vrui has a couple extras because he has got a couple other features in it. One of the aspects that he has is he has a server for the inputs and then the renderer. So I can read that server stuff, and that's how I get my Lighthouse stuff into FreeVR. His has a built-in widget system, and so he has it so that those widgets will adopt basically if you're in the cave or on the desktop. And then one of his kind of recent additions, which is 5 years now, is he like I said, he interfaced it with the Lighthouse tracking and also then interfaced it to initially the DK2 and then the Vive, so you can render his stuff in head-mount displays. All right, and that is generally my talk. Here's my home setup, which is similar to what I described upstairs, except instead of the stereo glasses, I don't have a 3D TV in my office, but I do have a 40-inch monitor, and so I can run ParaView with that. And I have a little puck. I have a little camera mount headband that I wear, and so I can move my head around. Here you can see the FreeVR tracking in the right, and this is ParaView, kind of some sample data for ParaView. And that is basically it. And I have one goodbye video here. Oh, I don't have audio maybe. Doesn't matter. So this is my friend Gonzo here, and I visited him when he was at the end of filming his last movie, I guess, almost, and so he's just saying goodbye.
Thanks a lot.
Yeah.
Very nice, very nice. We'll have questions. So questions from the audience, maybe, and I'll be reading questions online. Yep, from Mateo here in Minneapolis.
Oh, Will, very nice talk. What would be a good way to start with cave stuff without investing more than $1,000?
Right. Well, so my home office, I just have my monitor and Vive tracking, right? I mean, that's basically what I do. I don't have stereo because stereo TVs went away, right? So that was, I don't know if I explicitly said that, but we used to buy our stereo TVs, right, for $1,000, and now I have to buy a projector, which means it's a lot more expensive to get my stereo. I mean, maybe if you go to eBay, you can find some 3D TVs on eBay, but that was really a big disappointment for us in that world, doing the cave fish tank stuff, when all the TV companies decided 3D was not selling or was not worth their effort, even though, especially if it was like passive 3D, it probably cost them like 10 cents per TV, right? So I don't know. Very disappointing.
Sorry, like, awesome. And in which repository could I start reading, like, how to start, what to compile, what dependencies to build, and some examples to test?
Right. So I have a website. So when I was at Indiana, we called our low cost, right, sub $10,000 systems, IQ stations. Stood for interaction. It's I-quadded, so, or quint, yeah, quadded. Indiana Interaction Immersive Interface, right? So I quadded IQ stations, and so I have iq-station.com, and I have a wiki on there where I've tried to document this stuff. The stuff, a lot of the old material is still there, and now I'm adding new material again since I'm kind of back doing that. So you'll find some old information because it talks about 3D TVs, right? And now I'm updating it for the new stuff. And we had back in like 2013 through 2016, we did like a little traveling show. Here's how you do this, right? And so we had these little seminars mostly for scientific visualization community so that we could spread that. And that's what we used that wiki page for.
We have a question here from remote viewers. So, have you considered or used a looking glass display?
So I have not used looking glass display. My colleagues at my previous employer, they did buy some looking glasses, right? So I've not seen one yet in person because I haven't gone back to visit them. But I feel like they're kind of small, right? I mean, you kind of put your head down there, you can see a little bit of the data. The thing that actually excited me maybe more than that is when I was at SIGGRAPH 2 months ago, Domenco was displaying they were doing auto tracking, but they have about a 40-inch or 36-inch screen that has auto stereo on it. So I feel like that might be where we go next.
And you'll find it interesting to see that Ryan is interacting here, and he says you could actually use a Wiimote, at tracking. And if you had
as Ryan says that, let me actually let me demonstrate that. I can demonstrate that really quickly, Ryan. Let's see. Because I just showed a video yesterday at a different talk, and if I and if I move my VNC to their VLC, I don't have audio though, but this is Johnny Lee, and this is probably what Ryan is referring to. So he's explaining that you can take a Wiimote, and the Wiimote knows where it's at in space, and I'll fast forward it since we can't hear him anyway, if I can find my mouse. And I'll get to the part where he shows it working, if I can find, oh, there it is. All right, so here we go. So he talks about it for a while, and let's jump forward. All right, so he's talking about he's going to put his camera with the sensor bar because he does it in the reverse. He has you can see the Wiimote under the TV, and he's about to demonstrate it. So here it is without tracking, right? So this is just these targets on the screen. He has them placed in different spaces in 3D, but he hasn't turned on the tracking yet. So in a moment, he'll turn on the tracking. There we go. So now he's demonstrating basically, so this is Fish Tank VR, right? And this is what Cave VR is really Fish Tank VR in multiple screens and a lot bigger generally. But yes, so you can do very cheap tracking with a Wiimote. I feel like Vive trackers are cheap enough. And if you already have a head-mount display that has lighthouses, you've got them at the ready. And so I feel like that's a pretty good solution too. But yes, good point, Ryan.
Cool. Looking through the audience, we're good. We have one more question from Jacob.
Let's see. How much do you know if other people are looking into like using tracking of bodies and like instead of having glasses on with little markers on, like are people starting to look into machine learning to like track the faces or track hands like we are doing?
Right. So for my work, I don't do that. But actually, I was going to mention, I do have another. Well, I mentioned it already that I do write some books, right? So when I'm doing this work, I care about everything VR, right? Regardless of whether I'm going to use it or not. So yeah, I mean, that's definitely one of the things when you go to SIGGRAPH, there's whole panels just discussing face tracking and having cameras out here or putting using the cameras that are now doing eye tracking to do more than that, to do facial recognition, get expressions and stuff like that. So yeah, I mean, I think that's basically a year away or less, right? I mean, that's just happening. Yep.
Great, thank you so much for that very nice presentation. Yeah. And that's it, even online. All right, thank you, and take care.
And if anybody wants to look through my books, I got 2 of them here. I have my Developer Gems book and my text. This is more of a textbook, this one.
We'll also post the references on the channel. Yeah. All right? Okay, cool. See you.
Yep.
right, thanks everyone. So this is it for FOSSXR 2022. It was amazing, guys, so thanks very much. So a big shout out to everyone, especially today. Very courageous people, very courageous presenters with live demos, very risky setups. We made it, so congrats to all. Sometimes it was kind of scary. I didn't think we'd do it, but it was finally all good. So just one, of course, last word for our two sponsors. Of course, the Kronos Group, thank you so much, and Collabra for sponsoring all this. Again, you know, you've seen it. I mean, nothing would have been possible without those two. So thank you so much again. And finally, well, this is it, right? 2 days full of talks, 25, almost 30 presenters, many people here were present. Thank you so much for watching live. And that's it. I'll just, stay tuned and we'll see. It's just, we'll meet next year, right, for FOSSXR 2023, right? All right. Thank you so much. Bye.